2 satisfiability, 2 SAT. The 2 SAT algorithm checks if there's a way to make a bunch of yes-no decisions that don't break any rules you've set. Imagine you're deciding who can sit where at a party, but some friends can't sit together. The 2 SAT algorithm is like a puzzle solver that tells you if you can seat everyone without any conflicts. Rule 1. If Amy sits with Ben, then Carla can't sit with Dan. Rule 2. If Dan sits with Ella, then Fred can't sit with Greg. The 2 SAT algorithm will tell you if your party seating plan can work out without any friend conflicts or if it's just not possible. Use cases, party seating arrangements, solving puzzles with simple rules, making schedules where certain things can't happen at the same time. Asterisk search algorithm. The asterisk search algorithm is a smart way to find the shortest path from one point to another. It uses a special trick, called a heuristic, to guess which path might be the best one to take, so it doesn't waste time looking at paths that are too long. It's like if you were in a maze and had a map that showed you where the end was. You'd try to take the paths that looked like they were going towards the end, instead of wandering around every corner of the maze. Use cases. This algorithm is used in GPS to find the quickest route, in video games to help characters move around, and in robotics for navigation. Ackermann function. The Ackermann function is a mathematical operation that takes two numbers and calculates a new number. It grows very fast and is not like simpler adding or multiplying functions. It's used to show how some calculations in math are really big and complex. If you have m equals sign 1 and n equals sign 2, the Ackermann function tells you to do some steps, like a treasure hunt, until you find the final number, which in this case is 3. Use cases. The Ackermann function is used in computer science to understand how some problems can take a really long time to solve and to explore the limits of what computers can calculate. AdaBoost, short for adaptive boosting, is an algorithm that improves the performance of machine learning models. It works by combining multiple weak learners to create a strong classifier. Simply example. Imagine teaching a child to stack blocks. At first, the child might not be good at it. AdaBoost is like a teacher who helps the child get better. The teacher starts by showing simple ways to stack one block on another. If the child stacks a block incorrectly, the teacher focuses on that mistake and shows how to do it right. Gradually, the teacher introduces more blocks and more complex stacking. Each time the child makes a mistake, the teacher helps them learn from it. Eventually, the child becomes an expert block stacker thanks to the teacher's guidance. Use cases. AdaBoost is commonly used in face recognition systems to classify emails as spam or not spam, and in biology for predicting protein structures. It helps improve the accuracy of predictions by learning from previous errors. Adam algorithm. The Adam algorithm is a method used to optimize the learning process in machine learning by adjusting how the model learns from data. Think of the Adam algorithm as a smart assistant for playing a video game. Suppose you're playing a game where you need to jump over obstacles. At first, you might not know how hard to press the jump button, but as you play more, you learn just the right amount of pressure needed to jump perfectly every time. The Adam algorithm helps a computer learn from data in a similar way, making it jump better over time by figuring out the best way to use the information it has. Use cases. The Adam algorithm is commonly used in training neural networks to recognize images or speech, helping self-driving cars make decisions on the road, optimizing recommendations for what you might like to watch or buy online. Adams-Bashforth method. This method uses previous information to predict future outcomes in a mathematical way. Think of a bouncing ball. By knowing how high it bounced before, the Adams-Bashforth method can help guess how high it will bounce next. Use cases. It's used to forecast weather, estimate population growth, or predict how a disease might spread. Adams-Moulton method. The Adams-Moulton method is a numerical technique for estimating solutions to ordinary differential equations, which are equations involving rates of change. Imagine you have a pile of sand, and you want to figure out how much sand there is. Instead of measuring each grain, you estimate by looking at how quickly the pile grows when you add more sand. Suppose you watch the pile for 4 days and notice it grows a little each day. By estimating how much it grew each day and adding those estimates together, You get an idea of the size of the whole pile. Use cases. This method is used by scientists and engineers to predict how things like weather, population, or cars move and change over time without having to measure every tiny part. Advanced Encryption Standard, AES. AES is a secure way to scramble information, so only the person with the right key can understand it. Imagine you have a secret note that you want to send to your friend without anyone else reading it. You use the AES method to scramble the note into a code that looks like random letters and numbers. You and your friend have a secret password, the key, that can turn the code back into the note. Even if someone else finds the coded message, they can't read it because they don't know the secret password. Use cases. AES is used to protect all sorts of information, like emails, bank details, and personal data, to make sure only the right people can see it. AES algorithm, a method to keep digital information safe by scrambling it with a secret key. Imagine you have a box of alphabet blocks and you want to keep the message they spell out a secret. You put them through a machine, the AES algorithm, which rearranges the blocks in a complicated way using a secret pattern. Only someone with the pattern can put the blocks back in the right order to read the message. Use cases, protecting personal data on computers and smartphones, securing online banking and shopping, keeping government and business communication private. Aho-Korasic algorithm. The Aho-Korasic algorithm is a fast method for finding multiple patterns in a text, saving time by using a pattern tree and fail-safe jumps. Imagine playing a game of I Spy where you're super quick at finding things because you look for specific colors and shapes together, like only red and round items for a red ball. This algorithm helps computers quickly find words or phrases in a large document, similar to how you'd find the red ball in our game, by following clues efficiently. Use cases include looking for keywords within web pages or detecting harmful patterns in network traffic. AKS Primality Test. The AKS Primality Test is a mathematical method that can quickly determine if a number is prime by using a special formula. To check if 13 is prime, we use a formula involving powers of a number, let's say x. We compare x1 circumflex 13 to x circumflex 13, 1, and then see if, when we divide by x1, we get a whole number without any leftovers. If this works for all numbers x, then 13 is prime. When we try it with 2, 3, 4, and so on, we find out that 13 passes the test for all of them, which means 13 is indeed a prime number. Use cases. The AKS primality test is used in mathematics and computer science to identify prime numbers, which are important for cryptography, number theory, and secure communications. All-pair shortest path. This algorithm finds the shortest route between every 2 points in a network, with multiple connections and distances. Think of a school with many rooms and corridors. This algorithm is like creating a school map to find the quickest route from any room to another. Use cases. It's used for planning efficient routes in transportation systems and optimizing data flow in computer networks. Alpha-beta pruning. Alpha-beta pruning is a technique for searching a game tree efficiently. It cuts off branches that can't possibly affect the final decision, making the search faster. Imagine playing tic-tac-toe and trying to predict the outcome of every possible move. Alpha-beta pruning helps by eliminating moves that won't improve your chance of winning, allowing you to focus on the moves that matter. For example, if you notice a move that leads to a loss, you ignore it and any moves that follow it, because they are irrelevant to achieving the best outcome. Use cases. This algorithm is used in games like chess, checkers, and tic-tac-toe to help players or computers decide on the best move by evaluating fewer possibilities, saving time and computational resources. American flag. Sort. This is a sorting method that groups items by their specific characteristics, much like organizing colored balls into the pattern of the American flag. Imagine you have a mix of red, white, and blue balls, and you want to line them up to match the American flag, with red followed by white and then blue. You first separate the balls by color into 3 groups. Now, go through each ball, placing it with its matching colors. If you want the balls perfectly ordered within each color, you can use another simple sorting method. In the end, you'll have a neat row of balls, looking just like the American flag's colors, in the right order. Use cases, sorting data with multiple categories, organizing files or items by specific attributes, grouping information before final sorting. Ant colony optimization algorithm. Ant colony optimization, or ACO, is a problem-solving method that mimics how real ants find the shortest path to food. By leaving scent markers called pheromones, ants signal to others which paths are best. This algorithm uses a similar idea to find efficient solutions to complex problems. Imagine ants exploring several paths to reach a sugar cube. They wander randomly at first, but leave a pheromone trail. The shorter paths get more traffic and, consequently, stronger pheromone signals. Soon most ants use the shortest path, guided by the strongest scent. Use cases. ACO is used for scheduling, routing, and network optimization. It helps in planning the most efficient delivery routes, arranging tasks and managing data flow on the internet, much like ants efficiently find their way to food. A priori algorithm. The a priori algorithm helps find patterns of items that are often bought together. Imagine that every time someone buys a pencil, they also buy an eraser. By looking at many shopping lists, we notice this pattern. The a priori algorithm helps us see that pencils and erasers are a frequent item set, a group of items bought together often. Use cases. This algorithm is useful for stores to understand what products to put on sale together or to recommend products to customers. For example, if bread and butter are a frequent item set, putting them on sale at the same time might increase sales. Arithmetic coding. Arithmetic coding is a technique for compressing data without losing any details. It turns a message into a single number between 0 and 1. Imagine you have the word hello, and you assign each letter a spot on a number line. H is 0 to 0.2, E is 0.2 to 0.5, L is 0.5 to 0.7, and O is 0.7 to 1. Each letter narrows the range until you have a unique number for hello. Use cases. This method is used to make files smaller, like when you zip a file on a computer or when you watch videos online without them taking too long to load. Artificial bee colony algorithm. The artificial bee colony, ABC, algorithm is a method for finding solutions to problems by mimicking how bees search for the best flowers. Imagine a game where bees fly around a garden to find the sweetest flower. Each bee remembers the sweetness of the flowers it finds and tells the other bees. Then, they all decide which flowers are worth visiting again, while some bees keep looking for new flowers. They keep doing this until they agree on the sweetest flower. The ABC algorithm is used in real life to solve complex problems like planning the best route for delivery trucks or figuring out the best shape for an airplane wing. Use cases: 1. Optimizing logistics and transportation routes. 2. Designing efficient engineering structures. 3. Finding the best parameters for industrial processes. AVL tree. A type of tree that stays balanced by making sure each level is only a little taller or shorter than the others. Imagine you're organizing books on a bookcase. You want the bookcase to be balanced so it doesn't tip over. If you put a thick book on the top left, you'll put a similar sized book on the top right. As you add more books, you might have to shift some around to keep the whole bookcase from leaning too much to one side. Use cases. Keeping a list of items so that you can find any item quickly. Making sure a computer game's world stays in order when things are added or removed. Organizing a library's books so that you can find any book easily. Babay's nearest plane algorithm. This algorithm quickly finds a point on a grid that's very close to the one you're looking for, without having to check every single point. Imagine you're in a big room with lots of dots on the floor, and you want to find the dot closest to where you're standing. Instead of walking to every dot, you find a dot that's kind of close and then look around for a closer one. Keep looking around each new dot you find until you can't find a closer one. Use cases. Babay's algorithm is used in math and computer science to solve problems that involve finding the best or closest answer quickly, like in GPS navigation or when organizing data in computers. Backpropagation algorithm. Backpropagation is a method used to train neural networks by adjusting their weights based on errors. It guides the network in improving its performance. Imagine teaching a child to stack blocks. Each time the child stacks a block incorrectly, you show the mistake and encourage trying a different way. Gradually, the child learns to stack the blocks better. Use cases. Backpropagation is used in various applications, including voice recognition, image classification, and any task requiring pattern recognition or decision-making by an AI system. Bacterial foraging optimization algorithm. This algorithm mimics the way E. coli bacteria search for food. It's like how ants look for the best path to a food source, avoiding obstacles and leaving trails for others to follow. Think of a group of robots in a room trying to find the quickest way to a charging station. They start searching randomly. When one robot finds a good path, it beeps louder for others to hear. A robot that hits a wall beeps softly. Over time, the robots learn from the beeping and figure out the best path to the charging station. Use cases. Engineers use it to design more efficient electrical circuits. Scientists apply it to create new medicines by finding the best chemical mixtures. Businesses use it to organize warehouses for faster shipping. Bat algorithm. This algorithm mimics how bats use sound to find their way around and locate food. Imagine playing hide and seek in the dark. You're it, and you clap your hands to hear the echoes bouncing off walls and objects, helping you find your friends. The louder and clearer the echo, the closer you are to someone hiding. Use cases. The BAT algorithm is used in various fields like engineering, computer science, and artificial intelligence to find the best solutions, similar to how you use echoes to find your friends in the dark. Batchers odd-even. Mergesort Batchers odd-even mergesort is a sorting method that works by splitting numbers into odd and even sets, sorting them separately, and then merging them. Imagine you have 10 numbered balls and you want to arrange them in order. You put all the balls with even numbers in one box and the ones with odd numbers in another box. After sorting each box, you then combine them, picking the smallest ball from each box until they are all in a single sorted line. Use cases. Organizing numbers or data in a specific order. Parallel processing in computers to sort large lists quickly. Any situation where efficient sorting is needed, especially when dealing with large data sets. Baum-Welch algorithm. The Baum-Welch algorithm is a method for improving the guesses of hidden sequences in a system based on observed outcomes. Imagine you're teaching a robot to dance, but you can't see the dance moves it's programmed to perform, only the final pose after each move. By observing these poses, you try different programming changes until the robot's dance routine seems to match the poses you expected. Use cases. The Baum-Welch algorithm is used in speech recognition to predict spoken words from sounds and in biology to analyze DNA sequences and understand genetic patterns. Bcrypt is a method for securing passwords by scrambling them into a complex format that's difficult to decode. Think of your password as a simple drawing. Bcrypt is like a magic box that transforms your drawing into a puzzle. Only with the right key can the puzzle be put back into the original drawing. Use cases. Bcrypt is used for protecting user passwords on websites. When you create an account, your password is turned into a puzzle by the Bcrypt magic box. If someone tries to sneak in, they can't because they don't have the key to solve the puzzle, keeping your password safe. Bead sort algorithm. Bead sort is a simple sorting method that arranges numbers by letting them fall like beads on a string, separating them into their own groups. Imagine dropping beads onto parallel sticks where each bead represents a number. The beads slide down the sticks and form piles at the bottom. The height of each pile reflects the original numbers, sorted from smallest to tallest. Use cases. Bead sort is often used in educational settings to demonstrate sorting and in situations where sorting by gravity can be simulated and visualized easily. Beam search algorithm. The beam search algorithm is a method for finding the best solution by only keeping the most promising options at each step, similar to shining a flashlight on the best paths and ignoring the rest. Think of playing a game where you must choose between multiple doors, but you can only open 2 at a time to see if they lead to the prize. You pick the 2 doors that look most likely to have the prize behind them. At each set of doors, you keep making the same choice, always picking the two that seem closest to the prize. This way, you're more likely to find the prize quickly without having to open every single door. Use cases. Beam search is typically used in situations where you have too many choices and need to find a good solution quickly without checking them all. It's commonly used in machine translation, speech recognition, and text summarization, where the algorithm has to choose the best words or sentences from many possibilities. Bees algorithm. The bees algorithm is a method inspired by how bees search for the best flowers, used by computers to solve complex problems by working together and sharing information. Imagine you're playing hide and seek with friends to find the best hiding spot. You look around and tell your friends about the good spots you find. Together, you figure out the best one. Use cases. The bees algorithm is used by scientists and engineers to find answers to tough questions, like designing airplane wings or planning delivery routes. By having a computer try different answers, share the results, and choose the best one, just like bees picking the best flowers for nectar. Bellman equation algorithm. The Bellman equation algorithm is a method used to find the best series of decisions in situations where outcomes are partly random and partly under the control of a decision maker. It breaks a big problem into smaller, easier-to-solve pieces. Think of it as playing a board game where you can choose different paths. Each turn, you decide the best move by considering how good the next turns could be. The algorithm helps you choose the path that leads to the highest score in the end. Use cases. Planning routes in transportation, developing game strategies, managing investments and finances, making robots and computers smarter in decision-making. Bellman-Ford algorithm. This algorithm finds the shortest paths from a starting point to all other locations in a map with possible negative distances, but no negative cycles. Imagine you're playing a board game with your friends. You are at the start space, and you want to figure out the fastest way to visit several other spots on the board and get back to the start. The Bellman-Ford algorithm is like a clever set of instructions that helps you move your game piece on the shortest possible path to each spot, even if some moves seem to take you backward at first. The Bellman-Ford algorithm looks at the distance from start to each spot one by one. It keeps checking and updating the fastest routes, considering every path available, even the ones that go in a roundabout way. If it finds a quicker way to reach a spot, it remembers that new route. After it has checked all the routes, it knows the fastest path to each spot on the board. You can use this algorithm not just in games, but for things like finding the quickest driving route in a city, even if some roads have detours or are longer than others. Use cases. The Bellman-Ford algorithm is really useful for 1. GPS navigation systems when they calculate the quickest route for your trip, including detours or unexpected one-way streets. 2. Network routing, where data packets need to find the best path through a complex network with various connection speeds and conditions. 3. Managing financial transactions to find the best exchange rates or detect any odd changes that could mean there's something wrong. Berlekamp-Massey algorithm. The Berlekamp-Massey algorithm is a method used to find the smallest set of rules that generates a sequence of numbers. If you have a sequence like 2, 4, 8, 16, the algorithm can determine that each number is twice the previous one. Use cases. This algorithm is particularly useful in cryptography, error-correcting codes, and signal processing where discovering patterns in sequences is essential. Bezier curve algorithm. This algorithm creates smooth curves in digital images by using fixed points to guide the shape of the curve. Imagine you're drawing a curved line with a magic pen that follows your instructions. You place some invisible helpers along the line. As you draw, the pen moves toward these helpers, making the line bend and twist to create a smooth curve. Use cases. Artists and designers use Bezier curves to craft everything from simple drawings to complex shapes in digital art, animations, and user interfaces. Bezier surface. The Bezier surface algorithm helps create gently flowing surfaces on a computer by calculating the curves between points that you choose. Pretend you're drawing a wavy flag with a pencil. You put dots where you want the corners of the waves to be, and then you draw smooth lines between the dots to make the waves. Use cases. This method is used in video games to design hills and valleys, in car design to model the body of vehicles, and in animation to create characters that look real and move smoothly. Big O notation, a way to measure how long it takes to run an algorithm as the amount of data increases. If you have a list of 5 numbers and want to find the largest one, you look at each number, one at a time, until you find the largest. Use cases. Big O notation helps us understand algorithms used in searching, sorting, and data processing tasks. Big O, when using Big O to describe the algorithm for finding the largest number in a list, we call it ON, where n is the number of items in the list. It means that if the list gets bigger, the time it takes to find the largest number grows at the same rate as the list size. For example, a list of 20 numbers will take 20 steps to find the largest number. Binary indexed trees, Fenwick tree. A binary indexed tree or Fenwick tree is a data structure that allows for quick updates and calculations of cumulative sums in an array. Imagine a row of 10 buckets, each holding some number of apples. You want to quickly find out how many apples are in buckets 3 through 7. By using a binary indexed tree, you can easily add the apples in this range without counting each bucket one by one. Use cases. Binary indexed trees are useful in scenarios where you frequently need to calculate the sum of a range of elements and update the values, such as in real-time data analysis, gaming score management, and computational geometry. Binary insertion. Sort binary insertion. Sort is a method of arranging items by inserting them in their correct position, using a binary search to reduce the number of comparisons. Imagine lining up toy cars by size quickly by taking one car, finding the right spot using few steps, and placing it there before picking up the next car. Use cases. 1. Organizing computer files by size or date. 2. Arranging books on a shelf alphabetically. 3. Sorting scores in games to show leaderboards. Binary search algorithm. This algorithm finds a specific item in a sorted list by halving the search area each step. Pretend you're looking for a red lollipop in a sorted lineup of 100 candies. Instead of looking at each candy one by one, you start in the middle. If the 50th candy isn't the red lollipop, you decide if the lollipop is likely before or after it. Then you look in the middle of that half and keep halving until you find the red lollipop. Use cases. Binary search is used in computer programs to quickly locate items in sorted databases, to find a specific word in a dictionary, or to search for a number in a list. Binary search tree. A binary search tree, BST, is a structured way to maintain a sorted list of numbers. It allows you to quickly find, add, and remove numbers. Imagine we have a treehouse club with a rule that younger kids stay on the left side of the treehouse and older kids on the right. If we have kids aged 10, 7, 15, 5, and 12, we'll put the 10-year-old in the treehouse first. The 7-year-old is younger, so they go to the left. The 15-year-old is older, so they go to the right. The 5-year-old is even younger than the 7-year-old, so they go to the left of the 7-year-old. The 12-year-old is older than the 10-year-old, but younger than the 15-year-old, so they go to the right of the 10-year-old but left of the 15-year-old. Use cases. BSTs are used in many applications, like managing sorted lists in databases, powering search engine results, and organizing files in a file system. They are excellent when you need to frequently add, search for, or remove items while keeping them in order. Binary search. Binary search is an efficient algorithm to locate a specific item in a sorted list by repeatedly dividing the search interval in half. If you're looking for the word banana in a dictionary, instead of starting from aardvark, you jump to the middle of the dictionary. If you land on kangaroo, you know banana is in the first half. So you split the first half in the middle again and repeat the process until you find banana. Use cases. Binary search is used in computer science for quickly finding items in sorted arrays, databases, and large lists. It's also used in coding problems where finding an element efficiently is crucial. Binary tree. Sort. This algorithm sorts numbers by putting them into a binary tree and then reading them back out in order. Imagine you have toys numbered 2, 5, 3, and 7. You put toy number 5 in a box. Toy 3 is smaller, so it goes in a smaller box to the left. Toy 7 is bigger, so it goes in a bigger box to the right. Toy 2 is even smaller, so it goes to the left of toy 3. Now to put them in order, first, you take out toy 2, then 3, then 5, and finally 7. Use cases, organizing books on a shelf by height. Arranging students in a line from shortest to tallest. Sorting numbers for a math game. Bipartite matching algorithm. This algorithm finds the best way to pair up members from two separate groups, ensuring as many individuals as possible are matched with someone they want to be with. Imagine 5 boys and 5 girls at a party. Each boy and girl write down who they would like to hang out with. The bipartite matching algorithm helps everyone find a friend from their list to hang out with, by making sure that if a boy and a girl have each other on their lists, they are paired together. Use cases, arranging one-on-one meetings between two groups of people, assigning jobs to workers where each worker has specific job preferences, matching students with schools or courses based on their preferences, organizing team projects by pairing teammates according to their collaboration preferences. Bisection method. The bisection method is a straightforward technique for finding a root, where a function equals 0, by repeatedly halving an interval and selecting the half that must contain the root. Imagine playing a game where you must guess a number between 1 and 100, and you're told it's below 50. Start by guessing 25. If wrong, ask if the number is higher or lower. If higher, your next guess is halfway between 25 and 50, 37. Keep halving the interval like this until you find the right number. Use cases. The bisection method is used for solving mathematical problems where you need to find values that make an equation true, such as finding interest rates for investments, physics problems involving forces, or engineering tasks like material stress analysis. Bisection search algorithm. Bisection search is an efficient method for finding a specific value in a sorted list by repeatedly dividing the list in half and eliminating the portion that doesn't contain the value. Imagine you're looking for the number 11 in a sorted list. 1, 3, 5, 7, 9, 11, 13, 15, 17, 19. You start at the middle, 9. Since 11 is greater, you look in the upper half, 11, 13, 15, 17, 19. The new middle is 15, but 11 is smaller, so you check the lower half, 11, 13. The middle is now 11, which is the number you're seeking, and you've found it. Use cases, finding a word in a dictionary, looking up a number in a phone book, searching for a specific username in an alphabetically sorted list. Bitonic sort is a sorting algorithm designed to work quickly on parallel processors, such as GPUs. It organizes numbers by comparing them and then combining them in a specific sequence. Imagine you have 10 marbles numbered 1 to 10 mixed up in a bag. To sort them using bitonic sort, you'd first split them into 2 smaller groups, say even and odd numbers. Within each group, you compare pairs of marbles and order them from smallest to largest. Once both groups are sorted, you combine them and sort the entire set of marbles in the same way, until all marbles are in order from 1 to 10. Use cases. Bitonic sort is useful in systems where multiple processors can work at the same time, such as in sorting large sets of data in parallel computing environments, or when using graphics processing units, GPUs, for non-graphical calculations. Block sort algorithm. Block sort is a method that organizes items by grouping similar ones together and then arranging these groups in order. Imagine you have a deck of cards with different numbers and you want to put them in order. Block sort would have you first make piles of the same numbers and then stack these piles in numerical order, starting with the lowest number. Use cases. 1. Sorting a collection of stickers by their color. 2. Arranging books on a shelf by their size. 3. Ordering a set of toys by their type. Bloom filter. A bloom filter is a quick and efficient tool that helps guess if an item is part of a group. It can mistakenly say an item is there when it's not, but it never misses an item that's actually there. Imagine a small toy chest called a bloom filter. You have toy blocks with names like apple, banana, or cherry written on them. You put each block into the toy chest. The chest can either say, "Yes, this name is here," or "No, this name isn't here." Sometimes the toy chest gets it wrong and thinks it has a name when it really doesn't. That's like thinking you found your favorite toy under the bed, but it's just a sock. The toy chest has secret compartments for the blocks. When you put a block in, some compartments say full. If you ask about a name, the toy chest looks in the specific compartments. If all say full, it says the name is there. If not, it says it's not there. The bloom filter is our quick checker for whether a block is in the toy chest. But remember, it might be wrong sometimes. Still, it's very helpful for a fast check. Use cases. 1. Checking if a word is in a dictionary before allowing it in a game. 2. Preventing your computer from visiting unsafe websites by quickly seeing if the site is on a known list. 3. Saving space in computer memory when a program needs to know if something was seen before. Blowfish algorithm. Blowfish is an encryption method that scrambles information using a secret key, making it unreadable to others unless they have the key. Imagine you have a note to send to a friend and you don't want anyone else to read it. You scramble the note using Blowfish and a secret key that only you and your friend know. To others, the note looks like random letters and numbers. Your friend who has the key unscrambles the note to read your message. Use cases. Blowfish is used to protect sensitive data, such as passwords and personal information, in various software applications and communication systems. Bloom-Bloom-Shub algorithm. The Bloom-Bloom-Shub algorithm is a method for creating numbers that seem random. It uses two large secret prime numbers to make it very hard for others to guess the pattern of the numbers it produces. Imagine picking two secret numbers, 3 and 7, then multiplying them to get 21. Now start with the number 2, square it to get 4, and use the remainder of 4 divided by 21 as the next random number. Keep squaring the result and finding the remainder by 21 to make new numbers. Use cases. This algorithm is often used to make secure codes in computers and to protect information. It is valuable because the numbers it makes are difficult to predict, making it useful for keeping things safe online. Bloomicali algorithm. The Bloomicali algorithm is a method for sorting items by attributes using a step-by-step process. Imagine you're sorting your colorful toys into groups. You separate them by color first, red, blue, and green. Then you sort each color group by toy type, cars, dolls, and blocks. The Bloomicali algorithm gives you instructions to do this efficiently. Use cases. The Bloomicali algorithm is useful for organizing things that have multiple characteristics, like sorting toys by color and type, so you can find what you want easily. Bogasort. Bogasort is a simple but highly inefficient sorting method that shuffles a list until it happens to be in the correct order. Imagine you have a deck of cards. You shuffle them and then see if they're in order from lowest to highest. If they're not, you shuffle again. You repeat this until the cards are sorted. Bogasort is like playing a game of chance with the cards, shuffling and checking repeatedly. It's straightforward but can take a very long time, similar to looking for a needle in a haystack. Use cases. Due to its inefficiency, Bogasort is not used for practical sorting tasks. It's mainly used for educational purposes, to demonstrate how not to sort a list and to understand the basics of sorting algorithms. Bose-Nelson sorting algorithm. The Bose-Nelson sorting algorithm is a method used for arranging items in a certain order by comparing and swapping them two at a time until they are all sorted correctly. Imagine you have 5 pencils of different lengths. To sort them from shortest to longest using the Bose-Nelson algorithm, you compare the first pencil with the second. If the first is longer, you swap them. Next, compare the second, previously the first, with the third, swapping if necessary, and so on until the last pencil. Repeat the process until all pencils are in order from shortest to longest without any need to swap. Use cases. This algorithm can be used for sorting objects like books on a shelf by size, cards in a game by rank, or even clothes in a drawer by color. It's a straightforward sorting method, similar to how you might naturally organize things in everyday life. Bowler hat. Sort algorithm. Bowler hat. Sort is an algorithm that organizes items in order using a method similar to a priority queue. Imagine you have a line of kids and want to order them by height without measuring. Each kid imagines wearing a hat that represents their height. One by one, they visualize stacking their hat on the previous kid's hat, keeping track of the combined height. In the end, they reorder themselves based on these imagined hat stack heights, from shortest to tallest. Use cases, organizing data in a structured manner, sorting elements in a list or database, prioritizing tasks or items based on certain attributes. Boyer-Moore algorithm. The Boyer-Moore algorithm is a fast method for finding a specific sequence of characters within a larger text. Imagine you're playing a game where you must find the word cat in a sentence. Instead of reading every letter from the beginning, Boyer-Moore might suggest you start with the last letter of cat and then jump ahead, skipping unnecessary letters, to find the word much quicker. Use cases. 1. Word processors use it to find words in a document. 2. Web browsers use it to search for text on a web page. 3. Database systems use it to match patterns in data. Boyer-Moore horsepool algorithm. The Boyer-Moore horsepool algorithm is an efficient method for finding specific sequences within text by skipping sections that don't match a predetermined pattern. Imagine you're looking for a tiny, specific toy car in a large box of assorted toys. Instead of checking each toy one by one, you remember that the car has a unique red hood. You start by looking for toys with red hoods, skipping those without it. By focusing on the red hood feature, you find the car quickly. Use cases. Searching for a word in a document or a web page. Finding a sequence of DNA in a genetic database. Detecting plagiarism by comparing texts for matching strings of words. Branch and bound algorithm. Branch and bound is a technique to solve problems by dividing them into smaller parts, branch, and choosing the most promising options, bound, to find the best solution efficiently. Imagine trying to complete a puzzle in the fastest way. Instead of trying every single piece in every spot, you start with one piece and then only consider places for the next pieces that make sense. This way, you avoid wasting time on combinations that won't work. Use cases. Finding the shortest route for a delivery truck to visit several locations, traveling salesman problem. Creating the best schedule for machines in a factory to make products efficiently. Deciding the order to complete tasks when resources are limited, resource allocation problems. Breadth First Search, BFS. BFS is a method for exploring a network, like a map or a family tree, by first visiting all the places or people close by, then moving out to those farther away. Imagine you're at a park and you're looking for your friend, but you're not sure where they are. You start at the playground and ask everyone there if they've seen your friend. Next, you move to the picnic area right next to the playground and ask everyone there. You keep moving to new areas, one by one, always visiting the places that are closest to the last place you searched. You do this until you finally find your friend. Uses cases. Finding the shortest path from one point to another in a maze or city streets. Organizing games with many players so everyone knows when it's their turn. Making sure computers in a network can send messages to each other in the most efficient way. Brent's cycle detection algorithm, an algorithm that identifies if there is a loop in a sequence of elements. Imagine 4 kids, Alex, Ben, Charlie, and David, in a circle playing catch. If Alex throws the ball and it eventually returns to him, that's a cycle. Brent's algorithm uses 2 pointers moving at different speeds through a sequence. Like in the kids' game, if the fast-moving pointer, throwing the ball twice as fast, catches up to the slow-moving one, a cycle exists. Use cases. This algorithm helps find loops in computer programs, networks, and data structures. If the pointers meet, there's a loop. If not, there isn't. Brent's method. Brent's method is a mathematical algorithm used to find the root of a function by combining elements from the bisection, secant, and inverse quadratic interpolation methods. Imagine looking for your favorite book on a large bookshelf without knowing where it is. You start at one end and pick a book. If it's not the favorite, you guess another book, maybe far away from the first. Each time you pick a book, you get a clue if you're closer or further away. You use these clues to make smarter guesses, moving closer to the book each time until you find it. Use cases. Brent's method is used in situations where a precise solution is needed and other methods might fail or be less efficient. It's commonly applied in scientific computing and various engineering fields to solve equations where the exact root is unknown. Bresenham's line algorithm, a method for drawing straight lines on a pixelated surface using a step-by-step approach. Imagine you want to draw a straight line from one corner of a checkerboard to another. Bresenham's line algorithm tells you how to move from square to square so that the line looks straight and smooth without any jagged edges. You want to connect two dots on a piece of dotted paper with a straight line. Start at one dot, let's call it dot A, and use the algorithm to figure out which dots to connect in a straight path to reach the other dot, dot B. Use cases. This algorithm is used in computer graphics for drawing lines on screens, in computer-aided design for plotting lines on virtual grids, and even in CNC machining for creating linear paths. Brick sort algorithm. Brick sort is a simple sorting technique that alternates between sorting pairs and sorting odd and even indexed elements until the list is in order. Imagine you're lining up your Lego bricks from the lightest to the darkest. First, you compare every two bricks side by side, swapping them if the lighter one is on the right. Then you compare the bricks in all the odd spots, followed by all the even spots. You continue this swapping process, alternating between pairs and odd-even positions until all your Lego bricks are lined up correctly from light to dark. Use cases, organizing small data sets where simplicity is more important than efficiency. Educational purposes to demonstrate basic sorting concepts. Bron-Kerbosh algorithm. The Bron-Kerbosh algorithm is a method to find all groups of interconnected friends, maximal cliques, in a network of friends, undirected graph. Imagine you want each person at a party to have friends in every direction they turn. The Bron-Kerbosh algorithm helps you find all the possible friend circles where everyone knows each other. First, we list all potential friend circles, then we check each circle. If everyone is friends with everyone else, we keep it. If not, we remove it. We repeat this until we have all happy friend circles where no one is in more than one circle. This algorithm helps organize events, map social networks, or solve puzzles where groups must be closely connected without overlaps. Use cases: party planning for well-matched guest groups, social network analysis for understanding communities, puzzle solving where tight-knit groups are required. Brute force string matching. This algorithm searches for a specific string within a larger text by checking each position one by one. Imagine you're playing a game where you need to find the word cat in a jumble of letters. CATDOGHAT. You start at the top left and check if C is there. If yes, look for A right next to it, then T. If any letter doesn't match, you move to the next starting point and try again. Repeat this until you find cat or run out of places to check. Use cases: word search puzzles, searching for a word in a document, finding a sequence in DNA strings. Bubble sort: a simple sorting method that compares and swaps adjacent items until the whole list is in order. Imagine you have numbered cards out of order, like 4, 2, 1, 3. Starting with the first two cards, 4 and 2, you swap them because 4 is bigger. Now you have 2, 4, 1, 3. Next, compare 4 and 1 and swap again. Keep comparing and swapping until the cards are in ascending order. 1, 2, 3, 4. Use cases: bubble sort is used in computer programs where data needs to be arranged in a specific order, like sorting names in alphabetical order or organizing scores from lowest to highest. Bucket brigade algorithm. The bucket brigade algorithm is a method for sorting numbers by passing them through a series of buckets, with each bucket sorting part of the list. Think of having playing cards numbered 1 to 10. You and your friends line up, and each person takes a few cards. Starting from one end, each person arranges the cards they have in order. Once sorted, they pass the organized cards to the next person. In the end, the cards are all sorted from 1 to 10. Use cases. This algorithm is used in situations where parallel processing can speed up the sorting of data, like in some computer systems or collaborative tasks where tasks are shared among many workers. Bucket sort bucket. Sort is a method where you group items into buckets based on their value and then sort each bucket. Think of it like sorting socks. You put all the socks of the same color into separate piles, buckets, and then arrange each pile by size. Imagine you have 10 apples of different sizes, and you want to line them up from smallest to largest. You put the small apples in one bucket, medium in another, and large in a third bucket. Then you sort the apples in each bucket. After that, you take the apples out of the buckets, starting with the small ones, followed by the medium, and then the large ones. Now your apples are sorted. Use cases. Bucket sort is useful when you need to sort a large number of things, like sorting lots of books by their genres before arranging them by author name within each genre, or when you have data that's evenly distributed and you want to sort it quickly. Burrows-Wheeler transform inversion. This algorithm reverses the Burrows-Wheeler transform to get back the original text from its transformed version. Starting with the transformed word "nane" for banana, we follow steps to reconstruct banana. Use cases. It's helpful in data compression and bioinformatics for managing and examining large data sets effectively. Burrows-Wheeler transform. The Burrows-Wheeler transform is a way to reorganize the letters in a word to help compress it better. Take banana. 1. Rotate banana in every possible way. Banana ananab, nanaba, anaban nabana. Abanan 2. Sort the rotations alphabetically. Abanan anaban ananab banana banana nabana nanaba 3. The last column's letters give us ANBNA. The transformed ANBNA groups similar letters together, making it easier to compress. Use cases. This method is used in data compression to make files smaller so they can be stored and sent more efficiently. Canny edge detector. The canny edge detector is a method to identify the outlines of objects within images by detecting contrasts in brightness. Consider a photo of a cat. To outline the cat, the canny edge detector first reduces random specks in the image. Then it scans for areas where the brightness changes sharply, marking possible borders. It prioritizes the most distinct brightness shifts to find the cat's clear edges. Lastly, it links these edges to trace the cat's shape. Use cases. This algorithm is useful in various applications such as enhancing image clarity in photography, identifying objects in satellite imagery, assisting in medical image analysis, supporting driver assistance systems in vehicles, facilitating character recognition in scanned documents. Cartesian tree. A Cartesian tree is a tree where the root is the smallest number in a list, and the process repeats for sublists to form the tree. Given numbers 3, 6, 7, 2, 9, 1, find the smallest number 2 for the root. 2. Split list into left 3, 6, 7 and right 9. 3. Find smallest left number 3 for left child. 4. Split the left part into 6, 7, continue the process. 5. Right number 9 is the right child, no split needed. Resulting tree 2, 3, 9, 6, 7. Use cases. Creating priority search trees. Range minimum queries in sequences. Data structure for sequence alignment in computational biology. Catalan numbers. Catalan numbers are a sequence of natural numbers that uniquely determine the number of possibilities in certain combinatorial situations. Imagine you have 2 different colors of bracelets, red and blue, and you want to know how many distinct arrangements you can make by pairing them without overlapping. The Catalan number for 2 pairs, an equal sign 2, tells us there are 2 ways to do this. Use cases. Catalan numbers are useful in problems like counting the ways to correctly match parentheses in expressions, arranging non-intersecting diagonals in polygons, and different tree structures in computer science. They help mathematicians and computer scientists figure out the number of possible solutions to these types of problems. Chinese remainder theorem. The Chinese remainder theorem is a method to solve a puzzle where you need to find numbers that fit certain rules for remainders when divided by other numbers that don't share any factors other than 1 with each other. Imagine you have 3 baskets and you want to evenly distribute 7 apples into them so that when you take out the apples, each basket gives you a different number of apples back. To do this, you follow the Chinese remainder theorem to distribute the apples in a way that the remainders will match your plan when taking out the apples basket by basket. Use cases. This theorem is used in scheduling problems, computer science for managing data, and in cryptography for securing information. It helps to create patterns that are predictable if you know the secret rules, but seem random or scrambled without them. Cocktail shaker. Sort cocktail shaker. Sort is a bidirectional version of the bubble sort. It alternates sorting passes from the beginning to the end and then from the end to the beginning, ensuring elements are shifted into their correct place in both directions. Imagine sorting a row of colored pencils. You compare the first two and swap them if they're out of order. You keep doing this to the end of the row, then reverse, swapping pencils in the opposite direction until you reach the start. Repeat this process until all pencils are neatly arranged from lightest to darkest. Use cases. Cocktail shaker. Sort is useful for small or mostly sorted lists, where you need to ensure that both small and large elements are moved efficiently to their respective ends. It's used in scenarios where an element might be very far from its sorted position, but the list on the whole is almost sorted. Cohen-Sutherland algorithm. The Cohen-Sutherland algorithm is a method used to determine which parts of a line are inside a rectangular area and which are outside. Imagine you're looking at a picture, but only want to see the part that fits inside a certain frame. The Cohen-Sutherland algorithm is like a set of rules that helps you trim the edges of the picture so only the part inside the frame is shown. For example, if you draw a line on a piece of paper, but only want to keep the part inside a rectangle you drew, this algorithm tells you where to cut the line so it fits perfectly inside the rectangle. Use cases. This algorithm is used in computer graphics to draw lines within the boundaries of a screen or window. It helps computers figure out what to show and what to hide, making images look right on your screen. Coin change algorithm. This algorithm calculates the smallest number of coins needed to make a specific amount of money. To make 7 cents, use 1 nickel and 2 pennies. Use cases. It's used in financial systems, vending machines, and by programmers to minimize the number of coins given as change. Collaborative filtering. Collaborative filtering is a technique used to predict a user's interests by analyzing the likes and dislikes of many users. Imagine you're part of a club where everyone shares their favorite books. You notice some books are favorites among several members. If you're looking for a new book to read, you'd probably pick one that many in the club enjoyed. Use cases. Collaborative filtering is used by services like Netflix or Amazon to recommend movies or products to users by identifying patterns in the preferences of a large group of users with similar tastes. Collat's conjecture. A mathematical puzzle that predicts any positive number will eventually reach one through a simple process of halving if even, or tripling and adding one if odd. Start with any positive number. If it's even, divide by 2. If it's odd, multiply by 3 and add 1. Repeat the process with the new number. The claim is that you'll always arrive at 1. Begin with 6. It's even, so we divide by 2 and get 3. Now it's odd, so we multiply by 3 and add 1, resulting in 10. We continue this way. 10 becomes 5, then 16, 8, 4, 2, and finally 1. And indeed, we end up at 1. Use cases. The Collat's conjecture is used as a basis for research in number theory and computer science, and as a test case for computational experiments. Comb sort. Comb sort is a faster version of bubble sort that sorts items by comparing and swapping them over larger gaps, which then get smaller with each pass. Imagine you're lining up race cars based on their numbers. First, you compare cars that are far apart and switch places if needed. Each time you go back to the start, the distance between the cars you compare gets smaller until you're comparing cars that are right next to each other, ensuring they're all in the right order. Use cases. Organizing large sets of data. Improving sorting speed over basic algorithms like bubble sort. Situations where simplicity and easy implementation are important. Connected component labeling algorithm. This algorithm identifies and counts groups of connected items in an image. Imagine a coloring book page with several balloons that are either connected or separate. This algorithm would color each group of connected balloons with the same color to show they are together, and use different colors for other groups or single balloons. Use cases. In a medical image, it can help highlight connected organs or tissues. In satellite photos, it can identify clusters of buildings or vegetation. For quality control, it can detect defects that are grouped together on a surface. Content-based filtering. This method recommends items by comparing item content to your preferences. Imagine you love apple-flavored candy. The algorithm notes this and suggests other apple-flavored sweets. Use cases. Content-based filtering is like having a smart friend who knows you love stories about wizards. So, they recommend books with wizards for you to read. Convex hull algorithm. The convex hull algorithm calculates the smallest shape with straight edges that encloses all of the points in a set. If you scatter some nails on a board and then stretch a rubber band around them, the rubber band will snap into a shape that touches some of the outer nails, creating a border. This border is the convex hull. Use cases. 1. Creating boundaries around geographic locations on maps. 2. Determining the range of sensors in a field. 3. Finding the smallest area to investigate in search and rescue operations. 4. Analyzing patterns and shapes in data visualization. Convolutional neural network, CNN. A CNN is a type of computer program designed to recognize patterns in images. It works by examining small sections of an image for features like edges or colors, and then combines these details to identify objects. Imagine a game where you have to sort pictures of cats and dogs. A CNN would look closely at each picture, noticing the whiskers of a cat and the shape of a dog's nose. It uses these clues to sort each picture into the right group. Use cases. CNNs are used for facial recognition in security systems, for diagnosing medical images, sorting photos in your phone's gallery, and even for self-driving cars to understand their surroundings. Cooley-Tukey. Fast Fourier Transform, FFT. The Cooley-Tukey FFT is a fast method for computing the discrete Fourier transform, which breaks a large set of data into smaller chunks for quick processing. Consider you have a puzzle with 100 pieces. Instead of trying to fit pieces randomly, you divide the puzzle into 10 groups of 10 pieces and solve each small group first. Then, you put the solved groups together to complete the whole puzzle quickly. Use cases. The FFT algorithm is widely used for processing digital signals in music, engineering, and image compression, making tasks like voice recognition and image analysis faster and more efficient. Coppersmith's attack algorithm. This algorithm helps to find the factors of large numbers more easily by focusing on finding small solutions to polynomial equations with a modulus. Imagine you have a large number, like a giant puzzle piece, and you need to find the smaller pieces that fit together to create it. Coppersmith's algorithm gives you a special magnifying glass to spot these small pieces quickly. Use cases. Coppersmith's attack algorithm is used in cryptography, particularly for breaking encryption methods that rely on the difficulty of factoring large numbers. Counting sort counting. Sort is a sorting technique that arranges items by counting how many times each unique item appears. It's like sorting items into groups and then lining them up group by group. Imagine you have 5 apples, 3 oranges, and 2 bananas. With counting sort, you would first count each fruit, 5 apples, 3 oranges, and 2 bananas. Then you would place all the apples in a row, followed by all the oranges, and then the bananas, resulting in a sorted collection of fruit. Use cases: 1. Organizing a deck of cards by number or suit. 2. Sorting students in a class by their grades. 3. Arranging books on a shelf by genre. Count-Min sketch algorithm. The Count-Min sketch is an efficient tool that estimates the frequency of different events in a data stream, with a slight chance of slightly overestimating the numbers. Imagine you have a large jar filled with marbles of various colors. You want to estimate how many marbles of each color are in the jar, without counting each one. You take several small boxes, each representing a different color. Every time you grab a marble from the jar, you make a note in the corresponding box. Rather than keeping an exact tally, the Count-Min sketch helps you estimate the number of marbles roughly, using a special formula that saves time and effort. Use cases. Tracking the number of visitors to different websites, calculating the popularity of hashtags on social media, monitoring the frequency of words or phrases in text streams, managing inventory levels in real-time data feeds. Cube sort is a method that organizes items by repeatedly grouping and reordering them in a grid format. Imagine you have a cube similar to a Rubik's Cube, but instead it's used to organize colored blocks. You shuffle the blocks on the cube and then side by side arrange them until each side has its blocks in the correct order, like solving a color-coded puzzle. Use cases. Cube sort is useful for arranging items in an orderly manner, akin to tidying up various objects into their designated spots. Cuckoo hashing. Cuckoo hashing is a method for organizing data in a hash table using two hash functions for placement and a process of displacing existing items for new insertions. Imagine you have a toy chest with only two compartments to store your toys. To decide which compartment to use, you roll two different dice. Each die represents a hash function. Whichever number you roll tells you the exact spot for your toy. If a toy is already there, you take it out and try the second compartment with the other die. If that spot is also full, you move that toy and try again with the first die. You keep doing this until every toy has its own space. This is like cuckoo hashing, where you keep moving items until everything fits without any mix-up. Use cases. Cuckoo hashing is used in databases to quickly store, search, and delete data. It's also useful in networking for routing tables and in memory caches for fast access to data. Cuckoo search algorithm. Cuckoo search is an optimization algorithm inspired by cuckoo birds' egg-laying strategy. It simulates cuckoos laying eggs in different nests and finding the best one for hatching. Think of a scavenger hunt where players are cuckoo birds searching for the best spot to hide their treasure, eggs. Initially, they pick random spots, nests. They check other players' spots and move their treasure to better ones if found. The game ends when a player finds the best hiding spot. Use cases. This algorithm is useful in engineering for designing efficient systems, in economics for optimizing investments, and in logistics for route planning. Cycle sort is a sorting algorithm that reshuffles items into their correct order by following a cycle pattern. It's efficient because it minimizes memory use and the number of swaps. Imagine you have a line of numbered cards out of order. Cycle sort helps you find each card's correct spot by tracing a path, cycle, from one card to the next, swapping cards until each one is in its rightful place. Use cases. Organizing data with minimal memory and fewer changes. Efficiently sorting when minimizing the number of writes to memory is important, such as with flash memory to prevent wear. Damoreaux-Levenshtein distance algorithm. This algorithm calculates how similar two words are by finding the least number of steps needed to change one into the other. These steps can be inserting, deleting, replacing, or swapping letters next to each other. With cat and bat, we just replace C with B, so the distance is 1. Comparing kitten to sitting, we replace K with S, E with I, and add G to the end, making the distance 3. Use cases. It's used in spell checkers, DNA sequencing, and anywhere we need to see how different two pieces of text are. Data encryption standard, DIS. DIS is a method for securing information by scrambling it into an unreadable format, which can only be decoded with a specific secret key. Imagine you write a note and then cut it up into tiny pieces. DS is like gluing those pieces back together in a mixed-up order that only your friend knows how to put right, making your note secret to anyone else. Use cases. DS is used to protect sensitive data in banking, communications, and passwords, ensuring that only authorized parties can access the information. DBSCAN algorithm. DBSCAN is an algorithm that finds clusters of closely packed data points and distinguishes them from less dense, isolated points. Imagine your room is a bit messy with toys everywhere. Some toys are in groups, while others are all by themselves. If you had a magic magnifying glass that could show you which toys are in a group by drawing a circle around them, you would quickly see where each group is. The magnifying glass can move around the room, finding all the toy clusters for you. Use cases. DBSCAN is great for organizing things based on how close they are to each other. For example, it can identify which houses in a neighborhood are close enough to be considered a tight-knit community. It's like having a tool that spots which things belong together based on how near they are to one another. Decision tree algorithm. A decision tree is a method used to make decisions or predictions by asking a series of yes or no questions. Each question leads you down a different path until you reach a decision. Think about sorting fruits. You have an apple and an orange, and you want to sort them using a decision tree. Your first question might be, is the fruit round? If yes, go to the next question. If no, it's not one of our fruits. Then ask, does the fruit have a green color? If yes, it's an apple. If no, it's an orange. Use cases. Decision trees can be used for deciding what clothes to wear based on the weather, choosing what food to eat based on your preferences, or even for a doctor to diagnose illnesses based on symptoms. Delta encoding. Delta encoding is a technique for storing or transmitting data in the form of differences between sequential values rather than complete records. Consider the sequence 5, 8, 10, 12, 15, 18, 20, 25. Using delta encoding, we record the initial value of 5 and then the differences, plus 3, plus 2, plus 2, plus 3, plus 3, plus 2, plus 5. Use cases. Delta encoding is useful in compressing data, reducing storage needs, and highlighting trends in datasets, such as in numerical data streams or time series data. Depth-first search, DFS. Depth-first search, DFS, is an algorithm that explores a graph or maze by going as deep as possible down each path before trying a new one. Imagine you are at the start of a maze and you need to find the exit. You choose one path and keep following it, taking every turn until you can't go any further. If you reach a dead end, you backtrack to the last place where you could choose a different path and explore that new path in the same way. You mark the paths you've checked so you don't repeat them. It's like being an explorer in a tunnel system, making sure to investigate every single branch to its end before choosing a new direction. Use cases. 1. Solving mazes or puzzles where you need to explore all possible routes. 2. Analyzing networks like roads or computer connections to find all possible paths from one point to another. 3. Organizing tasks when you need to follow each step to completion before moving to the next. Depth-limited search. Depth-limited search is a version of the depth-first search algorithm that includes a predetermined limit on how deep the search can go. It's like exploring a cave with a rope. You can only go as far as the rope allows before returning to try another path. Imagine you're trying to find a toy in a stack of boxes, but you can only open up to 3 boxes on top of each other. If the toy isn't in those 3, you close them up and try a different stack of 3 until you find it. Use cases. Depth-limited search is useful in scenarios where searching to an unlimited depth is impractical or when the solution is likely to be found closer to the root. It's commonly used in games, solving puzzles, and navigating through networks or hierarchies where the depth of searching needs to be controlled to avoid excessive processing. Deutsch-Josche algorithm. A quantum algorithm that quickly determines whether a function is constant, all outputs the same, or balanced, outputs evenly different. Imagine having a box with an even number of balls, each ball either black or white. The Deutsch-Josche algorithm is like a magic trick that instantly tells you whether all balls are the same color or half are black and half are white without needing to check each ball one by one. You have a box with balls that are either all black or half black and half white. Using the algorithm is like asking a genie a single question to reveal if all the balls are the same color or split evenly. The genie answers in a snap, saving you from checking each ball. Use cases. This algorithm is used in quantum computing to solve problems involving checking the uniformity of large datasets, optimizing search functions, and testing the properties of mathematical functions more efficiently than traditional computers. Differential evolution algorithm. Differential evolution is an algorithm that improves a set of solutions over time to find the best one, much like players updating their strategies in a treasure hunt. Imagine you and your friends decide to find a treasure marked on a map. Each of you starts with a different search pattern, straight lines, zigzags, or circles. As you search, you notice which patterns are better and adjust your approach accordingly. Over time, everyone improves their search methods until one of you finds the treasure. Use cases. Optimizing engineering designs. Finding the minimum or maximum of mathematical functions. solving real-world problems in economics, genetics, and other fields, requiring optimal solutions. Diffie-Hellman key exchange. The Diffie-Hellman key exchange is a process that enables two parties to create a shared secret key which they can use to encrypt messages in a way that no one else can read, even if they are using an open communication channel. Imagine you and your friend want to have a secret conversation using a public bulletin board where everyone can see your messages. To keep your conversation private, you both decide to use a secret color no one else knows. You each choose a private color, but also agree on a third public color. You mix your private color with the public one, then exchange these mixtures on the bulletin board. Now each of you adds your private color to the mixture you received. Even though the mixtures were public, the final private colors that result are identical and secret, as they cannot be easily separated from the public color. This secret color is like your shared secret key for communicating securely. Use cases: encrypted communication over the internet, such as secure websites, HTTPS, creating secure VPN tunnels for private network access over the public internet, securing the exchange of keys in various cryptographic protocols. Digital Signature Algorithm, DSA. DSA is a method for creating a unique mark on digital content, much like a handwritten signature, using public key cryptography to confirm the origin and integrity of the content. Imagine you have a secret recipe for chocolate chip cookies that you want to give to your friend securely. You use the DSA algorithm to add a unique digital signature to the recipe. Your friend uses a special code you gave them to confirm that the recipe really came from you and was not altered. Use cases: DSA is used to ensure secure communication, validate software downloads, and confirm the authenticity of online documents and transactions. Dijkstra's algorithm. Dijkstra's algorithm is a method for finding the shortest path between 2 points on a map, like the quickest route from one city to another. Imagine you want to bike from your home to your school, and you want to take the quickest path. You make a list of all the streets you can bike on from your home and how long each one takes. You always choose the street that gets you closer to school in the shortest time, updating your list as you go. When you reach school, you found the shortest path thanks to this step-by-step process. Use cases: navigation apps for finding the fastest route, network routing to transfer data efficiently, robotics for pathfinding in an environment, planning and scheduling where sequences of tasks are involved. Dijkstra's shortest path algorithm. Dijkstra's shortest path algorithm is a method to determine the quickest route from a starting point to other locations in a network. Imagine you have a treasure map with several paths leading to the treasure. You want to find the shortest path to the treasure. Dijkstra's algorithm would be like hopping from one landmark to another, always taking the shortest available path until you reach the treasure. Use cases: GPS navigation systems for finding the fastest route, network routing protocols to transfer data efficiently, planning efficient routes for delivery services. Dijkstra's algorithm. Dijkstra's algorithm efficiently calculates the maximum amount of flow that can pass from a source to a sink in a network. It is built to avoid redundancies and ensure the shortest path is found quickly. Imagine you want to fill a pool with water using a system of pipes. Dijkstra's algorithm helps you figure out the fastest way to get the most water through the pipes to fill the pool. Use cases: optimizing water distribution in irrigation systems, managing network traffic to avoid congestion, allocating resources in manufacturing processes. Discrete cosine transform, DCT. DCT is a technique that changes pictures or sounds into a set of numbers that are easier for computers to handle. It's often used to make files smaller so they take up less space. Imagine you have a drawing made of colored blocks. DCT is like creating a list that tells you how many blocks of each color there are and where they are in the drawing instead of describing every single block. Use cases: making photos and videos take up less space on your phone or computer, helping websites load images and videos faster, ensuring clear video calls even when the internet is slow. Discrete Fourier transform, DFT. The discrete Fourier transform, DFT, is a tool that changes a list of numbers representing a signal, like musical notes, into another list of numbers that shows the strength and pitch of each part of the signal. Imagine you're clapping a rhythm with your hands and you want to find out the pattern of your claps. DFT is like a detective that listens and tells you how fast and slow your claps are and how they mix together to make the rhythm you hear. Use cases. DFT is used in music to analyze sounds, in engineering to study electronic signals, and in science to examine waves and vibrations. It helps us understand and recreate signals in many fields like audio processing, telecommunications, and physics. Double hashing algorithm. Double hashing is a method for managing data storage conflicts in a hash table. It uses two different hashing functions to determine the position for storing each item, which helps to distribute data more evenly and increase the efficiency of data retrieval. Imagine you have a row of mailboxes for letters, but sometimes two letters have the same address. To solve this, you use a backup plan. If the first mailbox is full, you use a second set of rules to find another mailbox that's empty. Use cases, storing data in hash tables in computer programs, organizing databases to reduce search times, preventing data overlap in memory structures. Double selection. Sort double selection. Sort is an efficient method to arrange items in order by selecting both the smallest and largest elements in each iteration and moving them to their correct positions. Imagine sorting a row of pencils by length. First, you find the shortest and the longest pencils and move them to the ends of the row. Next, you look for the second shortest and second longest pencils and place them next to the first ones. Keep doing this until all pencils are neatly arranged from shortest to longest. Use cases. This algorithm is useful in organizing data such as numbers, names, or any sortable items in a list, making it easier to find and manage them. Douglas-Puker algorithm. This algorithm simplifies a curved line by reducing the number of points that make up the line while keeping its overall shape similar. Imagine you have a wiggly worm and you want it to lie straight. You hold the ends of the worm and keep the parts that make big bends, but let go of the small wiggles. Use this algorithm when you have a map with a complex path and you want to make it simpler to read, or when you're trying to save computer memory by using fewer points to describe a shape. Dynamic programming. Dynamic programming is a strategy for solving problems by dividing them into smaller, overlapping subproblems, solving each once, and storing their solutions. Imagine you're stacking toy blocks to make the highest tower. You look at each block and figure out the tallest tower you can make with it. Then add the next block and see if it makes the tower taller. You keep track of the best combinations as you go, ensuring you only build the highest possible tower. Use cases, optimizing resource allocation, scheduling tasks, pathfinding in games or maps, solving puzzles like Sudoku. ECDH key exchange. ECDH, elliptic curve Diffie-Hellman, is a method for two parties to create a shared secret key, which they can use to encrypt messages by using the principles of elliptic curve cryptography. Imagine you and your friend have secret colors that no one else knows. You each mix your secret color with a public paint, resulting in a new color. Then you exchange these new colors. Finally, you mix the received color with your original secret color. The result is a new shared color that only you two know, even though the mixed colors were shared in public. Use cases. Encrypted messaging to make sure only the intended recipients can read the messages. Securely transmitting data over the internet, ensuring that only the communicating parties can access the information. Protecting sensitive transactions such as online banking to prevent unauthorized access. ECDSA, elliptic curve digital signature algorithm. ECDSA is a method for signing digital messages using the principles of elliptic curve cryptography, ensuring both the authenticity and integrity of the communication. Think of ECDSA like a tamper-proof sticker on a collectible card. When you put the sticker on, it shows you're the genuine owner. If someone tries to copy the sticker to fake ownership, it's extremely difficult because the sticker has unique features that are hard to replicate. ECDSA works similarly with digital messages, using unique mathematical stickers. Use cases: secure email transmission, cryptocurrency transactions, software code signing, Identity verification systems. Edit distance algorithm. The edit distance algorithm calculates the minimum number of single-character changes needed to transform one word into another. These changes can be insertions, deletions, or substitutions. To change cat to bat, we substitute C-U-R with B. The edit distance is 1. For dog to frog, we insert F at the start and R after F. The edit distance is 3. Use cases. Edit distance is used for spell checking, comparing genetic sequences, and various tasks in computer science where string comparison is necessary. Edmonds algorithm. Edmonds algorithm is a method for finding the largest possible set of pairs in a network, where each element is paired with just one other, and no pair shares an element. Think of kids at a dance looking for dance partners. Each kid can only have one dance partner, and nobody wants to be left out. Edmonds' algorithm is like an expert matchmaker who pairs up the kids so that the largest number of kids get to dance at the same time. Use cases. Organizing speed dating events to ensure everyone gets a partner. Matching students with mentors in a mentorship program. Assigning tasks to workers in a job-sharing arrangement. Edmonds-Karp algorithm. The Edmonds-Karp algorithm is a method to find the maximum flow through a network. It uses breadth-first search, BFS, to repeatedly search for the shortest path from the source to the sink, and adds flow along this path until no more improvements can be made. Imagine you're filling water balloons at your house and want to send as many as possible to your friend's house through a series of connected pipes. The Edmonds-Karp algorithm helps you to figure out the way to send the water so that the most balloons can be filled as quickly as possible, avoiding any bottlenecks in the pipes. Use cases. Calculating the maximum possible transportation through a network of roads or pipes. Optimizing network traffic. Managing resources in supply chain logistics. Determining the maximum matching in a bipartite graph. Elgamal encryption algorithm. Elgamal encryption is a method of keeping messages secure using mathematical operations with large numbers, a generator, and a prime number. It allows secure message exchange without others being able to read it. You want to send a secret message. You and your friend choose a generator number, say 7. Your secret key is 3. Calculate 7 circumflex 3 mod 11, getting 2. Share the numbers 7, 2, and 11 with your friend. Your friend picks a random key, say 5, and calculates 7 circumflex 5 mod 11, which is 2, and uses it to encrypt the message. To read the encrypted message, you use your secret key and the shared numbers to decrypt it, revealing the original message. Use cases. Secure email communication, confidential data transmission, encrypted messaging services, protecting sensitive information in storage. Elliptic curve cryptography, ECC. Elliptic curve. Cryptography is a method for securing information by using the complex math of elliptic curves. It's like a tricky lock that only you and your friend know how to open. Think of a secret code as a dot on a special curve on a graph. You know how to jump from one dot to another using a secret pattern. Others can see the first dot and the pattern, but they can't easily jump to the right dots. Only you and your friend can follow the secret path correctly to crack the code. Use cases. ECC is used for encrypting messages, securing internet transactions, and protecting sensitive data from hackers. It's like a super secure lock for your digital treasures. Elliptic curve discrete logarithm problem, ECDLP. ECDLP is a complex puzzle involving a curve and a starting point used to secure information. It's hard to reverse engineer the process to uncover the secret steps taken. Imagine you're at the top of a unique slide, the curve, with a friend. You both know where you're starting from, point A. You slide down secretly choosing a number of times, your secret number X, ending up at point B. Then your friend does the same with their secret number Y, reaching point C. Even if someone sees points A, B, and C, and knows you used the slide, they can't easily tell how many times you and your friend slid down it, which keeps your secret number safe. Use cases 1. Securing online communications. 2. Safeguarding digital signatures. 3. Protecting cryptocurrency transactions. Elliptic curve, Elgamal encryption. This encryption method uses the math of elliptic curves to send secret messages securely. By applying difficult mathematical problems associated with these curves, it ensures only the intended recipient can read the message. Alice and Bob want to communicate privately. They choose a curve and a point on it. They each pick a secret number and use it to find a special point on the curve, which is their public key. When Alice sends a message, she selects another secret number, finds a new point with it, and sends this point plus her message to Bob. Bob uses his secret number and Alice's public key to uncover the original message. Even if someone else sees their messages, they can't understand them without the secret numbers. Use cases. Secure messaging between two parties. Protecting sensitive information in digital communication. Ensuring privacy in various online transactions. Elliptic curve factorization. This is a method used to break down large numbers into smaller multiplying factors using the properties of elliptic curves. Imagine you have the number 12, and you want to find two numbers that multiply to make 12. You could say 2 and 6, right? Elliptic curve factorization is a fancier way to do this sort of thing. You start by drawing a smooth, curvy line called an elliptic curve on a graph. It looks a bit like an oval that's been squished. Then you pick a spot on the curve and draw a straight line through it. The line will hit the curve again at another spot. You use these spots to draw more lines and look for a pattern. As you keep drawing lines and finding where they meet the curve, you'll notice some points showing up over and over. But when you find a point that doesn't fit the pattern, that's when you've hit the jackpot, because this strange point helps us find the smaller numbers we're looking for. Even though it sounds tricky, it's a smart way to find out what smaller numbers you can multiply to get a big number, and it's super important for keeping secret messages safe. Use cases. Cryptography, keeping data secure by creating hard-to-solve puzzles. Math research, studying numbers and their properties. Computer science, designing secure systems for communication and information protection. Elliptic Curve Integrated Encryption Scheme, ECEs. ECEs is a secure method to encrypt and decrypt messages using the mathematical properties of elliptic curves. Alice wants to send Bob a secret note. They use a special curve and a point on that curve. Alice picks a secret number, uses it to scramble the message and sends it to Bob. Bob uses his secret to unscramble the message and reads the note. Use cases. ECIEs is used to keep data private in secure messaging, online transactions, and anywhere information needs to be hidden from outsiders. Euclidean algorithm. This algorithm finds the largest number that two given numbers can be divided by without leaving any remainder. Imagine we have the numbers 36 and 24. We keep subtracting the smaller number from the larger number until we can't subtract anymore without going into negative numbers. In this case, we subtract 24 from 36 and get 12. Now, we subtract 12 from 24 and get 12 again. Since we can't subtract 12 from 12 without getting 0, our answer is 12. The Euclidean algorithm is useful in math for simplifying fractions and finding proportions, and in computer science for managing data encryption. Euclid's algorithm. This is a quick way to find the largest number that divides two numbers without leaving anything behind. Imagine you have a large pizza and you want to cut it so everybody gets equal slices. Euclid's algorithm is like a pizza cutting guide. You start by cutting as many equal slices as you can. If you have leftover pizza, you then cut the leftovers into as many equal slices as possible. You keep slicing the leftovers until they can't be cut anymore. Euclid's algorithm tells you the biggest slice size for the original pizza and the leftovers that make sure everyone gets a fair share. So, if your pizza was cut into 30 slices and you have 12 people at your party, Euclid's algorithm would help you figure out that you can cut the pizza into slices of 6 with no leftovers. This way, everyone gets an equal share of pizza. Use cases. Splitting items evenly in groups. Simplifying fractions. Finding common time intervals for schedules. Cryptography and computer science applications. Euler's method. Euler's method is a simple way to estimate the solution of an equation that describes how things change. It's like stepping forward bit by bit and guessing where you'll end up. Imagine you're on a straight path and you take steps forward while blindfolded. Each time you step, a friend tells you if you're still on the path. You take small steps and adjust your direction based on what your friend says. Eventually, you'll get to the end of the path. Use cases. Euler's method is used to predict things like weather changes, population growth, or how fast a car is moving. It's helpful when you can't solve a problem in one big step and need to take it little by little. Expectation maximization algorithm. The expectation maximization (EM) algorithm is a statistical technique used to find the most likely parameters of a model involving hidden variables. It alternates between guessing these parameters, expectation, and then improving the guesses, maximization, in a repetitive process until the results are consistent. Imagine you have a jar of mixed-colored marbles, but you can't see inside. You want to guess how many of each color there are. You start by picking a few marbles randomly, recording their colors, and putting them back. Using this information, you make an initial guess of the proportions of each color. Then, you draw more marbles, refining your estimate each time, until you feel confident about the proportions of the colors in the jar. Use cases. The EM algorithm is used in various applications, such as image processing, machine learning, and data analysis, where the data might be incomplete or have hidden parts that need to be estimated. It helps in making educated guesses and progressively refining them to come up with the most accurate model or understanding of the data. Expectation maximization (EM) algorithm. The EM algorithm is a method for finding the hidden patterns or quantities in complex datasets where some variables are unknown. Imagine we have a jar full of mixed-color jelly beans, but we can't see inside to count them. To figure out how many jelly beans of each color are in the jar, we first guess the numbers, expectation step. Then, we take out a few jelly beans, note their colors, and use this to improve our guess, maximization step. Repeating these steps helps us get closer to knowing the actual numbers of each color in the jar. Use cases. The EM algorithm is used in various fields such as finding patterns in genetic data, refining artificial intelligence learning, and improving speech recognition systems. Expectation maximization (EM) clustering algorithm. This is a technique that finds groups within data when you don't know the groups up front. Imagine you have a pile of multicolored candies. You want them sorted by color, but there are too many to sort just by looking. With the EM algorithm, you first guess how many colors there might be, say 3. You then pick 3 random candies as the starting points. Next, sort all candies based on which starting candy they are closest to in color. After sorting, find the new average color of each group, creating new starting points. Repeat the sorting with these new points. Continue this until the groups don't change much. In the end, you've got your candies sorted into color groups, even though you didn't know how many groups you had at the start. Use cases. Organizing different types of items or data points into groups. Finding patterns in scientific data, like stars in the sky or genes in biology. Helping businesses segment their customers into different categories. Expectation maximization (EM) for Gaussian mixture models. The EM algorithm for Gaussian mixture models is a statistical technique used to find the hidden parameters of a set of data that is believed to be generated by a mix of several Gaussian distributions. Imagine we have a jar of multicolored candies, and we want to sort them by color, but the colors are mixed, and we can't see how many of each color we have. The EM algorithm guesses how many colors there are and sorts the candies by guessing where each one goes, then improves its guesses by looking at how the candies are sorted and making better guesses until the candies are sorted into clear groups of colors. Use cases. The EM algorithm is used in various fields, including machine learning for clustering data, biology for genetic population studies, and image processing for identifying objects in images. Expectimax algorithm. This algorithm helps in making decisions where chance is involved by predicting the most beneficial outcome on average. Imagine you're at a forked road where each way might have treats or tricks. Expectimax is like a crystal ball that tells you which way is likely to have more treats. It checks all possible ways, adds up the good and bad things that could happen each way, and finds out which way is the best bet on average. Expectimax is used in games and situations where outcomes are uncertain, guiding players to make smarter choices for better chances of winning. Exponential search. Exponential search is a technique for finding an item in a sorted list. It begins by checking indices that are powers of 2 to quickly narrow down the search range. Imagine you're looking for your favorite book on a shelf organized by size. Instead of checking every book, you skip ahead in bigger jumps. First book, second, fourth, eighth, and so on. When you overshoot, you go back to the last best spot and check book by book till you find it. Use cases. Exponential search is useful for searching in infinite lists or when the size of the list is not known in advance. It's efficient for large datasets where the element's position is closer to the start. Extended Euclidean algorithm. The extended Euclidean algorithm calculates the greatest common divisor, GCD, of two numbers, and finds two other numbers that, when multiplied with the original numbers, result in the GCD. Imagine you have 10 candies, and you want to give an equal amount to each of your 3 friends. The extended Euclidean algorithm helps you figure out the largest number of candies each friend can get without any leftovers, and if there are any candies remaining. Use cases. The extended Euclidean algorithm is used in math to simplify fractions, find multiples that add up to the GCD, and solve problems in number theory. It's also useful in computer science for cryptography and coding theory, where it helps in creating secure communication and data storage. Factorial algorithm. This algorithm finds the product of all positive integers up to a given number, which is useful for counting arrangements. To find the factorial of 3 times 2 times 1 equals 6. So there are 6 ways to arrange 3 items. Use cases. Factorial calculation helps in arranging objects and solving problems in math and statistics. Fast Fourier transform, FFT. The FFT is a method to quickly determine the frequencies that make up a signal, like a musical note in a song. Think of a song as a smoothie with different fruits blended together. FFT is like a filter that separates the smoothie back into individual fruits so you can see what's inside. Use cases. FFT is used in music to identify notes, in engineering to analyze vibrations, and in many digital applications like image processing and signal compression. Fenwick tree. A Fenwick tree, or binary index tree, is a data structure that allows for quick updates and queries of cumulative sums in a list. Imagine you have a row of pots, each needing a certain amount of water. You list the water amounts for each pot. Using a Fenwick tree, you can swiftly update the water amount for any pot and calculate the total water needed for any group of pots without adding each one individually. Use cases. Fenwick trees are used in various applications like computational geometry for range queries, in gaming for score management, and in financial software for cumulative statistics. Fermat primality test, a method for checking if a number is probably prime by using arithmetic. Let's say n is 5 and we choose a to be 2. We calculate 2 to the power of 4, since 5, 1 equals 4, getting 16. Divide 16 by 5, the remainder is 1. This suggests 5 might be prime. Use cases. The Fermat test is used in cryptography and by mathematicians to identify prime numbers quickly, even though it's not foolproof. Fermat's factorization method, a way to find a composite number's factors by turning it into the difference between two square numbers. To factor 21, start with the square root closest to 21, which is about 5. Next, look for a number that, when squared, is just a bit more than 21. That number is 6 because 6 circumflex 2 is 36. Now, subtract 21 from 36 to get 15. Keep trying with bigger numbers until you find a square number difference. With 21, we quickly see that 5 circumflex 2, which is 25, and 4 circumflex 2, which is 16, are 9 apart. 25 minus 16 equals 9, which is a perfect square, 3 squared. So, 21 factors into 5 plus 4, and 5, 4, which means the factors are 9 and 3 or 7 and 3 when simplified. Use cases. Fermat's factorization method is used to break down numbers into smaller parts called factors, especially helpful when working with large numbers or trying to find prime factors for math problems. Fibonacci search algorithm. The Fibonacci search algorithm efficiently locates an item in a sorted collection by dividing the search interval using Fibonacci numbers. Imagine you need to find a specific book on a shelf with 21 books. To save time, you pick Fibonacci numbers close to 21, like 13 and 8, and compare the book in the 13th spot. If your book isn't there, you eliminate part of the shelf based on whether your book comes before or after the 13th book. Then repeat the process in the smaller section. Use cases. This algorithm is used in searching databases, finding specific information in large sorted lists, and computer file systems where quick retrieval is essential. Fibonacci sequence. The Fibonacci sequence is a sequence of numbers where each one is the sum of the two before it, starting with 0 and 1. Starting with 0 and 1, you get 0, 1, 1, 0 plus 1, 2, 1 plus 1, 3, 1 plus 2, 5, 2 plus 3, and so on. Use cases. This sequence is used in mathematics, computer science, and to describe patterns found in nature. Firefly algorithm. The Firefly algorithm is a method used by computers to find the best solution to a problem by imitating how fireflies flock to the brightest one. Imagine fireflies at night, where each one is attracted to the brightest light. They move towards it but also wander a bit to possibly find a brighter light. For example, if fireflies were searching for the best route to food, they'd follow the brightest firefly, which represents the best path. Use cases. Finding the most efficient routes, optimizing network designs, searching for the best engineering designs. First in, first out, FIFO algorithm. The FIFO algorithm is a method used to manage data where the first item added is the first one removed, like taking turns in a queue. Consider a line of kids waiting to slide on a playground slide. The first child in line goes down the slide first, followed by the second, and so on. The order of sliding is based on who lined up first. Use cases. Managing tasks in a printer queue. Processing orders in a ticketing system. Organizing processes in computer memory management. Fisher-Yates. Shuffle, a method to randomly reorder elements in a list, ensuring each element has an equal chance of appearing in any position. Think of having 10 balloons, numbered 1 to 10 in a row. To shuffle them, take the first balloon and exchange it with another chosen randomly from the 10. Then, take the second balloon and swap it with one chosen randomly from the remaining 9. Keep doing this until all the balloons have been swapped. Use cases. Mixing up playing cards before a card game. Randomizing the order of questions in a quiz. Shuffling songs in a music playlist. Fisher-Yates shuffle. The Fisher-Yates shuffle is a method for randomly mixing items in a list, such as cards in a deck. Imagine you have 10 numbered cards from 1 to 10. To shuffle them using Fisher-Yates, you'd start with the last card, number 10. Randomly pick one of the 10 cards and swap it with card 10. Then move to card 9. Randomly pick one of the first 9 cards and swap it with card 9. Continue this process all the way to the first card. Use cases. This algorithm is great for any situation where you need a fair and unpredictable shuffle, like in card games, drawing raffle tickets, or creating a random playlist of songs. Flash sort algorithm. Flash sort is a sorting technique that groups elements into categories, sorts each category, and then combines them. It's like sorting items by color or size. Imagine you have pencils of different lengths and want them ordered shortest to longest. Flash sort would group pencils by size ranges, sort pencils within each range, and then line them all up in order. Use cases. Flash sort helps when you have lots of items with only a few types, like sorting clothes by size or organizing books by genre. It's fast when there aren't many different categories. Flood fill algorithm. A method to fill a connected area with a new color without crossing boundaries, used in digital art and image editing. Imagine a coloring book where you want to fill an area with one color and not cross the edges. The flood fill algorithm is like using a smart paintbrush that only colors inside the lines. Here's how it's done. Choose a point within the area to color. Change the color of that point. Next, change the color of neighboring points that match the original color. Continue this process with the new points until the entire area is recolored. It's as if a wave of color flows from your starting point, filling the area neatly. For example, you could color all the leaves on a tree without getting any color on the trunk, or outside the tree's outline. It makes coloring easy and mess-free. Flower pollination algorithm. The flower pollination algorithm is an optimization method modeled after how bees and butterflies transfer pollen among flowers to help them produce seeds. Imagine a garden as a puzzle where each flower needs to be matched with pollen to create seeds. The algorithm guides bees and butterflies to efficiently spread pollen across the entire garden, ensuring every flower can grow new ones. Use cases. This algorithm can be used in various fields such as engineering, computer science, and biology to solve complex problems by finding the best solutions in a similar way to how insects pollinate flowers. Floyd's cycle detection algorithm. Floyd's cycle detection algorithm is a method for identifying the existence and start of a cycle in a sequence of linked elements, typically in a linked list. It uses two pointers, which traverse the list at different speeds, to detect a cycle and determine its starting point. Imagine a racetrack with different points numbered in sequence. Two runners start at the beginning of the track. Runner A moves 1 point per turn, and runner B moves 2 points per turn. If runner B catches up to runner A, we know there's a loop in the track. To find the loop's start, a new runner, runner C, starts from the beginning and moves at the same pace as runner A. When runner C meets runner A, that point is the beginning of the loop. For example, let's say the track looks like this: 1, 2, 3, 4. 2 loops back to 2. Runner A and runner B both start at 1. At some point they meet at number 2, indicating a loop. A new runner, runner C, then starts at 1 and moves until they meet runner A at point 2, revealing the loop's start. Use cases, detecting infinite loops in computer programs, finding cycles in a network of computers or pathways, diagnosing repetitive patterns in data structures such as linked lists. Floyd-Warshall algorithm. The Floyd-Warshall algorithm calculates the shortest paths between all pairs of nodes in a weighted graph, which may have positive or negative edge weights, but no negative cycles. Imagine a board game with spaces representing locations and cards indicating the distance or cost to travel between them. To find the shortest path, you'd compare all the possible ways to travel from one space to another, using the cards to keep track of the shortest distance found so far. Use cases, GPS navigation systems to determine the quickest route. Network routing protocols to find the optimal path for data packets. Urban planning to improve traffic flow by analyzing all possible road combinations. Ford-Fulkerson algorithm. The Ford-Fulkerson algorithm is a method to find the maximum amount of stuff that can move from one point to another through a network of pathways, considering any limitations on the pathways. Imagine you're pouring water into a system of pipes, and you want to get the most water from the start to the end. You keep trying different pipes to see which ones let you pour more water through until no more water can fit. Use cases, managing network traffic to maximize data transfer, allocating water through irrigation systems, assigning tasks or jobs in an efficient way. Forward-backward algorithm. This algorithm calculates the likelihood of being in a certain state within a system that changes over time based on the observations you've made. Imagine you're looking at a friend's collection of colored beads that form a pattern you can't see. Every day your friend shows you one bead, but not the order they're in. The forward-backward algorithm is like guessing the pattern of beads by using the colors you've seen. You start by making a guess about the first bead's color, then update your guess each day after seeing a new bead. If the next bead doesn't fit your guess, you rethink your previous guesses. By doing this repeatedly, you become better at predicting the hidden pattern. This method is used in various situations where you need to make educated guesses based on limited information, like decoding a scrambled message or forecasting the weather based on patterns. Fringe sort is a sorting algorithm that organizes items by repeatedly selecting the smallest or largest element from an unsorted list and moving it to a sorted list. Imagine you have a bunch of marbles of different colors mixed together. Using fringe sort is like sorting these marbles into groups of the same color. You take one marble at a time and place it in a pile with other marbles of the same color until all marbles are grouped. Use cases. Fringe sort is useful for efficiently organizing data where a priority can be assigned, such as arranging tasks by importance or files by size. Fully homomorphic encryption, FHE, allows computations on encrypted data, giving an encrypted result that, once decrypted, is the same as if the operations had been done on the original data. Imagine we have a magic box that can add secret numbers inside it without us seeing them. We put 2 secret numbers in the box, and the box shows us a new secret number. When we open the box, we see the sum of our original numbers. FG acts like the magic box, working with hidden numbers to add, subtract, multiply, or divide, and keeping the numbers secret the whole time. Use cases. Cloud computing. Users can securely process their encrypted data in the cloud without exposing it. Privacy-preserving analytics. Companies can analyze encrypted data without accessing sensitive information. Secure voting systems. Votes can be counted without revealing individual voters' choices. Fuzzy logic algorithm. Fuzzy logic is a method that deals with imprecision by allowing variables to have degrees of truth, which are values between 0 and 1. It is used to make decisions based on uncertain or vague information. Imagine deciding how much ice cream to eat based on the weather. If it's very hot, you rate the weather as a 10, and your craving for ice cream might also be a 10. The fuzzy logic algorithm combines these numbers and suggests you eat a lot of ice cream. However, if it's cold, both ratings might be low, let's say 2, so the algorithm suggests you eat a little ice cream. Use cases. Fuzzy logic is used in various applications like controlling machines, handling uncertain data in decision-making systems, and creating smart systems in cars, such as anti-lock braking and automatic transmission. Gabow's algorithm. Gabow's algorithm is a method for identifying strongly connected components in directed graphs efficiently. Imagine you're sorting socks into pairs and want to group them by color quickly. Instead of checking each sock individually, Gabow's algorithm helps you sort them into smaller groups, then find which groups have matching colors step by step until all pairs are found. Use cases. Gabow's algorithm is used in computer science for organizing data, understanding relationships between different pieces of information, and solving problems where items need to be grouped based on their connections. Gale-Shapley algorithm. The Gale-Shapley algorithm, also known as the stable marriage problem, pairs 2 groups based on preferences, ensuring no one would benefit from swapping partners. Imagine 5 boys and 5 girls at a dance, each with a list of preferred dance partners. The boys ask the girls to dance in order of their preference. If a girl is asked by more than one boy, she chooses the one she prefers most. This process continues until all are paired with their top choice available, resulting in stable pairs where no one wants to switch. Use cases. Matching medical students with residency programs, assigning students to high schools, organizing participants in mentoring or peer review programs. Gauss-Jordan elimination algorithm. This algorithm solves systems of linear equations by turning the associated matrix into a form where each variable can be solved directly. Imagine you're trying to figure out the exact amount of apples, bananas, and carrots you have. You know that 2 apples plus 3 bananas equal 5, and 4 apples minus 2 carrots equal 2. The Gauss-Jordan elimination algorithm is like a recipe that tells you how to use these clues to find out exactly how many of each fruit and vegetable you have. First, you write down your clues as mathematical equations. Then, you transform these equations step by step, always performing the same action to both sides of the equation to keep things fair, until each fruit or vegetable stands alone with a number. This is like sorting and moving your fruits and vegetables until you see exactly how many you have of each. You repeat this process for every type of item until you know all the amounts. It's like having every fruit and vegetable in its own basket, with a label telling you the quantity. Gauss-Jordan. Elimination is used for decoding secret messages, predicting the weather, or even budgeting pocket money, where the amounts of different items need to be figured out. Use cases. Decoding encrypted information, weather prediction modeling, financial budgeting and accounting, engineering and physics simulations. Genetic algorithm. A genetic algorithm is a computerized method that mimics the survival of the fittest concept to find the best solution to a problem by evolving over iterations. Think of a genetic algorithm as a contest to create the best Lego car. You start with random cars, then take the parts from the best ones to build new cars. You repeat this, always choosing the best, until you get the coolest, fastest Lego car. Use cases. Genetic algorithms are useful for planning efficient routes, designing computer games, creating smart software, and solving complex science and engineering puzzles. Genetic programming. This algorithm evolves computer programs to solve problems by mimicking natural selection. Imagine we want a computer to draw a flower, but don't know how to program it. We generate a group of random programs like different artists trying to paint a flower. Each one has its style and technique. We then see which paintings look most like a flower. The algorithm picks the best artists and mixes their styles to create new painters, hoping for even better flower drawings. This process repeats until a computer artist creates a beautiful flower picture. Genetic programming helps computers learn to solve problems, improve tasks, or even create art without being explicitly programmed for the task. Gibbs sampling. Gibbs sampling is a technique used to estimate the makeup of a complex whole by repeatedly sampling individual parts and using those samples to make an informed guess about the entire set. Think of a bowl filled with mixed fruit where you can't see all the pieces. You pick one fruit, note its type, then put it back and stir. You pick again, record and return it. Repeat this many times. Afterward, you'll have a good idea of the different types of fruit and their amounts in the bowl. Use cases. Gibbs. Sampling is often used in statistics to understand large data sets, in image processing to reconstruct images, and in machine learning to build complex models when you can't see all the data at once. Gnome. Sort a simple sorting method where elements are repeatedly moved into their correct position, akin to a gnome organizing pots. Imagine lining up toy soldiers by height. Starting from the second one, you compare it with the one before. If it's shorter, swap them. Step back to compare again unless you're at the start. If it's taller or you're at the start, step forward. Repeat until the end, and every soldier stands taller than the last. Use cases. Ideal for educational purposes and small data sets due to its simplicity and ease of understanding. Golden section search. This algorithm efficiently locates the minimum point of a function by repeatedly reducing the search interval. Imagine you're playing a game where you need to find a hidden object in your backyard. To be smart about it, you first split the yard into two parts and look right in the middle. If you don't find the object there, you take the bigger side and split it into two again, looking at the middle of that part next. You keep doing this, splitting the larger section each time until you find your hidden object. Use cases. 1. Optimizing engineering designs to find the best dimensions or parameters. 2. Identifying the minimum cost or maximum efficiency in economics and finance. 3. Adjusting machine learning model parameters to improve performance. Goldwasser-Mikali encryption, a secure encryption method that scrambles messages using the quadratic residuosity problem, making them unreadable without the proper key. Suppose your message is hello, and you change each letter into a number like H equals sign 8, E equals sign 5, L equals sign 12, O equals sign 15. Then you scramble these numbers with a special math trick, so maybe 8 becomes 16, 5 becomes 25, and so on. Now the message looks like a bunch of mixed-up numbers that only someone with the right key can understand. Use cases. Goldwasser-Mikali encryption is used to keep data private in emails, online transactions, and secure communications, ensuring that only individuals with the correct key can access the original message. Gradient boosting. Gradient boosting is a technique that combines many simple models to solve complex problems. It improves predictions by learning from errors in a step-by-step fashion. It's like playing a video game where each level teaches you a new skill. If you keep losing at a certain spot, the game gives you extra help there until you get past it. With each level, you get better at the game. Use cases. Gradient boosting is used to predict things like house prices, identify if an email is spam, or decide if a bank should give someone a loan. Gradient descent. Gradient Descent is a method used to find the lowest point in a function by repeatedly stepping in the direction that goes downhill the fastest. Imagine you're at the top of a hill and you want to reach the bottom. You look around, see which way goes downhill, and take a step in that direction. With each step, you look around again and choose the steepest way down until you reach the bottom. Gradient descent helps in situations where you want to make something as small as possible, like the error in predicting house prices or the amount of medicine needed to treat a patient. It's like finding the easiest path down a hill to reach the lowest point without stumbling. Grey Wolf Optimizer. This algorithm mimics how grey wolves hunt and establishes a hierarchy to find the best solution to a problem. Imagine you're looking for the perfect place to have a picnic in a big park. You want a spot that's shady, has a beautiful view, and isn't full of bugs. The Grey Wolf Optimizer acts like an organized group of your friends, each one scouting for a great picnic spot. They compare notes to figure out which spot is the best, much like how wolves decide on the best strategy to catch their prey. Use cases, engineering design problems, finding efficient routes for delivery trucks, optimizing network structures. Grover's algorithm. Grover's algorithm is a fast way for computers to search an unsorted list. Imagine you're in a large room filled with balloons. Inside one balloon is a golden ticket, but you don't know which one. Normally, you'd have to pop each balloon until you find the ticket. But with Grover's algorithm, it's as if you clap your hands once and the sound pops only the balloon with the ticket. Grover's algorithm is used in computing for quickly finding items in a big list, speeding up searches in databases, and enhancing the efficiency of solving certain types of problems. It's like a shortcut for finding needles in digital haystacks. Harmony Search Algorithm. This algorithm mimics the process of finding a harmonious musical piece to solve optimization problems. Imagine building the ultimate spaceship from a mix of colorful Lego pieces. You test different combinations and swap pieces to make your spaceship cooler each time. Harmony Search does the same with numbers instead of Legos, tweaking them until it finds the perfect solution. Use cases, engineering design optimization, resource allocation, scheduling problems. Hash table. A hash table is a collection that pairs unique keys with values and uses a process called hashing to identify where to store and find each pair. Imagine a bookshelf as a hash table. Think of every book having a unique code. A magic system, hash function, tells us exactly which shelf and spot to place our book on or to look at when searching for it. This is helpful in many computer programs for organizing data so that finding and storing information is very fast. It's used in databases to find records and in web browsers to cache web pages. Hash-based signature algorithm. A hash-based signature algorithm is a method that uses a special function to create a unique and secure digital stamp on messages. It's safe against future powerful quantum computers. Think of sending a locked treasure chest to your friend. You lock it with a unique key that only you can make, the hash-based signature. Your friend has the special map, the public key, to check if the lock was really made by you and hasn't been changed. Use cases. 1. Secure communications, ensuring messages can't be faked or altered. 2. Protecting software, verifying that software updates come from the correct source. 3. Quantum-resistant security, creating signatures that even future computers can't break. Heapsort is an efficient sorting algorithm that arranges items in order by transforming the list into a binary heap structure. It repeatedly removes the largest element from the heap and places it at the end of the list until all elements are sorted. Imagine you have a tree where the biggest number is always on top. You take that number out and put it at the end of a line. Then you fix the tree so the next biggest number is on top and move it to the line too. Keep doing this until your tree is empty and the line has all the numbers from biggest to smallest. Use cases, organizing data for priority queues and scheduling tasks based on importance. Sorting large data sets where efficient in-place sorting is necessary. Implementing sorting in systems with limited memory resources. Heun's method. Heun's method is a strategy for estimating unknown values in a process that changes steadily over time. using initial measurements and updates to improve accuracy. Think of trying to predict the path of a rolling ball that speeds up or slows down based on the slope of the ground. You look at where it starts, guess where it'll be a little later, then correct your guess by observing where it actually goes, and keep doing this to track its path. Use cases. Hume's method is used in weather forecasting to predict temperatures, in engineering for simulating car crashes, and in economics for modeling market changes. Hierarchical clustering. Hierarchical clustering creates a tree-like structure of data, grouping similar items based on their features. Simply imagine sorting Lego blocks. First, you separate them by color, making big piles of each color. Then, in each color pile, you sort smaller piles by size. You keep sorting smaller and smaller until every Lego has been grouped with similar ones. Now, you have a tree of Lego blocks organized by color and size. Use cases. This method is used to organize things like books in a library, by genre, then author, products in a store, by category, then brand, or even organizing family photos, by event, then people. Hill climbing algorithm. This algorithm is like a shortcut for finding the top or bottom of a hill in math problems. It takes steps towards the steepest slope until it can't go any higher or lower. Imagine you're on a hill and you want to reach the very top. You look around to find the steepest path up and walk that way. After each step, you check again to find the next steepest part to climb. You repeat this until you're at the highest point you can find. Hill climbing is used in situations where you need to find the best answer quickly, like when a computer is playing a game or making a schedule. It's fast, but might not always give the absolute best answer. HMAC, hash-based message authentication code. HMAC is a technique for verifying the integrity and authenticity of a message using a secret key and a hash function. Imagine you have a secret handshake with your friend that no one else knows. When your friend uses the handshake, you know the message is really from them. HMAC is like that secret handshake for digital messages. HMAC is used in various security applications like data integrity checks, digital signatures, and verifying payment information. Hopcroft-Karp algorithm. The Hopcroft-Karp algorithm is a method used to match elements in two groups as efficiently as possible. Imagine you have two rows of cubes, one blue and one red, and you want to connect as many pairs as you can, but each blue cube can only be connected to one red cube. This algorithm helps you find the maximum number of cube pairs possible without any confusion. First, you take a blue cube and look for a red one that is free and can be paired with it. If all red cubes are already taken, you try to find a way to rearrange the existing pairs so that you can pair your blue cube with a new red one. You repeat this process until you can't pair any more cubes. The Hopcroft-Karp algorithm is like a game where you have to find the best way to connect as many blue and red cubes as possible, like creating the biggest chain without any cube left alone. This algorithm is really helpful when you have two types of things that need to be matched together, like players in a sports league who need opponents, or when assigning jobs to workers to ensure everyone has a task. Use cases. Partnering students for projects in a class, matching job seekers to job openings, organizing sports tournaments with competing teams. Transform the Who. Transform is a method for detecting shapes in images by finding points that align in a certain way. Picture playing connect the dots, but you're not sure where the lines should go. You use a grid to mark where lines could meet, and where many lines cross a lot, that's likely the center of the shape you want. Use cases. Detecting lines in road images for autonomous driving, finding circles in medical images to spot tumors, identifying shapes in satellite images for mapping. Huffman coding. Huffman. Coding is a technique that reduces the size of data by assigning shorter codes to more frequent characters. Imagine you have a box of different stickers, and you use smiley stickers more often than star stickers. To save space in a message, you could use a small dot to represent a smiley and a bigger dot for a star. Huffman coding makes a special sticker chart based on which sticker you use the most, giving the most common stickers the smallest dots. This way, your message uses fewer stickers. For example, if you use 5 smiley stickers and 3 star stickers, the chart might say Use a small dot for smileys and a bigger dot for stars. So instead of using a bunch of stickers, you just write down dots in a special order, and it means the same thing but takes up less space. Huffman coding makes sending and storing messages easier by using less room. Use cases, compressing files to save storage space on computers, reducing the amount of data needed to transmit messages over the internet, ensuring efficient data transmission in telecommunications. Huffman decoding. Huffman decoding is a method for converting a binary sequence back into the original text using a specific tree-like structure known as a Huffman tree, which was created during the encoding process. This algorithm ensures that more frequent characters have shorter codes, and less frequent characters have longer codes, making the encoded message compact. Imagine you receive a string of bits like 101100. With the Huffman tree, you start at the root and move left for a 0 and right for a 1 until you reach a leaf node, which corresponds to a character. You follow this path for each sequence until you decode the entire message. Use cases. 1. Data compression for reducing file sizes. 2. Communication systems to optimize bandwidth usage. 3. Storage devices for efficient data storage. Hungarian algorithm. This algorithm helps assign tasks in a way that is most efficient based on ability. Imagine you have 3 friends, Amy, Bob, and Charlie, and 3 chores: washing dishes, cleaning the living room, and vacuuming the floors. You rate how well each friend can do each chore on a scale from 1 to 10. Amy gets a 9 for dishwashing, Bob a 3, and Charlie a 6. You make a chart with your friends' names and chores. After rating each friend on every chore, you apply the Hungarian algorithm, which calculates the best chore for each friend to maximize the overall score. In the end, you might assign Amy to wash dishes, Bob to clean the living room, and Charlie to vacuum, ensuring everyone does what they're best at for a happy and clean house. Use cases, task assignment in teams, resource allocation and scheduling to optimize productivity. Hybrid merge bead. Sort a faster sorting method that combines merge, sort, and bead sort techniques. Imagine sorting your toys by creating color groups like red, blue, and green, and then arranging each toy in these groups from biggest to smallest. After sorting the groups, you merge them into one big sorted collection. This algorithm is used for organizing large data sets by initially dividing them into smaller, manageable groups and then combining them in a sorted manner. Hybrid merge binary tree. Sort. This algorithm combines merge sort and binary tree sort to efficiently organize data. Imagine we have some colored marbles and we want to sort them. With hybrid merge binary tree sort, we first split the marbles into color groups like red, blue, and green. Then, using merge sort, we sort within these groups. After that, we use binary tree sort to arrange the groups in a final sorted order, like red, then blue, then green. In the end, all marbles are neatly ordered by color. Use cases: organizing libraries of books or music, sorting databases with mixed data types, ordering products in an online store catalog. Hybrid merge bubble. Sort. This is a combination of merge sort and bubble sort methods to organize items more efficiently. Imagine you have a set of numbered cards to sort from least to greatest. Divide the cards into 2 piles. Use bubble sort for each pile by comparing pairs of cards and swapping if needed until they're in order. Then merge the 2 piles together in order, which is the merge sort part. Sorting computer data, organizing library books, or arranging playlist songs are common uses. Hybrid merge bucket. Sort. Hybrid merge bucket. Sort is a sorting technique that combines merge sort and bucket sort to organize items quickly and efficiently. Imagine sorting a mix of red, blue, and green marbles. First, you separate them into buckets by color, one for red, one for blue, and one for green. Then, within each bucket, you arrange the marbles in a line using merge sort, which combines smaller sorted groups into larger ones. In the end, you merge all the sorted buckets back together to have a neatly sorted line of marbles, grouped by color. Use cases. This algorithm is useful in situations where data can be naturally divided into groups, such as organizing books by genre before arranging them alphabetically, or sorting emails into categories before ordering them by date. Hybrid merge cocktail. Hybrid merge cocktail sort is a sorting method that blends the processes of merge sort and cocktail sort to efficiently organize items. It first sorts small groups and then combines them, checking and reordering any misplaced items. Imagine lining up toy cars by color. First you sort small groups by shade, and then you line them up to form one big colorful row. If you spot a car that's out of place, you'll correct it, just like stirring a drink to mix in the bits that didn't blend the first time. Use cases. This algorithm is used in computer programs that need to sort large amounts of data quickly and accurately, such as databases, search engines, or organizing files on a computer. Hybrid merge comb. This sorting method combines merge sort and comb sort to quickly organize items. Imagine you have many mixed-up toys. Hybrid merge comb sort is like first grouping your toys by type and then lining up each type by size. After sorting each group, you mix the groups back together in order, keeping the sizes correct. For example, if you sort toy cars and dolls separately, then merge them. The cars don't mix into the dolls. They all stay in the right size order. Use cases. 1. Organizing computer files by size and type. 2. Sorting numbers or names in a list. 3. Arranging library books by genre and then by author. Hybrid merge counting. Sort. This algorithm sorts items efficiently by combining merge sort structure with counting sort simplicity. Imagine you have marbles of different colors all mixed up. The hybrid merge counting sort would count how many marbles you have of each color first, then group the same colored marbles together, and finally arrange these groups in order. Use cases. Organizing libraries with a large number of books by genre and then by author. Sorting huge databases by categories, then by specific values within those categories. Hybrid merge gnome sort. This sorting method combines merge sort and gnome sort to quickly organize items. Imagine sorting your colored blocks into piles where each pile has blocks of the same color. First, you make small piles and arrange them. Then, you check each block in the piles and shuffle any out-of-place block until all piles are sorted. For example, if you have red and blue blocks, you first sort the red pile and then the blue pile. Next, you ensure each block in the red pile is in the right spot, and do the same for the blue pile. Hybrid merge gnome sort is useful for organizing things efficiently, like sorting books, arranging files, or tidying up toys. Hybrid merge heap. Hybrid merge heap. Sort combines the methods of merge, sort, and heap sort to sort items efficiently. Imagine you have a mix of toy cars, dolls, and action figures. First, you make separate piles for each type. Then, within each pile, you line up the toys by size or color, cars from smallest to largest, dolls by height, and so on. After sorting each type, you combine all the toys back into the box, now organized. Use cases. This sorting algorithm is useful in computing when dealing with a large set of data that needs to be organized quickly and efficiently. Hybrid merge insertion. A sorting algorithm that combines the simplicity of insertion sort with the efficiency of merge sort to organize items quickly. Imagine we have a pile of numbered cards. We want to line them up so that the numbers go from smallest to largest. At first, we make small piles and sort each one by hand, like playing a mini-game of sorting cards. This is the insertion sort part. If a pile gets too big, it's harder to sort by hand, so we switch to a super-fast card sorter machine to merge and sort those big piles. This is the merge sort part. Hybrid merge insertion sort is like playing the mini-game for small piles and using the sorter machine for big piles, making the whole task of lining up the cards faster and easier. Use cases. Organizing data that's partially sorted. Handling large lists where simple sorts slow down. Combining efficiency and simplicity in sorting tasks. Hybrid merge odd-even sort. This sorting method combines merge sort and odd-even sort to organize items efficiently. Imagine sorting a deck of cards by splitting it into two smaller decks, sorting each one, and then checking pairs of cards, switching any that are out of order. Use cases. Sorting large datasets where traditional sorting methods may be less efficient. Hybrid merge pancake. Sorting algorithm. This is a smart way to put things in order using two steps. First, split the items into small groups and sort them. Next, merge the groups, making sure everything stays in order. Imagine you have a stack of different-sized pancakes. To sort them, you split them into smaller stacks, organize each by size, then carefully put the stacks together into one big sorted stack, from the smallest pancake on top to the largest at the bottom. Use cases. The hybrid merge pancake sorting algorithm is useful when you have a lot of items like books, toys, or even computer data that you need to arrange from smallest to biggest or in a certain order. Hybrid merge radix. Sort a sorting method that combines merge sort and radix sort to efficiently organize numbers. Imagine you have a messy stack of number cards. To sort them using hybrid merge radix sort, first, you make piles based on the first number. Like all cards that start with one go together. Then sort each pile by the next number. Keep doing this until every card is in a mini pile. Finally, merge these mini piles by picking the smallest card from each, making a new pile that's all sorted. Use cases, organizing large sets of numbered data, sorting information in databases, arranging numerical files in order. Hybrid merge selection. Sort. This algorithm combines merge sort and selection sort to sort items more efficiently. Imagine you need to organize your numbered cards in ascending order. First, you sort some small groups of cards using selection sort, which is like searching for the tiniest card to place first, then the next tiniest for second place, and so on. After sorting these small groups, you merge them together into one big sorted stack using merge sort, like combining smaller puzzles into one big picture. Use cases, sorting moderately sized datasets, improving performance when merge sort benefits from initial ordered sequences, when combining simple selection. Sort's ease with merge sort's efficiency is beneficial. Hybrid merge smooth sort. This is a smart sorting method that combines two ways of sorting, one that divides and conquers, and another that sorts smoothly, to organize things quickly. Imagine you have a big pile of numbered cards. The hybrid merge smooth sort is like a game where you make smaller, neat piles of cards, sort each pile, and then cleverly combine them back into one big sorted pile. First, you make little groups with your cards, like when you sort your toys into piles. You sort each little group so the numbers go from small to big. It's similar to organizing your toy cars by size or color. Next, you merge these sorted groups together. You look at the cards and decide which one has the smaller number to arrange them. It's like putting all your toy cars together in a line, from the smallest to the biggest. The cool part about this sorting game is that it's super efficient, like a helpful robot making the sorting faster and smoother. In short, hybrid merge smooth sort is a clever trick to organize a messy pile of cards into a neat and ordered stack, just like a smart robot that helps you tidy up your room and sort your toys perfectly. Hybrid merge stooge. Sort. This algorithm blends the efficiency of merge sort with the simplicity of stooge sort to expedite sorting. Imagine arranging your toys by size using two steps. First, like merge sort, you separate them into smaller groups, sort those, and then combine them back. Then, like stooge sort, you sort parts of the collection again to ensure everything's in order. Use cases. The hybrid merge stooge. Sort is ideal for large lists where traditional merge sort benefits from added simplicity, leading to potentially faster sorting times. Hybrid quick. Odd-even sorter hybrid. Quick odd-even sort is a sorting algorithm that combines the methods of quick sort and odd-even sort to organize numbers more efficiently. Imagine you have colored blocks, some are red and some are blue. You want to arrange them so all the red blocks are on one side and all the blue blocks are on the other. So you choose one block and put it in the center, then move all red blocks to one side and all blue blocks to the other. Next, you take each side and repeat the process. Pick a block, put it in the center, and group the same colors together. You do this over and over until all the blocks are neatly arranged. Use cases. This method is useful for sorting large lists where dividing items into smaller groups based on certain conditions, like odd or even, can speed up the sorting process. Hybrid quick bead. Sort. This algorithm combines quick sort and bead sort to efficiently arrange items. Imagine sorting beads into piles by color. First, you pick a color, the pivot, and divide the beads into two groups. those that match the pivot and those that don't. Repeat until sorted. Near the end, when fewer beads remain, you quickly place them in order instead of dividing them further. Use cases, sorting large data sets with elements that can be easily compared, like numbers, where the combined approach can improve sorting speed. Hybrid quick binary tree. Sort. This algorithm sorts numbers by first using quicksort to create smaller groups and then arranging them with binary tree logic for efficiency. Imagine sorting the numbers 5, 3, 1, 4, and 2. Pick 5 as the first pivot, placing numbers smaller to the left, 3, 1, 2, and larger to the right, which there are none. Repeat this with the left side using 3 as a pivot, and you get 1 and 2 to the left and nothing to the right. Keep doing this until all numbers are in order. Then add each group to a binary tree, starting with the smallest, and combine them to get a sorted list. 1, 2, 3, 4, 5. Use cases, organizing data that needs efficient sorting, handling large data sets where traditional quicksort might be slow, sorting information in databases and file systems for quick retrieval. Hybrid quick bubble sort. This is a sorting algorithm that combines the quicksort method's dividing strategy with the bubble sort method's swapping technique to organize numbers efficiently. Imagine you have a mix of playing cards that you need to line up from lowest to highest. Using the hybrid quick bubble sort, you choose a card to be the pivot and separate the others into 2 groups based on whether they're less or more than the pivot. Each group uses a new pivot to keep sorting smaller groups. Additionally, cards next to each other are swapped if they're out of order, speeding up the process like a teamwork of sorting methods. For example, let's say you have the cards 3, 6, 2, 5, 1, and 4. You pick 3 as the pivot. Lower than 3, 2, 1, higher than 3, 6, 5, 4. Each side gets sorted again with a new pivot. While doing this, any cards that are out of place next to each other get swapped immediately. Use cases, organizing libraries or databases where data is somewhat but not completely sorted. Handling large datasets where traditional sorting methods are too slow. Improving performance in real-time applications that need quick sorting of information. Hybrid quick bucket. Sort. This is a sorting algorithm that merges the speed of quicksort with the grouping technique of bucket sort for more efficiency. Simply put, if you had to organize a mix of different-sized marbles, first you'd separate them by size into groups, just as hybrid quick bucket sort groups numbers. Then, within each group, you'd sort the marbles from smallest to largest, similar to how the algorithm applies quick sort within each group. In the end, you'd combine your groups back into a single, organized set, just like the algorithm combines sorted groups into a fully sorted sequence. Use cases include sorting large data sets or dealing with data that is somewhat sorted but clustered in ranges, making it ideal for applications where speed is critical and data is diverse. Hybrid quick cocktail. Sort. A combined sorting method that enhances performance by using both quicksort and cocktail sort strategies. Imagine you're playing a sorting game with colored marbles of different sizes. Your goal is to line them up from the smallest to the biggest. First, you compare a pair of marbles and place the larger one to the right and the smaller one to the left. You keep doing this until all marbles are sorted. But if the marbles are nearly in order, you switch to a different tactic. You sort from the ends toward the center by swapping marbles where needed. This hybrid approach helps you sort your marbles faster, whether they're mixed up or almost sorted. Use cases, sorting databases, organizing files on a computer, arranging products in a warehouse. Hybrid quick comb. Sort. A hybrid quick comb. Sort is a blend of quicksort and comb sort methods to sort items more effectively. Imagine sorting numbered cards. With quicksort, we choose a pivot card and arrange cards into 2 piles, one with cards smaller and the other with cards larger than the pivot. If cards are nearly sorted, quicksort slows down. That's when we switch to comb sort, similar to bubble sort but faster, to quickly sort nearly organized cards. By combining these methods, hybrid quick comb sort efficiently sorts mixed-up cards with quicksort speed and tidies up nearly sorted cards with comb sort's precision. Use cases. This algorithm is useful in computer programs for sorting large lists or databases where efficiency is crucial. Hybrid quick counting. Sort. This algorithm combines the speed of quicksort with the systematic approach of counting sort to organize items efficiently. Imagine you're sorting colored toy blocks, red, blue, green, and yellow. First, you quickly make a pile for each color, then count how many blocks there are in each pile. Finally, reorder the piles into a neat row based on the number of blocks in each. Use cases. Hybrid quick counting. Sort is ideal for sorting items with a mix of different and repeated values, like when you have a big collection of colored blocks and want to line them up quickly and neatly. Hybrid quick gnome. Sort. The hybrid quick gnome sort is an efficient sorting method that combines the fast sorting process of quicksort with the detailed checking process of gnome sort. Imagine you have a row of numbered blocks and want to line them up from lowest to highest number. You start by quickly comparing blocks and swapping them to get them in a rough order like quicksort. Then, you carefully move through the row, making sure each block is in the right place, similar to gnome sort. This sorting algorithm is particularly useful for organizing data quickly and thoroughly, making it practical for tasks like arranging files on a computer or sorting a list of names. Hybrid quick heap. Sort. This is a sorting method that blends quicksort and heap sort to sort items more efficiently. Imagine sorting your colorful toy blocks by shade. First, you choose a block, or pivot, and separate lighter and darker ones. That's quicksort. Next, you arrange these groups into a pyramid. Lightest on top, that's heap sort. The hybrid quick heap sort does both, separates colors with quicksort, then arranges them with heap sort. Use cases, sorting large lists or databases, organizing files on a computer, arranging data for analysis in scientific research. Hybrid quick insertion. Sort. This algorithm combines quicksort and insertion sort to sort items more efficiently. Imagine sorting your toy blocks by color, from lightest to darkest. First, you pick a random block and place it as a reference in the center. You then separate the lighter blocks to the left and the darker ones to the right. This is like quicksort, but if there are just a few blocks left, you arrange them one by one like insertion sort. This way, sorting is quicker and easier. Use cases. Sorting medium-sized data sets. Situations where quicksort is too slow due to small partitions. Improving efficiency when the data is partially sorted. Hybrid quick pancake. Sorting algorithm. The hybrid quick pancake sorting algorithm is an efficient method for ordering items that melds the quicksort's dividing strategy with the straightforward swapping technique of pancake sorting. Imagine you have different-sized pancakes and want to stack them from smallest on top to largest at the bottom. First, you'd split the stack into smaller stacks, sorting each one. If a stack is small, you'd just flip pancakes within it to sort them. This way you sort the entire pile faster. Use cases. Organizing mixed data efficiently, sorting in environments with limited memory, arranging items when initial order varies widely. Hybrid quick radix. Sort. This is a smart way to sort things that combines two different sorting methods to speed things up. Imagine you're sorting marbles by color using a machine. First, you drop in a marble, and the machine puts it in the right color pile. Keep doing this until each color has its own pile. But if one pile gets big, sorting each marble takes too long. So, for big piles, you switch to a faster sorter that handles many marbles at once. This gets the job done quicker. Use cases. Organizing large sets of data where items have distinct categories, followed by detailed sorting within those categories. Sorting complex data where simple sorting methods are too slow. Hybrid quick selection. Sort. Hybrid quick selection. Sort is a sorting method that combines the quicksort and selection sort techniques to efficiently organize numbers. It starts with quicksort and switches to selection sort for smaller groups. Imagine you're organizing colored pencils by length. You start by choosing one pencil as a reference and separating longer and shorter pencils on either side of it. You continue to divide these groups using new reference pencils until they're small enough. When only a few pencils are left, you simply compare and arrange them directly without dividing further. Use cases. Organizing a large set of data into a specific order quickly. Sorting files by size on a computer. Arranging students by height for a school photo. Hybrid quickshell. Sort. The hybrid quickshell. Sort is an efficient sorting method that blends the steps of quicksort and shell sort to organize items quickly. Imagine sorting a deck of mixed-up playing cards. First, you find a middle card, the pivot, and put all cards lower than the pivot into one pile and all higher cards into another pile. Repeat this with each pile, always picking new pivot cards until all cards are in order. Sometimes, instead of using a pivot, you sort the cards by jumping over some, like every third card, and then reducing the jump size until you're going through each card one by one. This is the shell sort part. Use cases. This algorithm is useful in computer programs that need to sort large sets of data efficiently, like when organizing a database or making information easy to search through. Hybrid quick smooth. Sort. This sorting algorithm merges quick sort and smooth sort techniques to efficiently organize items. Imagine sorting playing cards by first separating them into piles based on a chosen card's value, and then fine-tuning each pile by comparing pairs of cards until they're all in the correct sequence. Use cases. Organizing data in computer programs, sorting numbers or names in a list, managing files based on size or type. Hybrid quick stooge. Sort. Hybrid quick stooge. Sort is a sorting algorithm that combines the methods of quick sort and stooge sort to organize items efficiently. Imagine sorting your toy cars by using a hybrid quick stooge sorter. It's like a team of two robots. One sorts quickly by picking a special car, pivot, and separating smaller and bigger cars around it, while the other deals with the larger groups by dividing and conquering until all cars are neatly arranged from smallest to biggest. Use cases. Organizing large databases with varied data sizes. Sorting complex lists where traditional methods are inefficient. Handling datasets that need quick initial sorting, followed by detailed organization. Image segmentation. Image segmentation is a process that divides a digital image into distinct sections to identify and isolate different elements within the photo. Think of a picture with a cat, a ball, and grass. Image segmentation is like using a special pair of glasses that makes the cat glow yellow, the ball glow blue, and the grass glow purple. Now, we can see each part of the picture separately. Use cases. Image segmentation is used in medical imaging to identify organs or tissues, in self-driving cars to recognize objects like pedestrians and traffic signs, and in photography apps to apply effects to specific areas of a picture. Independent component analysis, ICA. This is a method that finds separate sources from a set of mixed signals. Imagine you have a bowl of mixed candies. ICA is like a helper that sorts out each candy type for you. You reach into the bowl and sort candies by feeling their shape and tasting them. ICA is like having a sense that distinguishes each candy type. Use cases. ICA is useful for unmixing audio tracks, separating different sources in images, or analyzing complex data to discover underlying factors. Index calculus algorithm. The index calculus algorithm is a mathematical technique used to find the index or the exponent in exponentiation problems involving large numbers. It simplifies the problem by breaking it down into smaller, more manageable pieces using the properties of numbers. Imagine we have a number like 9, and we want to find out what number, when multiplied by itself, gives us 9. The index here is 3, because 3 multiplied by itself, 3x3 equals 9. The index calculus algorithm helps us find such an index for much larger numbers by using a list of smaller numbers that we can easily square. Use cases. This algorithm is especially useful in the field of cryptography, where it helps secure information by solving complex mathematical problems that involve finding discrete logarithms, which are akin to the indices of large numbers in the context of modular arithmetic. In-place merge. Sort. This is a sorting method that organizes items by dividing, sorting, and merging them in the same area without needing additional space. Imagine sorting a row of numbered blocks. First, you split the row into smaller groups, sort each group, and then combine them back together in the right order using the same space on the table. Use cases. Organizing data with limited memory, sorting large files on a computer. arranging items when extra storage isn't available. Insertion sort insertion. Sort goes through a list and places each element in its correct order, one at a time, like sorting a hand of playing cards. Imagine you have some numbered cards in a random order and you want to line them up from the smallest number to the biggest. You start with the first card and then take the next one. If the new card's number is lower, you place it before the first card. If it's higher, you place it after. You keep picking up the next card and slotting it into its correct place until all the cards are neatly ordered from smallest to largest. Use cases, sorting small lists of numbers or data, organizing a hand of playing cards, ordering items where the cost of comparison is high and the list is almost sorted, simple database algorithms where data is mostly sorted. Integer factorization. This algorithm finds the prime factors of a number, which are the prime numbers that multiply together to make that number. Imagine you have the number 15 and want to know what prime numbers multiply to make it. You check by dividing 15 by the smallest prime number, 2, but it doesn't work. Then you try 3, and it does work because 15 divided 3 equals 5. Now you have two prime factors, 3 and 5. There aren't any more, so the prime factors of 15 are just 3 and 5. Use cases. Integer factorization is used in math for understanding numbers better, in cryptography to keep information secure, and in other areas like computer science and engineering. Interpolation search interpolation. Search is a method for finding a specific value in a sorted list by guessing where it might be and adjusting the search area accordingly. Imagine you're looking for a name in an alphabetically sorted list. Instead of checking every name, you make a guess where the name could be based on its first letter. For example, if the name starts with M, you might start looking around the middle of the list since M is halfway through the alphabet. Then, depending on whether the name would come before or after the name you see, you guess again, but closer to the correct spot until you find it. Use cases. Finding a specific number in a sorted list of numbers, searching for a word in a dictionary or an alphabetical list, looking up data in tables where the values are in ascending or descending order. Interval trees. An interval tree is a smart way to keep track of different ranges and find out which ones overlap with a range or point you're interested in. Imagine you have a bunch of sticks of different lengths on the floor. You want to quickly find all the sticks that are as long as the one you're holding, or maybe even longer. An interval tree helps you sort out those sticks without looking at every single one. Our example is a bunch of sticks from 1 inch to 10 inches long. We sort them into groups, and the interval tree tells us the longest stick in each group. When we want to know the longest stick between 3 and 7 inches, the interval tree gives us the answer fast. Interval trees are really useful when you need to manage a lot of ranges or segments, like setting up appointments, organizing computer memory, or even planning events so that they don't overlap. It's like having a quick reference chart that tells you what you need to know without digging through piles of data. Intrasort algorithm. Intrasort is a hybrid sorting algorithm that combines the speed of quicksort with the reliability of heap sort. It starts by using quicksort to sort items quickly and switches to heap sort when necessary to avoid slow performance. Imagine you're sorting your toy cars. First, you sort them into groups based on color using quicksort, which is fast. If you find that sorting a group is taking too long, you switch to a different method, heap sort, to finish arranging them by size. This combination ensures you can sort all your cars quickly, even if there are many. Use cases. Sorting large datasets in computer programs where performance matters. Organizing complex information where both speed and consistency are important. Inverse discrete Fourier. Transform, IDFT. IDFT is a process that takes complex frequency data and turns it back into sequential time-based information. Imagine you have a puzzle that's made up of different sounds instead of pieces. IDFT is like the instructions that help you put all the sound pieces back in the right order to hear the original song. Use cases. Reconstructing audio signals from their frequencies. Analyzing and editing digital music. Restoring time-based data in engineering and science applications. Iterative quicksort. Iterative quicksort is a method to arrange items in order by repeatedly dividing a collection into smaller groups and sorting those groups. Imagine you have a row of toys with numbers and you want them to line up from the smallest number to the biggest. You pick one toy called the pivot and place all toys with smaller numbers on one side and those with bigger numbers on the other side. Keep picking new pivots in the smaller groups and doing the same until all toys are lined up neatly. Use cases. This algorithm is useful in organizing lists like sorting names in alphabetical order or arranging files by size on a computer. Johnson's algorithm. Johnson's algorithm is a way to find the quickest route through a network with various paths and can deal with some paths being costly or even having a negative cost. Imagine you're in a park with many different paths and you want to get from the swings to the slide as quickly as possible. Johnson's algorithm is like using a map that tells you how fast you can get from one place to another, even if some paths are uphill or downhill. Use cases. This method is used in GPS systems to give you the fastest driving route, in social networks to find the closest connections between people, and in economics to optimize supply chains. Josephus problem. The Josephus problem is a puzzle that deals with eliminating every kth person in a group arranged in a circle until only one person remains. Imagine 10 kids sitting in a circle playing a game where every seventh kid is out, starting with the first kid and going around. The goal is to be the last kid left sitting. Use cases. This algorithm can be used in computer science for memory allocation, networking and systems design, as well as in various mathematical problems and games. JPEG compression algorithm. This algorithm makes digital images smaller by simplifying colors and details that are hard to notice, so files are easier to share. Imagine you have a big, colorful picture. Using JPEG compression is like using a magic tool to shrink the picture by blending similar colors and softening tiny details. It's like telling a story with fewer words, but still keeping the story's heart. For example, a photo with a big blue sky might have all the light blue parts mixed into one shade of blue to save space. JPEG compression is used to make pictures smaller so they can be sent by email, uploaded faster online, and take up less space on your computer or phone. Jump search algorithm. Jump search is an efficient algorithm to find a target value in a sorted array. It jumps ahead in fixed intervals, then checks the elements in that interval for the target value. Think of the algorithm like a frog hopping along lily pads that are lined up in a row. Each lily pad has a number. The frog wants to find a specific number, so it jumps several pads at a time. When it lands on a pad, if the number isn't right, it hops forward again. Once it goes too far, finds a number larger than the one it wants, it hops back one pad at a time until it finds the right number or confirms the number isn't there. Use cases. Searching for a person in a list of sorted names. Finding a book by its ID in an alphabetical library catalogue, locating a specific data point in a chronological dataset. K-nearest neighbors, KNN. KNN is an algorithm that identifies the category of a new item by looking at the closest existing items in the data. Imagine you have a mix of apples, oranges and bananas. You find a new fruit and want to know what it is. You compare it to the closest similar fruits you know. If it looks like the 3 nearest apples, you'd say it's probably an apple. Use cases. KNN is used for recommending movies similar to ones you like, deciding if an email is spam or not, and identifying diseases by comparing patient symptoms. Kadane's algorithm. Kadane's algorithm quickly finds the largest sum of consecutive numbers in a list. Imagine a list. 1, -3, 5, 2, -1, 4, -7, 6. Kadane's algorithm checks each number, keeping a running total that resets if the total goes negative. The highest total reached during this process is remembered. So, starting with 1, then adding -3 drops the total to -2, which is less than 0, so we reset and start at 5 instead. We keep adding the next numbers until we get a total of 10 with the subarray, 5, 2, -1, 4. This is the maximum sum we get, so this subarray is our answer. Use cases. Kadane's algorithm is used in computer science to analyze stock market trends, in computer vision to detect bright areas in an image, and in many applications that require finding a sequence with the highest value in a set of data. Kalman filter. The Kalman filter is a mathematical method used to improve predictions over time by estimating unknown variables in the presence of uncertainty. Imagine you're playing a game where you have to guess where a hidden toy car will move next. At first, you make a random guess. Then, as you receive clues, like the sound of the car's movement, you refine your guess. The Kalman filter is like using those clues to make your next guess much smarter. The filter takes your initial guess, combines it with new clues, and calculates an updated guess. It's like sharpening your guess each time you get more information. Use cases. It's used in navigation systems to predict the position of vehicles, in economics for estimating economic indicators, and in robotics for robots to understand their surroundings. Karatsuba algorithm. The Karatsuba algorithm multiplies large numbers quickly by splitting them into smaller parts, performing a few key multiplications, and then combining the results. Simply example. To multiply 1234 by 5678, you split them into 1234 and 5678, multiply the parts, 672 from 12 asterisk 56, 2652 from 34 asterisk 78, add and multiply the sums, 46 times 134 equals 6164, and finally, combine these products to get 76016. Use cases. The Karatsuba algorithm is used in computer systems for efficient multiplication of large integers, essential in cryptography, numerical computing, and large-scale mathematical operations. Karga's algorithm. A method to find the smallest number of edges that can be removed to separate a network into two parts. Imagine you have a network of friends where lines connect friends who know each other. You want to split this network into two groups so that the fewest friendships are broken. Karga's algorithm is like playing a game where you randomly erase connections between friends one by one. Each time you erase a connection, those friends join into a bigger group. You keep doing this until you have two big groups of friends with just a few or no lines left connecting them. The remaining lines are the fewest friendships you can break to split the network into two. For example, if you start with a circle of 6 friends all connected, you might first erase the connection between 2 friends. Then, they join into a group, and you continue erasing connections randomly until there are only 2 groups left with 1 or no lines between them. Use cases. Dividing a network into parts to understand its structure. Identifying weaknesses or bottlenecks in networks. Planning efficient road systems or data networks. KD tree algorithm. A KD tree organizes points in space to make it easier and quicker to search for specific items within multi-dimensional data. Imagine you have a large garden with various trees. A KD tree is like a treasure map for your garden, helping you find the exact tree you're looking for. You start by planting the first tree in a specific spot, then find the center of the garden for the next tree, repeating the process until all trees are planted. When searching, you use the map to guide you in the right direction until you find your desired tree. KD trees are used for tasks like searching for points within a space efficiently, such as finding the nearest coffee shop on a map or sorting through a list of stars in the night sky. K-means algorithm. This is a method used to group similar items into clusters. The goal is to find cluster centers that are spread out, which helps the process work faster. Imagine you have a collection of different colored candies and you want to sort them into groups by color. First, decide on the number of groups, say 3. You randomly choose 3 candies to be the leaders of each group. Then compare each candy to these leaders and group them with the one they resemble the most in color. Next, calculate the average color of the candies in each group and adjust the leaders to these new colors. Keep comparing and regrouping candies based on the closest leader. Continue this until the leaders no longer change their color. Finally, you'll end up with the candies sorted into 3 color groups. The K-means algorithm does a similar thing with data points, grouping them by common traits. Use cases. Market segmentation to find groups of customers with similar behaviors. Organizing computing resources in data centers based on usage patterns. Image compression by reducing the number of colors needed to represent an image. Document clustering for organizing similar texts or articles together. K means clustering. Brief description. K-means clustering is a simple technique to group similar data points together by their features. Think of having 15 fruits on a table, and you want to group them by type. You decide on 3 groups for apples, bananas, and oranges. First, you guess where to start the groups and place a few fruits in each. Then you check each fruit and put it into the group it fits best. If a fruit is misplaced, you switch it to the correct group. You repeat this until all fruits are with their like kinds, and no more switching is needed. Use cases. K-means. Clustering is used in market segmentation, organizing computing clusters, social network analysis, and image segmentation. KMP, Knuth-Morris-Pratt algorithm. The KMP algorithm is a method for finding a specific sequence of characters, called a pattern, within a longer string of characters quickly and efficiently. Imagine you're looking through a long line of people to find someone wearing a red hat. Instead of asking each person if they have a red hat, you remember some of the people's features as you move along. If you don't see the red hat after a few people, you don't start again from the first person. You just move slightly back and continue checking from a new point, using what you remembered to skip some people. Use cases. 1. Searching for a word in a book or document. 2. Finding specific sequences of DNA and genomic data. 3. Detecting plagiarism by comparing texts for matching strings. KMP algorithm. The KMP, Knuth-Morris-Pratt algorithm, is a method for finding the starting position of a pattern within a longer text efficiently by skipping non-matching characters. Imagine you have a sentence, "I like ice cream and ice lollies," and you're looking for the word ice. The KMP algorithm will compare ice to the sentence, and when it finds that ice doesn't match Ike after I like, it doesn't start over but skips to compare the next ice in the sentence, quickly finding the matches. Use cases. The KMP algorithm is used for searching specific sequences in DNA strings, detecting plagiarism by matching text segments, and in text editors for find and replace functions. Knapsack problem algorithm. The knapsack problem algorithm helps you choose the most valuable combination of items for your backpack without making it too heavy. Imagine you're packing toys in a small box but can only carry 5 pounds. You decide which toys to pack, knowing a teddy bear is worth 8 fun points but weighs 3 pounds, and a puzzle is worth 3 fun points but only weighs 1 pound. You pick the best mix of toys to get the most fun without the box being too heavy. Use cases. Deciding what equipment to carry on a space mission where weight is critical. Selecting the most profitable products to ship within a weight limit. Packing the most valuable items for a hiking trip without overburdening the backpack. Nearest neighbors, or KNN. KNN is an algorithm that guesses the category of a new item by looking at the categories of the closest items around it. Imagine you're at school and there's a new kid who doesn't know where to sit for lunch. To help them choose, you see which lunch tables have seats open and what kinds of foods the kids at those tables like. If the new kid likes pizza and the table with the most pizza lovers has an open spot, you'd suggest they sit there. Use cases. KNN can help recommend movies or songs by seeing what other people with similar tastes like. It can also identify what kind of plant or animal something is by comparing it to known examples. Doctors can use it to predict diseases by looking at similar symptoms in other patients. Knuth-Morris-Pratt, KMP algorithm. The KMP algorithm is a fast method for finding a word within a larger text. It uses a pattern to avoid repetitive searching. Imagine searching for cat in a sentence. KMP first prepares by understanding the word cat to know where to resume if a mismatch happens. If we match C and A, but the next letter isn't T, KMP uses its preparation to skip ahead instead of starting over. Use cases. KMP is useful for searching words in large texts, like finding a name in a book or a keyword in a website's content. It helps computers do these tasks quickly. Knuth-Morris-Pratt algorithm. The Knuth-Morris-Pratt KMP algorithm is a method for finding a specific sequence of characters within a larger text quickly, without rechecking characters that have already been compared. Imagine you have a string of beads with different colors, and you're looking for a particular pattern of colors. Instead of starting from the first bead every time you don't find a match, You just slide the pattern over by the number of beads that you've already confirmed match and continue checking from there. Use cases. The KMP algorithm is used in text editing software for the find feature, in DNA sequence analysis, and in network applications for pattern matching within data packets. Cohenor network. A Cohenor network is a type of neural network that groups similar data points together without needing someone to tell it how. It's like having a map to sort stickers by color. You start with a random spot on the map for your first sticker. Every new sticker you get is compared to the map, and you place it where the color fits best. As you place more stickers, the map updates, making sure similar colors stick together. In the end, you'll have a sorted map of stickers. Use cases. Cohenor networks are great for organizing things without clear categories, like grouping animals by traits, sorting fruits by taste, or arranging books by topic, all without a pre-made system. Kozaraju's algorithm. Kozaraju's algorithm identifies strongly connected components in a directed graph, revealing which nodes are closely linked together. Imagine you have a schoolyard with different clusters of kids. Each cluster consists of kids that all know each other well. To find these clusters, you use Kozaraju's algorithm, a step-by-step method. Here's a basic example. 1. Draw circles for each kid and lines for friendships. 2. Look for the tightest circles where everyone is friends with everyone else. 3. Apply Kozaraju's algorithm to split the schoolyard into these tight-knit circles. 4. Now you can spot who's in which cluster and how they're all friends. Kozaraju's algorithm is like solving a puzzle to find who hangs out with whom, forming exclusive groups in the schoolyard based on friendships. Use cases. Social network analysis to identify close-knit communities. Web page ranking by understanding interconnected groups of pages. Analyzing road networks to find strongly connected regions. Krill herd algorithm. The krill herd algorithm is a problem-solving method that mimics how krill swarm in the sea to reach a common goal. Imagine you and your friends can't decide on a place to eat. You each have a favorite spot. Using the krill herd algorithm, everyone shares their choices, and you all consider them to find a restaurant that makes the whole group happy, like krill moving together in the ocean. Use cases. The krill herd algorithm is used in various areas such as engineering, computer science, and economics for finding the best solution to complex problems by considering multiple factors and options. Kruskal's algorithm. Kruskal's algorithm is a method used to connect different points, like islands, with the least amount of work, or shortest bridges, ensuring they can all reach each other without making any loops. Imagine you have 5 islands. You need to build bridges of lengths 2, 3, 4, 5, and 6 to connect them. Kruskal's algorithm tells you to start with the shortest bridge of length 2, then take the bridge of length 3, and so on, until all islands are connected using the fewest bridges. Use cases. Kruskal's algorithm is useful for planning how to lay out electricity cables, water pipes, or roads to connect different places efficiently, ensuring everything is reachable with the least amount of material and cost. Lagrange interpolation algorithm. Lagrange interpolation is a method to find a polynomial that connects a set of known points on a graph. If you have points 1, 3, 2, 5, and 3, 7, the algorithm finds a math formula that fits exactly through these points. Use cases. This algorithm helps in predicting unknown values, like figuring out the height of a bouncing ball at a moment not directly measured, based on the pattern of other known heights at different times. Lamport signature algorithm. The Lamport signature algorithm is a method that uses one-way functions to verify the authenticity of digital messages. Imagine Alice wants to send Bob a secret note in class. She writes her note and then uses a special sticker that only she can create. She puts the sticker on her note and gives it to Bob. Bob has a special light that checks if the sticker is really the one Alice makes. If the light says the sticker is genuine, Bob knows the note is really from Alice. Use cases 1. Secure email communication. To make sure an email is really from the person it says it's from. 2. Document signing. To confirm that a digital document hasn't been changed by someone else after it was signed. 3. Software distribution. To ensure that the software you download is from the legitimate creator and not a fake version with viruses. Lattice-based cryptography. Lattice-based cryptography is a secure communication method that uses complex grid-based mathematical problems that are hard to solve without a special key. Imagine you have a secret clubhouse with a unique lock that uses a pattern of dots instead of a key. To send a secret note to a friend, you lock it using a pattern that only you and your friend know. Your friend then uses their knowledge of the pattern to unlock the note and read your secret message. Use cases. Lattice-based cryptography is used for secure data transmission, protecting information from hackers, and is considered strong enough to resist future threats from quantum computers. Least recently used, LRU, cache algorithm. The LRU cache algorithm helps computers remember recent information while discarding old, unused information to save space. Imagine your backpack can only hold 3 books. If you want to add a new book but your backpack is full, you remove the book you haven't read in the longest time. This is like the LRU rule. Use cases, managing memory in computers to keep them running fast, organizing data in smartphones so they can run more apps smoothly. Lemma random number generator, a mathematical method to create a sequence of numbers that appear random. 1. Start with a number, say 5. 2. Multiply by 7. 3. Divide by 11 and keep the remainder. 4. Use the remainder to repeat the process. Use cases, creating sequences for simulations, games, and cryptographic applications. Lempel-Ziv-Welch, LZW algorithm. The LZW algorithm is a method for reducing the size of files like GIF and TIFF images by compressing the data without losing any information. Imagine you have the repeated sequence A, B, B, C, C, C. LZW would assign a number to each unique letter. A equals sign 1, B equals sign 2, C equals sign 3. The sequence is then represented by the numbers 1, 1, 1, 1, 1, 2, 2, 2, 2, 3, 3, 3, which takes up less space. Use cases. The LZW algorithm is commonly used in compressing graphics files, such as GIFs and TIFFs, and can also be used for text and other data types to save storage space or speed up file transfer. Lempel-Ziv-Welch, LZW, compression algorithm. LZW is a method for reducing file size that creates a dictionary from the input data and substitutes repeated strings with shorter codes. Imagine your favorite book is filled with the word chocolate, repeated 100 times. LZW would give chocolate a code like #5. Now your book is shorter because every chocolate is replaced with #5, but you can still enjoy the full story when #5 is translated back to chocolate. Use cases, compressing text files to save space, reducing image file sizes in formats like GIF and TIFF, making web pages load faster by compressing the data. Lempel-Ziv-Welch, LZW. Decoding LZW. Decoding reconstructs original data from compressed code by using a dictionary to match patterns. Imagine a dictionary like this: A, 1, B, 2, AB, 3. If we get a code 123, we decode it as A, then B, and then AB, which gives us ABAB. Use cases. LZW decoding is used in file compression like GIF and TIFF images to reduce file size for storage or transmission. Lenstra elliptic curve factorization. This algorithm helps find the prime factors of a large number by using the properties of elliptic curves. Imagine you have the number 143 and want to find 2 smaller prime numbers that multiply to make 143. The Lenstra elliptic curve factorization algorithm can help. You start by drawing a special squiggly line called an elliptic curve. Then, you choose a point on that line and use math to find new points. If you keep doing this and suddenly the math leads to an error, you've just found the 2 prime numbers that multiply to make your big number. Use cases, breaking down large numbers into prime factors, cryptography and encrypting data, improving computer security systems. Levenberg-Marquardt algorithm. The Levenberg-Marquardt algorithm is a method used to find the best fit in a set of data by minimizing the difference between the observed values and the values predicted by a model. Imagine trying to draw a line through a set of points that are scattered around on a piece of paper. This algorithm would help you adjust the line bit by bit until it fits through those points as close as possible. Use cases. This algorithm is used in various fields such as robotics for fine-tuning control systems, in finance for adjusting complex pricing models, and in data science for refining predictions based on nonlinear relationships. Levenshtein distance. The Levenshtein distance algorithm measures how many changes you need to make to turn one word into another. If you start with cat and want to change it to cot, you only need to change the A to an O. The Levenshtein distance is 1. Use cases. This algorithm is used in spell checkers, DNA sequence analysis, and language translation tools to find similar words or patterns. LFU cache algorithm. The LFU cache algorithm removes the least often used items when the cache is full. Imagine your toy box can only hold a certain number of toys. To make room for new toys without removing your favorites, you use a system that tracks which toys you play with the least. This is the LFU cache method. If there's a toy car you use every day and a puzzle you only use once a week, the LFU cache algorithm will remove the puzzle when you need space for a new toy, keeping your most loved toys in the box. Use cases. Web browsers. Storing frequently visited pages, databases caching queries and results, operating systems, managing memory resources. Library sort library. Sort is a sorting algorithm inspired by the method of sorting books on a shelf. It organizes items by creating a library, a sorted section of the array, and then efficiently placing each unsorted item into its correct position. Imagine 5 books with the sizes 5, 3, 8, 2, 7. Start with the first book, 5, and compare it to the second, 3. Since 5 is larger, swap them to get 3, 5, 8, 2, 7. Next, compare books 5 and 8. They're in the correct order. Then compare 8 with 2 and swap them, resulting in 3, 5, 2, 8, 7. Finally, compare 8 with 7 and swap to end with 3, 5, 2, 7, 8. Continue this process until all books are sorted from smallest to largest. Use cases library. Sort is useful for organizing data when you have a partially sorted structure, and you want to insert new elements with minimal disruption to the existing order. Its efficiency shines in scenarios where the cost of moving elements is high, but comparing them is cheap. Linear congruential generator. A method for creating a series of numbers that seem random by applying a simple math formula to each number to get the next one. Imagine you have a wheel with 11 numbers on it, and you spin it to pick a starting number. Let's say it lands on 3. To get the next number, you multiply by 5, add 7, and then see where you land on the wheel. Starting with 3, you do 3 times 5 plus 7, which equals 22. On the wheel, 22 goes past the 11 twice, landing back at 0. So your new number is 0. You repeat the process using 0 to get the next number and keep going like this to get a chain of numbers. Use cases. Video games use it to create random events. Computer simulations use it to mimic randomness. Lotteries use it to draw random numbers. Linear probing. Linear probing is a method used in hash tables to solve the problem of 2 items wanting to go into the same spot. If that spot is full, the item goes into the next free spot. Think of a row of 10 lockers for your toys, numbered 0 to 9. You try to put each toy in the locker with its number. If locker 5 is full, you check locker 6, then 7, and so on, until you find an empty one. Use cases. Linear probing is used in computer programs to organize data efficiently when there's limited space, and items might have the same storage address. Linear regression. Linear regression is a method used to predict the value of a variable based on the value of another variable. The variable you want to predict is called the dependent variable, and the one you use to make the prediction is called the independent variable. Imagine you have a chart showing how much water different plants get and how tall they grow. If you draw the best-fitting straight line through the chart's points, you can estimate a plant's height by seeing where the line is for a certain amount of water. Use cases. Linear regression is used in many fields such as economics to predict prices, in meteorology to forecast weather, in health sciences to determine risk factors for diseases, and in engineering to test the strength of materials. Linear search. This is a simple method to find an item in a list by checking each one in order until you find what you're searching for. Imagine you have a line of 10 ducks and you want to find the one with a blue hat. You start at the first duck and look to see if it has a blue hat. If it doesn't, you move to the second duck, then the third, and so on, until you find the duck with the blue hat. Linear search is useful when you have a list of items like names on a class register, and you need to see if a particular person is on the list by reading each name one at a time. Long Short-Term Memory, LSTM, network. An LSTM network is a type of artificial intelligence that remembers important information for a long time and forgets less important details. Think of it like a backpack, where you keep only the most important toys. If you get a new toy that's really cool, it goes into the backpack. If the toy is just okay, it might not stay in the backpack for long. Use cases. LSTMs are used for predicting stock prices, translating languages, and even helping your phone's keyboard guess what word you want to type next. Longest common prefix algorithm. Brief description. The longest common prefix algorithm finds the longest beginning part that is the same in all words within a group. Imagine you have sun, sunny, and sunflower. The longest same starting part in all these words is sun. Use cases. This method is useful for sorting words, searching in dictionaries, or organizing files by their names. Longest common subsequence, LCS. The LCS algorithm finds the longest series of elements that appear in the same order within two sequences, even if they are not continuous. Given the words cat and bat, the LCS is at, because both contain A followed by T. Use cases. The LCS algorithm is used in text comparison, such as diff tools, DNA sequencing, and data version control. Longest common subsequence algorithm. This algorithm finds the longest series of characters that two sets of letters have in common without changing their order. Imagine you have the words elephant and rhythms. You want to find the longest string of letters they both have, keeping the order the same. You make a chart with elephant on one side and rhythms on the other. Whenever the same letter is in both words, you add 1 to the number in the corner. If not, you pick the biggest number next to it. After filling the chart, you find the longest set by starting from the end and going back to the beginning, picking the letters with the same numbers. You compare elephant to rhythms and find the longest set of letters they share is A. Use cases. This method is used in computer programs to compare DNA sequences, find similar documents, or see how closely related two languages are. Longest common substring algorithm. This algorithm identifies the longest sequence of characters shared by two or more strings. Consider apple and maple. We create a chart, placing apple on one axis and maple on the other. We mark where characters match. The longest continuous line of marks represents the longest common substring. Here, app is shared by both words. Use cases. It's used in DNA sequencing to find similar regions between genes, in text comparison tools to highlight shared content, or in file comparison utilities to detect common lines between documents. Longest increasing subsequence, LIS, algorithm. This algorithm finds the longest sequence of numbers that go up in order without skipping any. Imagine a line of ducks from smallest to biggest. You want to see how long you can make a line by only picking ducks that are bigger than the last one you picked. For example, with ducks numbered 2, 4, 1, 7, 5, 3, 8, 6, you'd choose 1, then 5, and then 8. So your longest line would be with ducks 1, 5, 8. This is used in places like computer software that needs to sort things in order or figure out patterns in data. Longest increasing subsequence algorithm. This algorithm finds the longest sequence of numbers that go up in order without any breaks. Imagine you have numbers like toys in a line, 5, 2, 8, 6, 3, 6, 9, 7. You want the longest line where each toy's number is bigger than the last one. You start with the smallest number, 2, then find a bigger one like 3, then 6, and finally 9. The longest line you can make is 2, 3, 6, 9. Use cases. This method is useful when you want to organize things in a certain order to see the longest possible pattern of things going up or getting bigger. Longest palindromic subsequence. The longest palindromic subsequence, LPS, is the longest sequence of characters in a string that reads the same backward as forward. In the word race car, the LPS is race car itself because it reads the same from both directions. Use cases. The LPS algorithm is useful in fields such as text processing, bioinformatics, and data compression, where recognizing patterns and sequences within strings is essential. Longest palindromic substring. This algorithm searches for the longest part of a word that reads the same forwards and backwards. In race car, it finds race car as the longest palindrome. Use cases. The algorithm is useful for analyzing texts and in various computer science problems. LRU cache. The LRU, least recently used. Cache is a method of managing memory where the items that haven't been used for the longest time are replaced first. Imagine your desk can only fit 5 books. When you get a new book, you remove the one you've read the longest time ago to make space. Use cases, LRU. Caches are used in computer programs to manage limited memory resources, ensuring the system runs efficiently by keeping frequently used data ready to access. LZ compression algorithm. The LZ compression algorithm reduces file size by replacing repeated data with references. If a sentence says cat loves catnip because cat feels happy, LZ might abbreviate it to cat loves catnip because C feels happy, using C to represent cat. Use cases. LZ is used in file compression, speeding up file transfers and saving storage space. LZ77 compression algorithm. This algorithm shrinks data by finding and replacing repeating patterns with shorter references. Consider the sentence, I like ice cream and I like summer days. Using LZ77, we might compress it to I like ice cream and 24 summer days. The 24 tells us that like appears 2 words back and is 4 letters long. Use cases. LZ77 is used in file compression, like in zip files, to reduce file size for storage or faster transmission over the internet. LZ78 algorithm. The LZ78 algorithm is a method for compressing data without losing any information. It works by turning repeated data into shorter reference codes. Let's say you want to send the word happy using the LZ78 algorithm. First, you would add the letter H to your list. Next, A is added because it's new. When you reach P, you see it's new too and add it. But the second P isn't new. You just refer back to the first P in your list. Similarly, Y is new and added. Now, instead of writing happy, you have a list like this. HAP, reference to PY. Use cases, 1. Reducing file sizes for storage. 2. Speeding up data transfer over the internet. 3. Compressing images or documents for email attachments. LZW algorithm. The LZW algorithm is a way to make files smaller by replacing repeating sequences of characters with shorter codes. Imagine the word banana abababa. The LZW algorithm would give each letter a number like B equals sign 1, A equals sign 2, and N equals sign 3. It would then find repeated sequences like BA and give that a number 2, like BA equals sign 4. Now replace BA with 4. Na 4 a 4B4 AA. The word is now shorter. Use cases. The LZW algorithm is used to shrink files, making them quicker to send over the internet and take up less space on computers and other devices. LZW compression algorithm. This algorithm compresses data without losing any information by using codes to replace repeated patterns. Imagine if ice cream is a favorite phrase in a story. Instead of writing ice cream each time, we use 1 inch to represent it. So I love ice cream is great becomes I love 1 is great. LZW is useful when you want to make files smaller for saving space on a computer or sending them over the internet faster. It's like packing a suitcase by folding clothes neatly instead of throwing them in. Maneker's algorithm. This algorithm quickly finds the longest sequence that reads the same backward as forward in a given string. For level, Maneker's algorithm transforms it to L hashy hash V hashy hash L, then checks each character, finding that level is the longest palindrome. Use cases. Maneker's algorithm is helpful in computer science and text processing applications where palindromic sequences need to be identified fast. Markov chain, Monte Carlo, MCMC. MCMC is a method used to understand and predict patterns in a large set of data. It works by making random choices and seeing how often these choices are repeated, which helps to identify what's most common or likely in the data. Imagine your jar of mixed jelly beans. You want to know which flavor is the most common, but there are too many to count one by one. Instead, you pull out one jelly bean, note its flavor, and put it back. Then you take another jelly bean. If it's the same flavor as the first, you think, yes. If it's different, you just continue. You do this many times, and the flavor you said yes to the most often is probably the most common one. Use cases. Predicting the weather by looking at past patterns. Understanding which products people will buy most often. Deciding which medicine works best for a disease based on patient data. Matrix chain multiplication. This algorithm finds the most efficient way to multiply a series of matrices together. Imagine you have to multiply several chains of blocks, each with a different number of links. The algorithm decides the best sequence to multiply these chains to require the least effort. For example, if there are chains with 2, 3, and 4 links, the algorithm might suggest multiplying the 2-link chain with the 4-link chain first, and then multiply the result with the 3-link chain. Use cases. It's used in computer graphics, scientific computing, and optimizing certain calculations in computer programs. Maximum flow algorithm. The maximum flow algorithm determines the greatest quantity of something that can move from a starting point to an endpoint through a network with limited capacities. Think of a system of water hoses with each hose only able to carry a certain amount of water. The algorithm helps to figure out how to organize the flow to get as much water as possible from the start to the end without overflowing any hose. Use cases. The algorithm is used for optimizing networks like traffic management, streamlining production processes, and distributing resources in supply chains. Macaleese cryptosystem. The Macaleese cryptosystem is a secure method for sending messages using hard-to-solve math problems. Imagine you have a locker with a special lock that uses a secret code. You put your message inside the locker. To lock it, you scramble the message with a secret code that only you and your friend know, which is made from 2 big secret numbers. This scrambled message is like a locked locker. When you send the message to your friend, it's still locked. Your friend uses the same secret numbers to unscramble the message, just like unlocking the locker. Other people might see the locker, but they can't open it because they don't know the secret code. The Macaleese cryptosystem is like a super secure locker for your messages that only you and your friend can open with your secret code. Use cases. Sending confidential emails. Protecting information in secure systems. Keeping sensitive communications private between parties. MD algorithm. The MD algorithm is a series of complex operations that turn messages into a unique string of characters to ensure data security and integrity. Imagine you have a secret note saying, "I love ice cream." The MD algorithm changes it into something like 83D4X, which no one can understand without the special process to decode it. Use cases. This algorithm is widely used to protect passwords, confirm digital signatures' validity, and secure data sent across the internet. It's like a super secure lock for information. MD5 algorithm, a cryptographic tool that converts data into a 32-character hexadecimal number. Think of a spell that changes any word you say into a weird mix of symbols. Every time you say the word, the spell makes the same symbols, but nobody can guess the word from the symbols. Use cases. MD5 is used to check data integrity, verify file authenticity, and securely store passwords. Merge insertion. Sort. This algorithm is a hybrid sorting technique that combines the breaking down process of merge sort with the simplicity of insertion sort to sort items efficiently. Imagine sorting playing cards. You split the deck in half repeatedly until each pile has 1 card. Then you merge the piles in order, like combining a 2-card pile and a 5-card pile to make a sorted 2-5 pile. Keep merging until the deck is sorted. Use cases. Organizing databases. Sorting files on a computer. Arranging customer records in order. Merge sort. Merge sort is a method that breaks down a list into smaller pieces, sorts each piece, and then combines them into a fully sorted list. Pretend you have 10 toys and you want to line them up by size. You split them into pairs and arrange each pair. If a toy is alone, it stays as it is. Then you merge the pairs into groups of 4, putting the smaller toy first. If there's an odd one out, it joins after the pairs are sorted. You keep combining the groups, always putting the smaller toys first until all your toys are lined up from smallest to largest. Use cases. Merge. Sort is used in organizing files on a computer, sorting lists of names in an address book, or putting any collection of items in order. Merkle tree, a method to confirm the completeness and accuracy of data. Imagine a puzzle is a set of data. Each piece is a small chunk of the whole. To make sure every piece is correct and none are missing, we use a Merkle tree. First, we pair up the pieces. Then we merge each pair using a special formula, creating a new piece. We repeat this until there's only one piece left, the root. To check the puzzle, we just look at the root. If it's correct, we know all pieces are right. If it's wrong, we know there's a mistake or a missing piece. The Merkle tree ensures data hasn't been altered, which is vital for secure digital transactions and reliable internet information. Merkle-Damgard construction. The Merkle-Damgard construction is a method used to create secure and reliable hash functions in cryptography. Imagine you're organizing your Lego blocks by building a tower. First, you pair up the blocks and stack them to form small towers. Then you pair up these small towers to create larger towers. You keep pairing and stacking until you have one big tower. At each step, you write down which towers you combined, so anyone can check your work by looking at your notes to see that every block is in its correct place. Similarly, in computing, the Merkle-Damgard algorithm takes data, divides it into sections, and combines these sections step by step. Each step is recorded, making it easy to check the data's integrity and identify any issues. Use cases. Securing digital transactions. Verifying the integrity of software downloads. Protecting against data tampering in communication networks. Merkle-Hellman knapsack. Crypto system, a type of encryption that turns messages into numbers based on a hard math problem involving the sums of a group of numbers. Imagine you have a backpack with objects of different weights. You find a unique way to pack them so nobody can guess the total weight. To send a secret note, you represent the message with numbers that match the total weight. Your friend knows how to unpack the weights to read your note. Use cases. Secure communication. Protecting information in computer systems, ensuring privacy in data transmission. Mersenne twister algorithm. A method for creating random numbers that ensures a wide variety and unpredictability. Imagine a dice that, when rolled, almost never repeats the same number. The Mersenne twister algorithm ensures that the numbers rolled are as random as possible, similar to a dice that surprises you with a new number each time. Use cases. Computer simulations that require randomness. Selecting random samples for statistical analysis. Computer games for unpredictable outcomes. Metropolis algorithm. The Metropolis algorithm is a technique for finding the best solution by randomly trying different options and learning from each attempt. Imagine you're in a maze with many paths. You're like an ant that tries different paths and remembers which ones are good and which ones are dead ends. Eventually, you find the quickest way out. The Metropolis algorithm is like playing a guessing game where you keep guessing and learning until you figure out the right answer. It helps solve problems by testing different possibilities and picking the best one. Metropolis-Hastings algorithm. The Metropolis-Hastings algorithm is a way to sample from a complex probability distribution using a series of random steps. Imagine you're trying to solve a jigsaw puzzle. You might swap two random pieces to see if the picture looks better. If it improves, you keep the swap. If not, you might still keep the change occasionally, hoping it'll help in the future. The Metropolis-Hastings algorithm does something similar, but with mathematical problems. Use cases. This algorithm helps find solutions to complex mathematical and statistical problems by exploring different possibilities and deciding which ones are most likely to be correct. It's widely used in science and mathematics for tasks like optimizing arrangements, making decisions, and simulating systems. Middle square method. The middle square method is a simple technique to create a sequence of numbers that seem random. You start with a number, square it, and use the middle part of the result as the next number. If your starting number is 23, you square it. 23x 23 equals 529, and then take the middle digits, 52, as your next number. Use cases. This method is used to generate numbers that appear random for simulations, games, and other applications where you need a series of unpredictable numbers. Midpoint circle algorithm. This algorithm helps to draw perfect circles on a pixelated surface, like a computer screen or graph paper. Imagine you want to draw a circle on graph paper. The midpoint circle algorithm tells you which squares to fill in to make a smooth circle. First, you choose the center of the circle and decide how big you want it to be by picking a radius. Then you use the algorithm to find the points at the top, bottom, left, and right of your circle and start filling in squares to connect these points with a smooth curve. By repeating this process and calculating more points around the circle, especially if it's a large one, you create an even curve that looks like a perfect circle on the graph paper. Use cases: creating graphics in video games, drawing circles in computer-aided design, CAD software, generating patterns for digital art or animations. Miller-Rabin primality test. The Miller-Rabin primality test is a way to check if a number is probably a prime. It uses some math tricks and gets more accurate with more tries. Imagine you want to know if the number 21 is a prime. You'd pick a smaller number like 2 and do some math with it. You calculate 2 to the power of 20 and then see what's left over after dividing by 21. If you get 1, 21 might be prime. If not, it's not a prime. If you keep trying with different numbers and always get 1, then 21 is probably a prime. Use cases. This algorithm helps quickly figure out if big numbers are primes without testing every smaller number, which takes a long time. It's useful for things like computer security, where primes are super important. Minimax algorithm. The Minimax algorithm helps a computer decide on the best move in a game by considering all possible future moves and their outcomes to minimize its chances of losing. In tic-tac-toe, a computer using the Minimax algorithm will think ahead about all possible moves. It considers your potential responses and then chooses the move that is most likely to lead to a win or a draw. Use cases. Minimax is used in two-player games like chess, checkers, and tic-tac-toe, where one player's win is another's loss, and the goal is to outsmart the opponent by looking several moves ahead. Minimum spanning tree algorithm. The minimum spanning tree, MST, algorithm connects all points in a network using the least total distance or cost without forming any loops. Imagine several islands and you want to build bridges to connect them all with the smallest amount of materials. The MST algorithm would find the shortest bridges to connect the islands, making sure there is a path between each one, like a tree with branches that never cross. Use cases: designing efficient road networks between cities, laying out electricity cables or water pipelines, organizing network connections in computer networking to reduce cable length and cost, planning the construction of bridges to connect islands. Min-max algorithm. The min-max algorithm is a strategy used to decide the best move in a two-player game by considering all possible moves and predicting the opponent's counter-moves. Imagine you're playing a game with your friend where you take turns choosing numbers from 1 to 10, trying to get the highest number. To win, you need to think about not just your move, but also how your friend will respond. If you choose 7, your friend might choose 8 and beat you. Min-max helps you look at the worst outcome for every move you could make, and then pick the move that still gives you the best chance to win. For example, you realize that choosing 7 is better than 6 because even if your friend then picks 8, you've still picked the highest number you could before losing. Use cases. Min-max is used in strategic games like chess or tic-tac-toe, where players must consider their moves and anticipate their opponent's reactions to stay ahead and increase their chances of winning. Monte Carlo method. The Monte Carlo method is a strategy that uses random samples to estimate complex calculations. Imagine you want to guess how many blue cars go by your house every day. You could count blue cars at random times and then average those counts to guess the total for the day. Use cases, predicting weather patterns, calculating financial risk, and simulating physical systems. Monte Carlo Tree Search, MCTS. MCTS is an algorithm that finds the best move by playing out random simulations and seeing which moves lead to winning the most. Imagine you're playing a game of tic-tac-toe and it's your turn. MCTS would randomly play out many games for each possible move you could make, then choose the move that wins the most. Use cases. MCTS is used to make decisions in complex games like Go, chess, and video game AI, where planning ahead for all possible moves is too hard. Moth Flame Optimization Algorithm. This algorithm mimics moths flying toward light, helping to solve tricky problems like finding the quickest path somewhere. Imagine you're playing a game to find the fastest way to a park. You try lots of streets, but some are quicker than others. In the Moth Flame Optimization algorithm, pretend you're a moth, and the quickest path is a bright light you want to reach. You start by guessing and checking different streets. When you discover a really fast route, it's as if you leave a shiny breadcrumb trail that other moth friends can see and follow. Soon, all your friends are using the shiny trails to find the fastest way to the park, just like you did. This is how the algorithm works. The moths keep refining their paths until they all zoom to the light on the best route possible. Use cases, deciding on the best layout for a city's roads, figuring out how to pack a lot of stuff into a small space, finding the best way to connect computers in a network. Move to front transform. The move to front transform is a method used to rearrange data in a way that makes repeated information easier to compress. Imagine you have a line of your favorite snacks on a shelf. Whenever you eat a snack, you put its box at the start of the line. Next time you're hungry, your recent favorite snack is right in front for you to grab quickly. Use cases. This algorithm is often used in data compression software to improve the efficiency of encoding repetitive data. It's helpful in making files smaller for storage or faster to send over the internet. Multi-level feedback queue. A computer system uses the multi-level feedback queue algorithm to decide which program should run next by sorting them into different levels of priority queues. Imagine a slide at the playground with 3 levels. The top level is for kids who've waited the longest, the middle level is for those who've waited a shorter time, and the bottom level is for the ones who just got there. Kids slide down from the top level first, then the middle, and then the bottom. Use cases, operating systems. Use this algorithm to efficiently manage different programs running on a computer, ensuring that longer waiting programs are addressed first while newer ones eventually get their turn. Naive Bayes algorithm. Naive Bayes is a simple prediction method based on the likelihood of certain outcomes, assuming each feature is unrelated to others. Imagine a bag with 100 marbles, 40 red, 30 blue, and 30 green. If one friend prefers red and another green, the Naive Bayes algorithm helps guess their chances of picking their favorite marble. Use cases. Naive Bayes helps decide which emails are spam, recognize someone's voice, or suggest what movie you might enjoy based on your past choices. Needleman-Wunsch algorithm. The Needleman-Wunsch algorithm is a method for lining up 2 sequences to find the highest level of similarity. It scores matches and differences, and it can insert gaps to optimize alignment. Let's say Tom and Lily have 2 strings of letters, Gattaca and Gehatgu. Using the Needleman-Wunsch algorithm, they create a grid and compare each letter to find the best match. They may add gaps like a space to aid in alignment. For example, Tom's Gattaca may become Gattaka to better align with Lily's GCA-TGCU, showing where the letters are the same or different. Use cases. The Needleman-Wunsch algorithm is used in genetics to compare DNA, RNA, or protein sequences. It's essential for understanding evolutionary relationships, gene function, and genetic diseases. Neural network algorithm. A neural network is a computer program that learns to recognize patterns and make decisions. It's designed to work like the human brain, with parts called neurons that look at different pieces of information and help solve a problem. Think of it like playing a guessing game with animal cards. You can only see parts of the animal, like a jigsaw puzzle. In this game, you have friends who are experts in certain animal features, stripes, tails, or ears. Each friend guesses the animal based on their expertise, and then you combine all the guesses to figure out the whole picture. A neural network does the same by using neurons, each focusing on a specific part of the picture. They work together to guess the animal correctly. Use cases. Neural networks are used in many places, like when your phone recognizes your face to unlock, helping doctors find diseases in medical images, or even helping cars drive themselves by recognizing road signs and obstacles. Newton-Raphson method. The Newton-Raphson method is a way to find the solution to an equation by making repeated, improved guesses. Imagine you're trying to split a number into two equal parts, like cutting a cake so you and your friend get the same amount. If your first cut isn't exactly in the middle, you'd adjust and cut again. Each time you're getting closer to the perfect middle slice. That's like the Newton-Raphson method, but with figuring out answers in math. For example, let's say you want to know what number when multiplied by itself gives you 9. You guess 3 because 3 times 3 is 9. But what if you didn't know it was 3? You'd start with a guess, maybe 4. Check how good your guess is. Then use the Newton-Raphson formula to make a better guess. Maybe you'd adjust to 3.5 next, then 3.1 and so on, until you're so close to 3 that it's just right. The Newton-Raphson method is used in many situations, like when engineers are designing buildings and need to calculate measurements precisely, or in finance to figure out investment risks. It's a way to solve tricky math problems in the real world by making smarter guesses each time. Newton's method. Newton's method is a mathematical process that helps you find the lowest point on a curve, a point where the slope is 0, by taking systematic steps. It's like playing a game of hot and cold to find a hidden treasure, except you use math to make your guesses smarter and get to the treasure faster. Imagine you're trying to roll a marble into the lowest point in a bowl. You give the marble a gentle nudge and watch which way it rolls. If it moves closer to the bottom, you nudge it again in the same direction. If it moves away from the bottom, you try a different direction. Newton's method is like nudging the marble in the best direction each time, using math to be more precise, so it reaches the bottom quickly. Use cases, finding the best settings for machines to work efficiently. Adjusting recipes in cooking to get the best flavor. Balancing budgets to minimize costs in businesses. Improving computer graphics in video games for smoother visuals. EncryPT. EncryPT is a secure encryption method that uses complex math, known as lattice-based cryptography, to protect information from being read by anyone other than the intended recipient. It's designed to be safe, even against future quantum computers. Think of EncryPT like a tricky lock on a treasure chest containing your secret note. You scramble the note with this lock, which only your friend has the key to open. Even if a nosy pirate finds the chest, they can't read your note because they can't unlock it. Use cases. EncryPT is used to safeguard sensitive information in digital communications such as emails and files, ensuring that only authorized parties can access the content. It's important for maintaining privacy and security in various online transactions and communications. Odd-even sort. The odd-even sort algorithm is a method for arranging numbers so that all odd numbers come before all even numbers, while maintaining their original sequence. Imagine you're lining up red and blue marbles, so all reds are together and all blues are together without mixing up the order they were in your bag. Use cases. This algorithm is useful when you need to separate odd and even elements of a list while keeping their initial order intact. PageRank algorithm. The PageRank algorithm assigns a numerical value to each web page based on how many other pages link to it and the importance of those pages. It's like figuring out the most popular person in school by seeing who has the most friends, especially friends who are themselves popular. Imagine every student starts with 1 point. If a student is friends with a very popular student, they get more points. Over time, as you keep adjusting the points based on friendships, you'll see who is the most popular by who has the most points. PageRank does something similar with websites, giving more points to sites linked by other important sites. Use cases. PageRank helps search engines like Google rank web pages. The higher a page's PageRank, the more likely it is to show up at the top of search results when someone looks for related information. Palier Cryptosystem. The Palier cryptosystem is like a secret code that only you and your friend can understand. It uses big special numbers to turn a message into a secret that can only be solved by someone who has the key. Imagine you wrote a note and locked it in a box. You send the box to your friend, and only your friend has the key to open it. No one else can peek inside. In this system, you make a special lock, public key, using math with big special numbers. When your friend gets the box, they use their very own key, private key, that fits perfectly with the lock to open the box and read your note. Use cases, sending secret emails that only the right person can read, protecting personal information in online services, keeping votes private in electronic voting systems. Pancake sorting algorithm. This algorithm rearranges a sequence by repeatedly flipping sections of it, similar to sorting pancakes by size using a spatula. Imagine you have differently sized pancakes in a stack. To sort them, find the largest pancake and flip everything above it to put it on top, then flip the whole stack to put it on the bottom. Repeat this until they're all sorted. Stack sizes are 4, 1, 3, 2, 1. Find the largest pancake, 4, and flip the top part to get 4 on top. 2, 3, 1, 4. 2. Flip the whole stack, 4, 1, 3, 2, 3. Now ignore the bottom pancake, 4, since it's in place. Find the next largest, 3, and flip the top to get 3 on top. 2, 3, 1, 4. Flip everything but the bottom pancake to get 3 at the bottom. 1, 3, 2, 4, 5. Repeat the process for pancake size 2, then 1 until sorted. 1, 2, 3, 4. Use cases include teaching sorting algorithms, solving related puzzles, or organizing objects in constrained environments. Park-Miller Random Number Generator. A method for creating seemingly random numbers through a fixed mathematical process using an initial seed number. Imagine you have a magic box that takes a secret number, let's say 1, then uses a special math trick on it to give you another number that seems random. If you use the same secret number again with the same trick, you'll get the same random number. That's how the Park-Miller algorithm works. Use cases, frequently employed in computer programs and video games, to simulate randomness for things like loot drops, character encounters, or unpredictable events. Particle filtering. Particle filtering is a method for predicting an object's location by guessing and refining those guesses using evidence. Imagine you're playing hide and seek. You're it, and your friend is hiding somewhere in a big park. You have magic glasses that let you see footprints for a short time. Those footprints guide you to your friend. Each guess where your friend might be is a particle. When you see footprints, you keep guesses near them and discard the rest. Slowly, you focus on the area where your friend is likely hiding. Use cases. 1. Tracking objects or people in motion. 2. Navigation and mapping for robots. 3. Estimating positions in systems with uncertainty. Particle swarm. Optimization. Particle swarm optimization, PSO, is a simple yet effective algorithm that mimics the social behavior of birds or fish. It's used to find the best solution to a problem by having a group of particles or points move around in a search space. Each particle adjusts its movement based on its own experience and the success of neighboring particles, gradually getting closer to the optimal solution. Imagine you're playing hide and seek with your friends. Everyone chooses a different hiding spot. After a while, you peek to see who is hidden the best. Then, everyone changes their hiding spot to be closer to the best hider. With each round, everyone gets better at hiding by learning from the best, until you all find the perfect hiding spot together. Use cases. PSO is used in various fields such as engineering for optimizing design and control systems, computer science for artificial intelligence and machine learning tasks, economics for portfolio optimization, many other areas where finding the best solution in a complex space is necessary. Partition problem. This algorithm determines if a set of positive numbers can be split into two groups with the same sum. Imagine you want to share your candies equally with a friend. The partition problem algorithm checks if you can split your candies into two piles with an equal number of candies in each. You add up all your candies and then use the algorithm to find out if there's a way to make two equal piles. If it works, you can share your candies fairly. If not, you'll need another way to share. The partition problem algorithm is useful in many situations, such as sharing items evenly or dividing tasks fairly among people. Patience. Sorting patience. Sorting is a sorting algorithm inspired by the card game Patience. It sorts items by creating and organizing piles. Think of sorting colored pencils by length. You take the shortest pencil and start a new pile. Then you take the next shortest pencil and place it on top, repeating this process to form a sorted pile. Use cases. Patience. Sorting is used in computer science for tasks like organizing data and improving performance of certain types of search algorithms. PBKDF algorithm. The PBKDF, password-based key derivation function algorithm, strengthens simple passwords to better protect online accounts from hackers by mixing them with random data and repeatedly processing them. Imagine your password is MagicKey. PBKDF mixes MagicKey with random stuff to create a new, complicated key. It's like adding pepper to a soup and stirring it lots of times to make a unique flavor that only you know. Use cases. PBKDF is used to secure passwords for online banking, email accounts, and any system that needs strong protection to ensure only the right person gets access. Pigeonhole. Sort. This is a sorting method where you group items with similar features into their own categories, just like sorting objects into different boxes. Imagine you have some socks of different colors and you want to sort them. You make piles for each color, one for red, one for blue, one for green, and so on. Each pile is like a pigeonhole. You go through each sock, putting it in the pile that matches its color. When you're done, each pile has socks of just one color. Now your socks are sorted. 1. Sort each item into the right group, pile or pigeonhole, based on its feature, like color. 2. Once everything is in the right group, arrange the groups in a specific order. Use cases. Pigeonhole. Sort is handy when you have a lot of things that are similar in number to the categories you're sorting them into, like organizing books by genres when you have about the same number of books in each genre. PNG compression algorithm. The PNG compression algorithm reduces image file size without sacrificing quality, perfect for images with text and transparency. Imagine you have a large photo of a puppy. The PNG algorithm shrinks the photo's size by identifying repeated color patterns, like areas of the same blue, and encoding them efficiently so that the file takes up less space. Use cases. The algorithm is ideal for web images requiring clarity, such as logos, illustrations, and graphics with text. It ensures fast sharing and loading while preserving the original look of the image. Polig-Hellman algorithm. Brief description. The Polig-Hellman algorithm is a method for encrypting and decrypting messages using numbers and remainders, ensuring that only someone with the correct key can read the message. Imagine you have a lockbox with a special number lock that uses a big number P. You choose a secret number A and combine it with your message number B. You lock the box by doing some math with A, B, and P. Your friend who knows the secret number A can unlock the box with their own number C and the big number P to read the message. Use cases. The Polig-Hellman algorithm is primarily used in secure communication systems to protect information from being read by anyone except the intended recipient. Pollard's P1 algorithm. This is a method to find one factor of a number by using the properties of numbers and division. Asterisk, 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 asterisk. Imagine you have the number 15 and want to find its prime factors. You start with a random number, say 2. You raise 2 to increasing powers like 2, 4, 8, etc. And for each result you find the remainder when you divide by 15. When the remainder starts repeating, you look at the differences between them. If you find the greatest common divisor, GCD, of any two differences is more than 1, you found a factor of 15. Asterisk, asterisk, use cases. breaking down large numbers into prime factors in cryptography, simplifying complex math problems involving division, finding factors in algorithms that require number theory knowledge. Pollard's row algorithm. This algorithm is a clever shortcut to find factors of a large number. Think of it as a number detective game. If you have a number like 91 and want to find which two numbers multiply to make it, you start with a number like 2 and use a special math rule over and over. You're looking for a repeating pattern in the numbers that come out of this rule. When you see it, you've found your clue. For example, if you keep seeing 4, 6, 9, 3 repeating, that tells you 7 and 13 are the numbers that multiply to make 91. Use cases. This algorithm is handy when you want to break down a big number into smaller pieces, like in cryptography, where you need to figure out secret keys. Postman sort postman. Sort is an algorithm that organizes information in a sequence, making it easier to manage, much like a mail carrier sorting letters by address. If the mail addresses are 5, 3, 8, 1, and 4, postman sort will arrange them as 1, 3, 4, 5, and 8 to streamline delivery. Use cases. This algorithm is useful in postal systems, delivery route planning, and any situation where items need to be sorted in a specific order for efficiency. Post-quantum cryptography. Post-quantum cryptography consists of encryption methods designed to be secure against the powerful capabilities of future quantum computers. Think of a secret box that you can lock with a special combination. Currently, people can use tools to figure out the combination and open the box. However, post-quantum cryptography is like a lock with a combination so complex that no one can find the right numbers, not even with the most advanced tools. Use cases. These algorithms are used to safeguard sensitive information, such as personal communications, financial transactions, and government secrets, in a world where quantum computing could break current encryption methods. Primality testing algorithm. A primality testing algorithm checks if a number is a prime number. A prime number is a number that can only be divided by 1 and itself without leaving any remainder. To see if 7 is prime, we divide it by numbers between 2 and 6. It's not divisible by 2, 3, 4, 5, or 6, so 7 is prime. Use cases. This method is good for small numbers. For bigger numbers, other methods are better. But you can use this simple way to find out if smaller numbers are prime. Prim's algorithm. Prim's algorithm is a method for finding the shortest set of paths to connect all points in a network without any loops. Think of a group of islands connected by bridges. To connect all the islands with the shortest total length of bridges, you start with one island and choose the shortest bridge to another. Then keep choosing the shortest bridge from your connected islands to an unconnected one until all islands are connected. Use cases. Designing efficient road networks in a city. Laying out electricity cables or water pipes with minimal material. Creating computer networks with least amount of cabling. Principal Component Analysis, PCA. PCA simplifies data by focusing on the most important features. It's like tidying up a room full of toys by grouping similar ones and then picking the main characteristic of each group to organize them. Imagine your room is cluttered with toys. PCA would first help you group toys by color, size, or shape. Then it would help you find the most standout feature of each group, such as color for red toys. Finally, you'd organize the toys by these key features, making your room neat and your toys easy to find. Use cases. Reducing the number of variables in data analysis. Visualizing complex data by simplifying it. Improving the performance of machine learning models by removing irrelevant information. Priority scheduling algorithm. Priority scheduling is a method used by computers to decide which task to do next based on importance. Imagine you're at home with a list of chores from your mum. Each task has a different level of importance. You choose to do the most important tasks first, like cleaning your room, because mom says you can't go out to play until it's tidy. For example, you might put away your books first to prevent them from getting damaged, then pick up your clothes, and finally organize your Lego sets last. Even though all chores are important, some are more urgent than others. Priority scheduling is used in computers to sort out tasks. The computer checks which tasks are most important and does those first, just like you sorted your chores. Quadratic probing. Quadratic probing is a method to deal with two items that should go in the same spot in a hash table. Imagine you have a box with many compartments to store your different toys. Each toy should be placed in a particular compartment, but sometimes two toys might be assigned to the same one. Let's say you want to put a new toy car in compartment number 3, but it's already occupied by a toy soldier. To find a new spot for your car, you would try the next compartment by moving over 1, then 3, then 5 more compartments from your starting point. This is like skipping 1, then 2, then 3 compartments each time. Use cases. This technique helps computers store and find information quickly, even when many pieces of information need to share the same space. Quadratic residue. Diffie-Hellman algorithm. A secure method for two parties to create a shared secret key using the mathematical concept of quadratic residues. Two friends, Alice and Bob, want to create a shared secret. Alice chooses 3 and Bob chooses 5 as their private numbers. They agree on a public large number, 11. Alice calculates 3 circumflex 2 equals sign 9, and the remainder when divided by 11 is 9. Bob calculates 5 circumflex 2 equals sign 25, and the remainder when divided by 11 is 3. They exchange their remainders. Alice then calculates 3 circumflex 3. The remainder Bob sent raised to her private number, and the remainder when divided by 11 is 1. Bob calculates 9 circumflex 5, and the remainder when divided by 11 is also 1. They both arrive at the shared secret number, 1. Use cases, secure communication channels, encrypting messages in online transactions, protecting sensitive data exchanges between devices. Quadratic sieve algorithm. The quadratic sieve algorithm is a method for factoring large numbers by finding two smaller factors that multiply to form the original number. Imagine you have the number 91, and you want to find two numbers that multiply to make 91. This algorithm finds pairs of numbers that, when squared, leave the same remainder after dividing by 91. For example, 5 squared is 25, and 12 squared is 144. Both leave a remainder of 25 when divided by 91. These are known as quadratic residues. Using these residues, you create equations that help you find the factors. Solving these equations, you might find that 8 and 11 are the factors of 91 because 8 times 11 equals 88. And when you add 3, which is 5 squared, you get 91. Use cases. The quadratic sieve algorithm is used in cryptography, especially for breaking encryption that relies on the difficulty of factoring large numbers. It's also used in mathematics and computer science for research and to teach concepts related to number theory and algorithms. Quantum adiabatic algorithm. This algorithm is a quantum approach to swiftly find the best solution to a problem without checking every possibility. It's like a shortcut for solving complex puzzles. Think of trying to find the fastest way out of a maze. Instead of walking every path, the quantum adiabatic algorithm lets a quantum computer slide directly to the exit, skipping all the wrong turns. Use cases. Optimizing travel routes for delivery trucks. Figuring out the best layout for electronic circuits. Solving complex scheduling problems like planning classes at a school. Quantum annealing algorithm. The quantum annealing algorithm is a fast method for finding the best solution to a problem from a set of possibilities using principles of quantum mechanics. Think of having a big, complicated maze. The quantum annealing algorithm is like a smart friend who can quickly try many paths in the maze all at once and find the exit way faster than you could alone. Use cases. This algorithm is useful for solving complex optimization problems like scheduling tasks efficiently, designing computer chips, or finding the most efficient way to pack a lot of different items into a small space. Quantum approximate counting algorithm. The quantum approximate counting algorithm quickly estimates the total number of items that satisfy a certain condition. Imagine you're trying to guess the number of red marbles in a big jar without counting them all. This algorithm is like a magic trick that tells you about how many red marbles there are using the principles of quantum physics, which deals with super tiny stuff. Let's pretend the jar is a machine, and when we ask it about the red marbles, it uses quantum magic to give us a good guess. It's faster than counting each marble, and while it's not perfect, it's usually pretty close. Use cases. Searching through large databases quickly. Solving complex problems in science and engineering. Optimizing systems and processes in various industries. Quantum Approximate Optimization Algorithm, QAOA. The QAOA is a quantum algorithm designed to quickly find near-optimal solutions for complex problems with many variables. Think of trying to solve a giant jigsaw puzzle. The QAOA would be like a super-fast robot that can consider many different arrangements at once to rapidly find a way that the pieces can fit together really well, even if it's not the absolute perfect way. Use cases. The QAOA is used to tackle large-scale challenges that have many possible solutions, such as scheduling, route planning, or any task requiring the selection of the best combination of options from a vast pool of possibilities. Quantum Bell Test Algorithm. The quantum bell test algorithm is a method used to check if two particles are entangled, meaning they are magically linked so that the state of one immediately affects the state of the other, regardless of the distance between them. Imagine Alice and Bob each have a special coin that can show heads or tails. They flip their coins and do a dance if both coins match, or they stand still if the coins are different. After doing this without seeing each other's coin, they compare actions. If they always do the same thing, their coins are magically connected through quantum entanglement. Use cases. Scientists use this algorithm to verify quantum entanglement, which is important in quantum computing, secure communications, and tests of quantum theory. Quantum communication complexity. This is a study of how little communication is needed to solve problems when computers are far apart, using quantum mechanics. Alice and Bob play a game where Alice picks a number from 1 to 10, and Bob guesses it using a magic crystal ball that sends many numbers at once. Bob's crystal ball helps him find the right number quickly. Use cases. Quantum communication complexity helps computers share information quickly and solve problems efficiently using quantum mechanics, which is much faster than normal methods. Quantum counting algorithm. Brief description. The quantum counting algorithm uses quantum mechanics to estimate the number of solutions to a problem, similar to guessing the quantity of items without direct observation. Imagine you have a closed box with some balls inside. The quantum counting algorithm is like a magical pair of glasses that lets you peek at the box and guess the number of balls inside it without opening the box or touching the balls. Use cases. Finding the number of solutions to complex mathematical problems. Estimating the number of items in a large set without counting each one. Quantum cryptographic protocols. Quantum cryptographic protocols are secure communication methods that use quantum mechanics to protect messages. Imagine you have a secret box that changes color every time someone else tries to look inside it. You and your friend each have one of these boxes, and you use them to send secret notes to each other. If someone else tries to peek, the box changes color, and you both know that the secret is no longer safe. You and your friend use a special machine to make and measure tiny particles that act like these secret boxes called qubits. When you measure your qubits, you make a secret code. If an eavesdropper tries to look at the qubits, their state changes, and you can tell that someone is snooping. Use cases. Sending secure messages without anyone else reading them. Safe online communication for banks, military, or personal data. Quantum cryptography. Quantum cryptography uses the laws of quantum mechanics to create secure communication. It involves encoding messages using particles that can exist in multiple states simultaneously. Pretend you have a magical box that changes colors only you and your friend know how to read. When you send a message using the box, it shows colors in a special pattern. If someone else looks at the pattern, it changes and doesn't make sense. Only you and your friend can see the original colors and understand the message. Use cases. Quantum cryptography is used for secure data transmission, protecting banking information, and safeguarding sensitive government communications. It ensures that any attempt at eavesdropping is detectable, making it a powerful tool for security. Quantum digital signature, a type of digital signature that uses quantum mechanics to provide secure authentication, even against quantum computers. Let's say you have a secret handshake with your friend to know it's really them. A quantum digital signature is like a super-secret handshake that uses the magical world of quantum particles to check if a message is genuinely from your friend and hasn't been tampered with. Use cases: sending secure emails that only the intended recipient can verify and trust. Protecting financial transactions from fraudsters using quantum-safe methods, ensuring confidential documents remain authentic and unaltered. Quantum entanglement. Swapping entanglement swapping is a quantum process where two particles become entangled through an intermediary particle. Imagine having two marbles, one red and one blue. If each marble could magically copy its color to another marble far away, that's like entanglement swapping. You mix a piece of the red marble's magic with the blue marble's magic, and now, if the red marble changes, the faraway blue marble changes instantly too. Use cases. Quantum entanglement swapping is used in quantum communication and quantum computing to link particles over long distances, making information sharing faster and more secure. Quantum error correction algorithm. This is a method used to protect quantum information from mistakes that might happen during processing or transmission. Imagine you're sending a note with "hello" written on it to your friend, but you're worried some letters might get mixed up. To help your friend, you add a note saying, "There are two L's." If a letter gets mixed up, your friend can look at the note and know what to fix. Quantum error correction algorithm. A strategy to shield quantum data from possible errors. Simply example. Think of it like a safeguard for a secret note. If parts of your note could get jumbled, you add hints for your friend to fix any mix-ups. Use cases. It's used in quantum computers to make sure they work right, even when there are tiny mistakes. Quantum Fourier transform, QFT. QFT is a quantum algorithm for transforming quantum bits, qubits, by analyzing their individual probability amplitudes in a fast and efficient way, similar to how a normal Fourier transform breaks down a wave into its frequency components. Think of QFT as a way to find out what ingredients are in a fruit smoothie. If you blend different fruits together, QFT can quickly tell you exactly what fruits were used and in what amounts, but instead of fruits, it works with the parts of a quantum state. Use cases. QFT is used in complex quantum algorithms like Shor's algorithm for factoring large numbers, quantum phase estimation for measuring the eigenvalues of operators, and in quantum simulations that require analyzing the properties of quantum systems. Quantum key distribution, QKD. A secure method for sharing secret keys based on quantum mechanics principles. Imagine you have invisible ink that only you and your friend know how to make visible. You write a message with this ink and send it. If anyone else looks at the message, the ink changes and you know it's no longer a secret. Use cases. Secure communication between governments, protecting financial transactions, safeguarding sensitive medical data. Quantum key distribution. Quantum key distribution, QKD, is a secure way to share secret keys between two parties using the laws of quantum mechanics. Think of it like whispering a secret code into your friend's ear while you're both in a room full of noise. If someone tries to eavesdrop, the noise changes and you'll know someone is listening. In QKD, we use quantum particles to whisper the secret code, and any eavesdropping will disturb these particles, alerting us to the intrusion. Use cases. QKD is mainly used in secure communication to protect information from being intercepted or decoded by unauthorized individuals. It's useful for governments, military, banks, and any organization needing high-level security for their communications. Quantum phase estimation algorithm. The quantum phase estimation algorithm is a method to determine the phase associated with an eigenvalue of a quantum operation. Imagine you have a secret spinning top that can spin at different speeds. You want to guess how fast it's spinning without stopping it. By carefully watching how the top behaves over time, you can make a good guess about its spinning speed. Quantum phase estimation is used in quantum computing for tasks like factoring large numbers, simulating quantum systems, and solving complex mathematical problems that are hard for classical computers. Quantum Secure Direct Communication, QSDC. QSDC is a method of sending secret messages using quantum physics, ensuring that only the intended recipient can read them without risk of interception. Imagine you want to send a secret note to a friend in class. Instead of passing a paper note that someone could read, you use a magic box that only your friend can open. If anyone else tries to open it, the note disappears. Use cases. Military communication to transmit sensitive information securely. Private conversations between diplomats to maintain confidentiality. Secure financial transactions to prevent fraud and interception. Protecting personal privacy in digital communications. Quantum teleportation. Quantum teleportation is a method of sending quantum information, like the exact state of a particle, from one place to another without physically moving the particle itself. Suppose you have a toy car that you want to show to your friend on the other side of the playground, but you can't walk or throw it to them. Instead, you both have magic walkie-talkies that let you describe your toy car so well that your friend's identical toy car becomes a copy of yours as soon as you finish describing it. That's kind of like quantum teleportation. Quantum teleportation is used in advanced communication and computer technologies that require the secure and exact transfer of information, like in quantum cryptography and quantum computing. Quantum tomography. This is a technique to figure out the inner workings of a quantum system by analyzing many measurements. Think of it as solving a puzzle about a light-producing box. Imagine you have a toy that's supposed to change colors, but it's not working right. Quantum tomography is like using a special tool to take a lot of snapshots of the toy's colors. Then, with some clever calculations, you work out how to fix the toy so it shows the right colors. Use cases. Quantum tomography is useful for fixing machines in quantum computers and for scientists trying to understand mysterious quantum particles. It helps make sure that everything in the quantum world is working just as it should. Quantum walk algorithm. The quantum walk algorithm is a quantum version of the classic random walk. It allows a particle to walk along multiple paths simultaneously rather than just one. Think of standing at a crossroads where you can flip a coin to decide whether to go left or right. In a quantum walk, when you flip the coin, you go both left and right at the same time. This happens because in quantum mechanics, particles can be in multiple places at once. Use cases. Quantum walks can help in solving complex computational problems, optimizing networks and searching databases faster than traditional algorithms. They are also used in developing new quantum computing technologies and understanding physical processes at a quantum level. Quick merge sort algorithm. The quick merge sort algorithm is a hybrid sorting technique that combines the speed of quicksort with the stability of merge sort to arrange items in a particular order quickly. Consider 8 numbered cards, 5, 3, 8, 2, 7, 6, 1 and 4. 1. Split into smaller piles. Pile 1, 5, 3, 8, 2. Pile 2, 7, 6, 1, 4, 2. Sort each pile. Pile 1, 2, 3, 5, 8. Pile 2, 1, 4, 6, 7, 3. Merge sorted piles. Combined. 1, 2, 3, 4, 5, 6, 7, 8. Use cases. The quick merge sort. Algorithm is useful for organizing data such as numbers, names, or other items that need to be sorted in databases, file systems, and various software applications. It ensures efficient and reliable sorting even for large sets of data. Quicksort is an efficient sorting algorithm that divides a list into smaller parts based on a chosen element, called the pivot, and then recursively sorts those parts. Imagine you're sorting your playing cards by number. You pick one card as the pivot and move all cards with a lower number to one side and those with a higher number to the other side. Repeat this process with the smaller groups until all cards are sorted. Use cases. Quicksort is used in various applications for organizing data, such as ordering numbers, arranging files on a computer, or sorting names in an alphabetical list. Rabin cryptosystem. This is a secure way to send secret messages using mathematics. It's tough to break because it uses a math problem that's hard to solve. Imagine you want to send hi to a friend without anyone else reading it. You pick 2 special numbers, let's say 3 and 11, and multiply them to get another number, 33. This number, 33, is like a special lock only you and your friend know how to open. For HI, H is the 8th letter and I is the 9th. You do some math with these numbers and the lock number 33 to scramble them. This makes a secret code that looks like gibberish to anyone else. Your friend, who knows the two special numbers, 3 and 11, does the reverse math with the secret code and the lock number 33 to unscramble it and read shy. Use cases. The Rabin crypto system is a way to keep information safe. It's used when you need to make sure that only the right person can read your message, like sending passwords, secret plans, or personal notes. Rabin-Karp algorithm. The Rabin-Karp algorithm is a technique for finding a specific sequence of characters, called a pattern within a larger text. It speeds up the search by converting the pattern and text chunks into numerical values, known as hash values, for comparison. Imagine you're playing a game where you need to find the word apple in a jumbled-up page full of letters. Instead of reading each word, you use a special magnifying glass that only shows you sections as long as the word apple. You look through the magnifying glass, moving it across the page, checking each section quickly by comparing a secret number each section makes instead of reading the words. When the numbers match, you've found apple. Use cases. Searching for a word or phrase in a large document or database. Plagiarism detection software to find similar text passages. DNA sequence analysis to locate specific sequences within genomes. Rabin-Miller primality test. A method to determine if a number is probably prime by using modular arithmetic and random numbers. Let's test if 11 is prime. Choose 2 as a random number, called base. Calculate 2 circumflex 10% 11, which equals 1024% 11, giving us 4. Finally, square the result and modulo by 11 again, getting 4 squared % 11 equals sine 5. We check if this result is 1 or 10, since 10 is 11, 1. Since 5 is neither, 11 fails this test round. However, we should do more rounds with different bases to be sure. Use cases. Cryptography, to generate large prime numbers for encryption keys. Mathematics for prime research and number theory studies. Computer science in algorithms that require prime numbers. Radix exchange. Sort-radix exchange sort is a sorting algorithm that organizes numbers by grouping them according to each digit, starting from the least significant digit and ending with the most significant digit. Imagine sorting the numbers 345, 216, 123, 456, and 789. First, group them by the last digit. Pile 3, 123, pile 5, 345, pile 6, 216, 456, pile 9, 789. Next, sort the groups by the second to last digit. Pile 1, 123, pile 2, 216, pile 4, 345, 456, pile 7, 789. Finally, sort by the first digit to get them in order. 123, 216, 345, 456, 789 use cases, radix exchange. Sort is useful for sorting large sets of numbers, especially when the numbers have the same length and the distribution of digits is uniform. It's efficient for sorting data like phone numbers, identification numbers, or any numerical data where the position of each digit is significant. Radix sort radix. Sort is a sorting method that organizes numbers by their individual digits, starting from the least significant digit to the most significant. Imagine sorting a deck of numbered cards, 0, 99, using buckets labeled 0, 9. First, sort the cards based on the rightmost digit, one's place, into the buckets. Then collect and sort them based on the next digit to the left, 10's place. Repeat until all digits are sorted. Use cases. Radix sort is useful for sorting large sets of data, like phone numbers or long integers, where comparison-based sorts, like quicksort, could be less efficient. Raymer-Douglas-Pucher algorithm. The Raymer-Douglas-Pucher (RDP) algorithm simplifies lines or shapes by reducing the number of points needed to represent them without significantly changing the overall form. Imagine you draw a zigzag line that looks like a lightning bolt, with lots of little jigs and jags made up of many points. The RDP algorithm would smooth out the lightning bolt, keeping only the points that are necessary to recognize it as a lightning bolt. The result is a cleaner, simpler line that still looks like a lightning bolt but with fewer points. Use cases. The RDP algorithm is used in digital mapmaking to simplify road shapes, in computer graphics to reduce the complexity of shapes for faster processing, and in data compression to minimize the amount of information needed to store shapes. Random forest algorithm. Random forest is a method that uses multiple decision trees to make better predictions. It's like asking a group of friends to help decide on the most common answer. Pretend you want to guess the most common fruit flavor in a bowl of candy. You ask several friends to take a scoop and tell you their main flavor. Then you combine their answers to find the most common flavor. Use cases. Random forest is used to recognize handwriting, predict stock prices, and decide if an email is spam or not. Randomized American flag. Sort. This algorithm sorts items by randomly arranging them until they form a pattern like the American flag. Imagine you have red, white, and blue marbles. You throw them into a box without looking, then check if they look like the American flag. If not, you shake the box and try again until it's right. Use cases. Organizing data in a fun and unpredictable way, testing sorting efficiency with randomization. Randomized bead. Sort. This algorithm sorts beads from lightest to darkest, using random comparisons and swaps. Imagine you have a necklace with beads of different shades. You mix them up and then take 2 beads at a time, comparing their colors. If the bead you picked up first is darker, swap places with the lighter bead. Repeat this until all the beads are in the correct light to dark order. Randomized bead sort is helpful for organizing things based on certain characteristics, like sorting beads by shade, separating recyclables by type, or arranging books by size. Randomized binary tree. Sort. This algorithm sorts numbers by building a binary tree with random elements as roots, then retrieving the numbers in sorted order by traversing the tree. Given numbers 5, 3, 8, 2, 7, 4, 9, 1, pick 5 as the root. 2, place 3 to the left of 5, it's smaller. 3, place 8 to the right of 5, it's bigger. 4, insert 2 to the left of 3, and so on. 5. After inserting all numbers, we visit the tree from lowest to highest to get sorted numbers. 2, 3, 4, 5, 7, 8, 9. Use cases. Sorting collections of numbers. Organizing data for quick search and retrieval. Randomized block. Sort. This is a sorting method that groups items and then randomly sorts each group one by one. Imagine sorting your toy cars by color. First, group them by color, then pick a color group at random, say red cars. Next, randomly compare 2 cars within this group and order them by size or model. Keep comparing and ordering the red cars until they're all sorted. After that, move to another color group, like blue cars, and do the same until all the cars are sorted by color. Use cases. Organizing books on a shelf by genre and then by author. Sorting music files on a computer by genre and then by album. Arranging recipes in a binder by meal type and then by prep time. Randomized. BOGO sort. Randomized BOGO. Sort is an inefficient but straightforward sorting algorithm that arranges items by randomly shuffling them until they happen to be in the correct order. Imagine you have a row of numbered blocks and you want them to go from 1 to 5. 1. You mix up the blocks in a random order. 2. Check if the blocks are in the correct sequence. 1, 2, 3, 4, 5. 3. If not in order, mix them up again and recheck. 4. Repeat until the blocks are in the correct order. Use cases. Due to its simplicity but high inefficiency, the randomized BOGO sort is not practical for real-world use and is generally used for educational purposes or as a joke among computer scientists. Randomized Cartesian tree. Sort. Randomized Cartesian tree. Sort is a sorting method that uses a shuffled tree structure to efficiently arrange numbers in ascending order. Consider the numbers 7, 2, 9, 1, and 5. We place them into a randomized Cartesian tree. After organizing them based on their values, an in-order traversal produces a sorted list, 1, 2, 5, 7, 9. Use cases. This algorithm is useful in situations where standard sorting methods may be inefficient, providing better performance through randomization. Randomized cocktail shaker. Sort. This is an improved version of the cocktail shaker sort that starts by randomly mixing up the items before sorting them. It sorts by repeatedly swapping items that are in the wrong order, moving back and forth through the list like shaking a cocktail. Imagine you have some numbered balls in a row. To sort them, you first shake them up to mix them randomly. Then you start from one end, comparing each pair of balls side by side. If the first ball is larger, you swap them. You keep comparing and swapping until you reach the other end. Now you go back, doing the same from the other side. You repeat this, shaking back and forth until all your balls are sorted from smallest to largest. Use cases, sorting a list of names or numbers, organizing data that is mostly sorted but might have some misplaced items, when the randomness can help break up any existing order and potentially speed up the sorting. Randomized cocktail sort. Brief description. Randomized cocktail sort is a sorting technique that alternates between moving forwards and backwards through a list, comparing and swapping items as needed. It incorporates random shuffling to enhance the sorting process. Imagine you have cards numbered 1 to 10 in a random order. You compare two adjacent cards at a time, swapping them if they are in the wrong order. You go from the first card to the last, then reverse back to the start. Before each round, you shuffle the cards to mix them up. Repeat this back and forth process until the cards are sorted from 1 to 10. Use cases. Organizing a shuffled deck of cards in order. Sorting random sequences of numbers. Arranging books on a shelf by height or in alphabetical order. Randomized comb sort. Randomized comb sort is a sorting technique that arranges items into a specific order using random steps to optimize efficiency. Think of sorting a shuffled deck of cards by comparing and swapping cards that are far apart, then gradually reducing the distance until all cards are sorted. If you have 10 cards, you might start by comparing cards 5 steps apart. After each round, you reduce the step size until you're comparing cards next to each other to complete the sorting. Use cases. Randomized comb sort is useful in computer science for organizing lists or databases where traditional sorting methods are slow. It's also handy when the initial order of items is unpredictable. Randomized cycle sort. This algorithm sorts items by randomly selecting elements and placing them in their correct order. Imagine sorting numbered blocks. You randomly pick block 5 and put it in the 5th position. Then you pick block 2 and place it in the 2nd spot. Keep going until all blocks are in order. Use cases. Randomized cycle sort is useful for sorting lists or arrays, such as organizing books on a shelf by their size or students in line by their height. Randomized flash sort. This algorithm sorts items by repeatedly picking random elements and placing them in the correct order. Imagine you want to line up your toy cars by number. You pick a random car and see if any car has a smaller number. If you find one, you place it at the start. Keep picking cars at random and placing them in the right spot until they're all lined up. Use cases. Organizing a deck of cards by number. Sorting numbers in a list. Arranging books on a shelf by their sizes. Randomized gnome sort. A sorting method that randomly shuffles elements before organizing them in order by comparing and swapping adjacent pairs. Imagine lining up random toys to order them by size. Randomized gnome sort is like playing a game where you randomly pick 2 toys and see which is smaller. If the smaller toy is on the left, they stay put. If not, swap them. Keep playing until all toys are lined up from smallest to largest. We have toys numbered 5, 2, 7, 1, 3. We start by randomly picking 2 toys to compare. 5, 2, 7, 1, 3. Compare 5 and 2. Swap to get 2, 5, 7, 1, 3. Continue comparing and swapping until the toys are lined up as 1, 2, 3, 5, 7. Use cases. Randomized gnome sort is used in computing for arranging data when a simple, easy-to-understand method is needed, but it's not suitable for large datasets due to its inefficiency. Randomized in-place merge sort. This is a smart way to sort things where you first break everything into small groups, sort each group, and then mix them back together randomly until everything is in the right order. Imagine you have some numbered cards and you want to line them up from smallest to biggest number. You'd split the cards into 2 piles, sort each pile, and then merge them by choosing cards from either pile at random until they're all in one sorted pile. Use cases, organizing data in computers. Sorting things like books by page number or people by their names in an unpredictable order. Making sorting games more fun by adding randomness. Randomized insertion. Sort randomized insertion sort is a sorting technique that randomly shuffles items before sorting them, making the process more efficient. Imagine you have a deck of cards with different numbers. You want to arrange them in ascending order. You start with no cards in your hand. You randomly pick a card from the deck, and that's your starting card. Next, you randomly pull another card and decide if it goes before or after the first card you picked. You keep picking cards at random and placing them in the correct position relative to the cards you already have in your hand. In the end, all your cards will be in order, even though you picked them randomly. Use cases. 1. Sorting items when the order of input is unpredictable. 2. In programming contests or educational purposes to understand how randomness can improve traditional algorithms. Randomized merge. Sort a faster way to sort things by randomly choosing items and combining sorted groups. Imagine you have a toy box with jumbled up animal toys. To sort them first, you shuffle them all up. Then you pick one toy, and a friend picks another. You see which toy is first alphabetically, and make a small sorted pile. Keep picking toys and sorting them into piles. When you both have your piles sorted, you combine them into one big sorted pile. For example, your friend has a toy lion and you have a toy elephant. You both pick new toys and sort them into your piles. Once done, you mix your piles together so all the toys follow the alphabet order. Use cases. Sorting large lists of numbers or items. Organizing data in databases. Arranging files on a computer. Randomized odd-even sort. This sorting algorithm mixes random shuffling with the odd-even sort method to arrange items in order. Imagine you have cards numbered 1 to 7 shuffled randomly. First, shuffle the cards again. Then look at each pair. Cards 1 and 2, then 3 and 4, and so on, and swap them if they're out of order. Repeat this until the cards are sorted. Use cases. When you need a simple visual way to understand sorting. In educational settings to teach sorting concepts. It can be useful in certain niche situations where its performance might be advantageous. Randomized pancake sorting. This algorithm sorts a stack of pancakes by size using random flips. Imagine you have differently sized pancakes and need to stack them from smallest to largest, but you can only flip several at once using a spatula. The randomized pancake sorting algorithm does this by flipping random portions of the stack until they're all in order. For example, if you have pancakes numbered 4, 1, 3, 5, 2, you might first flip starting from pancake 4, resulting in 2, 5, 3, 1, 4. If you then flip starting from pancake 2, you'd get 4, 1, 3, 5, 2. Repeat until they're sorted 1, 2, 3, 4, 5. Use cases. Educational purposes to teach randomness and sorting. Games that mimic sorting challenges with a fun twist. Algorithms where approximate solutions are acceptable. Randomized patience sorting. This is a sorting technique that mixes the cards up and sorts them into piles before arranging them in order. 1. Shuffle a deck of cards. 2. Create empty spaces for piles. 3. Place the first card in a pile. 4. Compare the next card to the top cards of existing piles. Place it on top of a smaller card or start a new pile. 5. Repeat until all cards are in piles. 6. Sort the cards in each pile, then merge them into a sorted sequence. Use cases, organizing a deck of cards. Sorting data in computer programs where random shuffling can speed up the process. Randomized postman. This algorithm sorts items by randomly choosing a starting point and grouping items that belong together before moving on to the next random point until all items are sorted. Imagine you have 10 letters to deliver to 5 different houses. You start at a random house, deliver all the letters for that house, and then randomly choose another house to continue until you've delivered all the letters. Use cases. The randomized postman. Sort is useful for organizing deliveries or tasks efficiently to minimize unnecessary back and forth movement. Randomized quick. Sort. This algorithm sorts a list by randomly choosing an item as the pivot, then arranging items smaller than the pivot on one side and larger items on the other side. It repeats this process for each section. Imagine you have colored balls numbered from 1 to 10. You pick a ball randomly, say number 5, and place all balls with numbers lower than 5 to its left and all higher numbers to its right. Next, you randomly select a pivot in each group and repeat until all balls are in order. Randomized quicksort is used to arrange items like numbers or words in a specific order efficiently. It can sort students by grades, books by titles, or products by prices. The random pivot choice prevents slow sorting times that can happen with the standard quicksort, especially for poorly arranged lists. Randomized selection algorithm. The randomized selection algorithm is a method to randomly select an item from a group. It works by shuffling the items and then choosing one to ensure a fair and unbiased selection. Let's say you have a box of 10 different stickers. To pick one sticker randomly, you shuffle the stickers in the box and then take one out without looking. Use cases. The algorithm is useful for making fair choices in games, selecting random samples for surveys, or deciding without bias in any situation where a random selection is needed. Randomized shell. Sort. This algorithm sorts items by first grouping them into smaller subsets, sorting each subset, and then progressively regrouping and resorting until everything is ordered. Imagine you have a mix of toy cars and you want to line them up from smallest to largest. Randomized shell sort is like 1. Dividing the cars into groups by size. 2. Sorting each group from smallest to largest. 3. Combining the groups and repeating the process with fewer groups. 4. Keeping this up until all the cars are in a single sorted line. Use cases. Organizing files on a computer, sorting data in databases, arranging products for sale on a website. Randomized smooth sort. This is a sorting algorithm that mixes up the items randomly before arranging them, making it quicker and more fun to sort numbers. Imagine you have cards numbered 1 to 10 all mixed up. To sort them, you shuffle them first, then start comparing pairs, switching them to get the right order. You keep shuffling and comparing until all cards are sorted, smallest to largest. Use cases. Organizing a mixed set of data into a specific order quickly. Enhancing efficiency in sorting when dealing with sequences that may have patterns. Making the sorting process less predictable and more adaptable. Randomized sorting algorithm. This algorithm sorts items by randomly shuffling them into place, which can lead to quicker sorting by preventing repetitive patterns. Imagine you have a bowl of mixed fruit and you want to sort the fruit into separate bowls by type. You blindfold yourself, randomly pick a piece of fruit, and then place it into the matching bowl. You keep doing this until all the fruit is sorted into the correct bowls. Randomized sorting is useful for organizing data, creating fair groupings, or preventing predictable outcomes in various applications such as computer science, gaming, or statistical sampling. Randomized stooge. Sort. This algorithm sorts numbers by mixing them up randomly first and then sorting parts of them step by step. Imagine you have 9 cards numbered 1 to 9. First, you pick a random card, say the card with number 5. Then you make 3 piles, one with cards less than 5, one with the card number 5 itself, and one with cards greater than 5. Next, you would sort just the 2 bigger piles in the same way by picking a random card in each and making new smaller piles. Keep doing this until all the piles are in order, just like arranging your cards from smallest to biggest. Use cases. Randomized stooge sort is great for learning about sorting because it's like a game. It might not be the fastest way to sort things, but it shows how sorting can be done step by step and with a bit of randomness. Randomized strand. Sort. This is a sorting method that mixes random selection with sorting to arrange items efficiently. Imagine sorting beads by color using the alphabet, by repeatedly swapping 2 random beads if they're out of order until all are correctly lined up. We have beads colored red, blue, green, yellow, and orange. We place them randomly as blue, green, red, orange, yellow. We pick 2 random beads, say blue and green. Blue stays before green, so no swap needed. Next, we pick green and red. Green goes before red, so we swap, getting blue, red, green, orange, yellow. We continue randomly picking and swapping beads until they're in alphabetical order: blue, green, orange, red, yellow. Use cases. Randomized strand sort can be used in computer algorithms for organizing data, in games for randomizing elements, or in educational tools to teach sorting principles. Randomized timsort. This algorithm is an improved version of timsort, which sorts items more efficiently by randomly mixing them before sorting, making the process faster. Imagine you have a deck of cards that needs to be arranged by number and suit. First, you shuffle the cards to mix them up. Then you sort small groups of cards, and finally, you combine these groups into a fully sorted deck. Use cases. Randomized timsort is used in computer programs that need to sort large lists or databases quickly, like organizing contacts in an address book or arranging products by price on a shopping website. Randomized tournament sort. Randomized tournament sort is a sorting method where elements are randomly matched in pairs, and winners, higher value elements of each pair, move on to the next round until the largest element is found. Imagine 8 kids, A to H, playing a game where they are paired randomly, and the winner of each pair moves to the next round. After a few rounds, one kid is declared the best player. Use cases include organizing competitions, selecting the maximum minimum in a dataset, and sorting items where traditional comparison might be inefficient. Randomized tree. This algorithm sorts items by randomly choosing a starting item and organizing the rest based on how they compare to it, like sorting balls by color. Imagine we have balls of different shades and we want them lined up from lightest to darkest. We randomly pick a ball as our starting point and place all lighter balls on one side and darker ones on the other, like branches on a tree. We do this until every ball has its place on the tree. Then we collect the balls from the lightest side to the darkest, like climbing down a ladder, to get them all sorted out. We can use this method for organizing books on a shelf by height or students in a line by age. Randomized unbiased shuffle algorithm. The algorithm shuffles a deck of cards, or any list of items, by randomly swapping each card with another, ensuring that every card has an equal chance to be in any position. Imagine you have 10 cards numbered 1 to 10. Start with the first card. Randomly pick another card from the deck and swap them. Do the same for the second card and continue until you've swapped all the cards. Now the cards are mixed up randomly. Use cases. Shuffling playing cards for a fair game. Randomizing the order of quiz questions. Mixing up names for a random draw or selection. Ransack algorithm. The Ransack, random sample consensus algorithm, is a technique that helps to find and validate a model within a dataset that contains outliers. It repeatedly selects random subsets of the data to estimate the model parameters and determines the best fit by looking for the subset with the highest number of inliers, data points that fit the model well. Imagine you're playing a game where you're looking for a hidden object in a room full of decoys. You randomly pick a few items and guess which one could be the real hidden object. If your friends also pick the same item, then it's likely the correct one. The Ransack algorithm does this by repeatedly choosing random items and checking if most people agree on the same item. Use cases 1. Finding the best fitting line in a scatterplot with some noisy points. 2. Estimating the location and orientation of an object in robotics or computer vision. 3. Separating the background from the foreground in an image with noise or unwanted objects. RC4 algorithm. The RC4 algorithm is a simple method for encrypting messages using a shared secret key to keep them private. If you want to send a coded note to your friend, you use RC4 to scramble it using a special password that only you two know. It's like using a secret alphabet that only you and your friend can decode. Use cases. RC4 is used to secure private communications, such as emails or messages, so that only the intended recipient with the right key can read them. Recurrent neural network, or RNN. A recurrent neural network, RNN, is a type of artificial neural network that can remember previous information and use it to process new data. It's like having a memory that helps the network understand sequences, such as sentences or events over time. Think of an RNN like a diary where you write what happened each day. When you write a new entry, You read the past entries to remember what happened before. This helps you understand today's events better. Use cases. RNNs are used for tasks that involve sequences, such as language translation, speech recognition, and predicting the next word in a text. They help machines understand patterns that occur over time. Red-black tree algorithm. A type of binary search tree that stays balanced by coloring nodes red or black and following certain rules. Imagine a tree where each number is a ball with a color, red or black. The numbers are sorted from smallest to largest. The red-black tree keeps the tree even by coloring each ball red or black, not allowing two red balls in a row, having the same number of black balls from the root to any end. If you add a new ball, the tree might change some colors or move balls to stay even. For example, adding a red ball may cause other balls to turn black to maintain balance. Removing a black ball might result in other balls changing color or position to keep the tree even. The red-black tree algorithm keeps the tree tidy and makes finding numbers fast. Use cases. Databases to organize and retrieve data efficiently. Language libraries for sorted collections. Operating systems for managing various tasks. Red-black tree deletion. The red-black tree deletion algorithm preserves the balance of a red-black tree after a node is removed, ensuring it still follows the red-black tree rules. Imagine a tree with red and black balls. If we take off a red ball, the deletion algorithm helps us rearrange or recolor the remaining balls so the tree doesn't tip over and stays neat. Use cases. Maintaining sorted data in a balanced search tree for quick lookups, insertions, and deletions, implementing associative arrays, where values are linked to keys, supporting undo operations in applications by maintaining a balanced version history tree. Reed-Solomon error correction. The Reed-Solomon algorithm adds extra data to messages so that if errors occur, like missing or wrong information, the original message can still be understood. Imagine sending a secret message with a puzzle. If some pieces go missing, the extra pieces you included help solve the puzzle and reveal the original message. Use cases. Fixing errors in QR codes. Correcting data sent to and from space probes. Ensuring music and video files play without glitches. Regular falsi method. The regular falsi method is a mathematical technique used to find the exact value of something by starting with two guesses and iteratively refining them. Imagine you have a lemonade stand and want to find the perfect price. You start by picking two prices, one too high and one too low. If more people buy lemonade at the lower price, you know the perfect price is closer to that one. If more people buy at the higher price, then it is closer to that. You keep adjusting the price between these 2 points until you find the best one. Use cases. Determining the root of an equation. Optimizing business strategies. Engineering calculations requiring precise measurements. Ringdale algorithm. The Ringdale algorithm is a method for encrypting data, turning readable text into a scrambled format that can only be deciphered with a special key. Think of the Ringdale algorithm as a magic box. You put a note inside, lock it with a special key, and the note turns into a secret code. Only someone with an identical key can unlock the box and decode your note. Use cases. Protecting personal information on the internet. Keeping sensitive data secure on computers and smartphones. Encrypting files to ensure they are safe from unauthorized access. Reversed cipher algorithm. A method for encoding messages, so only people with a special key can read them. You write hello and use the algorithm with a key to turn it into XQYZ. Only someone with the key can change XYZZ back into hello. Use cases. Keeping private messages secure, protecting sensitive data, and ensuring confidential communication. Round-robin scheduling. Round-robin scheduling is a method that gives each task a fixed amount of time to work before moving on to the next task. This keeps everything fair and efficient. Imagine 4 kids, Anna, Ben, Cindy, and David, want to play with a single toy car. They use round-robin scheduling, so each kid plays with the car for 5 minutes and then passes it to the next kid. After everyone has a turn, they start again with Anna. This way, they all share the toy car equally. Use cases, round robin. Scheduling is used in computers to manage how programs share the central processing unit, CPU. It helps the computer run smoothly by giving each program a turn to work for a short time and preventing any single program from using the CPU for too long. RSA algorithm. RSA is a method for secure communication that keeps data safe through encryption using a pair of keys. Imagine you have a box that needs two different keys to open. You give one key, the public key, to everyone, but keep the second key, the private key, to yourself. To send a secret note, your friend locks the box with your public key, and only you can open it with your private key. For example, if your secret word is shy, you convert the letters to numbers, like 8 and 9. You then use your public key to change these numbers and send them to your friend. Your friend uses their private key to change the numbers back into the letters chai. RSA is commonly used to secure emails, online transactions, and for signing digital documents, ensuring that private information stays private. RSA blind signature. The RSA blind signature is a method that allows a person to obtain a digital signature on a message without revealing its content to the signer. Imagine Alice wants Bob to sign a secret note. She puts it in a special envelope that hides the message. Bob signs the outside of the envelope. Then Alice opens it and can show everyone that Bob signed her note, but Bob never saw what he signed. Use cases 1. E-voting systems, where votes are kept secret but need to be verified. 2. Anonymous digital cash transactions, where payment authorization is required without revealing identity. 3. Secure messaging, where senders need their messages certified without exposing the content to the certifier. RSA cryptography. RSA is a method for securing data by encoding it with a key that only the intended recipient can decode. Imagine you have a secret note that only your friend should read. You turn the note into a secret code that only your friend knows how to turn back into the note. This is like locking your note in a special box that only your friend has the key to open. Use cases. RSA is used to protect sensitive information sent over the internet, like credit card numbers, and to ensure that messages and documents are authentic and haven't been tampered with. RSA cryptosystem. RSA cryptosystem is a secure method for encrypting messages and creating digital signatures, relying on the complexity of factoring large prime numbers. Asterisk, 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 asterisk. Imagine you want to send a secret note to your friend. You pick two prime numbers, like 5 and 7. Multiply them to get 35, your public key. Then find a special number, 11, that helps you figure out your private key, 3. You turn your note into numbers, change them using your public key, and send these new numbers. Your friend uses the private key to turn those numbers back into your original note. Asterisk, asterisk. Use cases. RSA is widely used for secure data transmission online, such as sending emails or making transactions. Its unique key pair, public and private keys, ensures that only the intended receiver can read the message, keeping the information safe from others. RSA digital signature algorithm. The RSA digital signature algorithm is a way to check that a digital message or document comes from the person who claims to have sent it and hasn't been changed. Imagine you have a secret handshake that only you and your best friend know. When you perform this handshake, your friend knows for sure it's you. Now think of the digital handshake as a special digital code. When you send a message, you add your unique code, like the special handshake, to prove it's really from you. Use cases. 1. Secure email, ensuring that the email you receive is really from the person it says it's from. 2. Software security, making sure that the software update you download is the authentic one from the software company. 3. Online transactions, confirming that the banking instructions you're receiving are from your bank and not a scammer. RSA encryption, RSA. Encryption is a method of securing messages using mathematical properties of prime numbers. It allows you to send encrypted messages that only the intended recipient can read. Say you want to send HI secretly. Using small prime numbers for simplicity. 1. Choose two primes, 5 and 7. Multiply them to get 35, your public key. 2. Choose a smaller number, 11, with no common factors with 5, 1 asterisk, 7, 1 equal sign 24, your private key. 3. Encrypt high by converting H, 8th letter, and I, 9th letter, into numbers, then raising each to the 11th power, and finally taking the remainder when dividing by 35. 4. Send the encrypted numbers. 5. Your friend uses the public key, 35, to decrypt the message and gets back the original shui. Use cases. Email encryption to protect sensitive information. Secure online transactions like banking or shopping. Authentication systems to verify identity. Protecting data storage such as personal documents or company records. RSA-OEP. RSA-OEP is a secure way to encrypt messages using the RSA algorithm with extra padding to prevent certain attacks. Imagine you have a secret note that says hello. To encrypt it with RSA-OEP, you might convert hello into a number, then scramble it using a special public key that everyone can see. The only way to unscramble it and get back hello is with a private key that only your friend has. Use cases. RSA-OEP is used for securely sending private information over the internet, like passwords or credit card numbers, so that only the intended recipient can read it. RSAPS algorithm. RSAPS is an advanced method to securely sign messages using RSA encryption. It ensures that a signature cannot be forged, even if someone tries to trick the system by choosing specific messages to sign. Think of it like a game of secret messages between you and a friend. You have a box with a special lock, public key, that anyone can close, but only your friend has the unique key, private key, to open. RSAPS adds extra secret symbols to the lock, making it even harder for anyone else to open the box without the right key. Use cases. 1. Online banking to verify transactions. 2. Email encryption to ensure the sender's identity. 3. Secure software updates to confirm the update is from a trusted source. Runge-Kutta method. The Runge-Kutta method is a way to predict how something moves by calculating its speed and position over small time steps. Imagine you throw a ball and want to know where it will land. You could guess where it is after 1 second, check how fast it's moving then, and use that to make a better guess for the next second. Do this a few times, and you'll have a good idea of where the ball will end up. The Runge-Kutta method does this by breaking time into small parts and updating predictions of speed and position step by step. Use cases. Predicting the path of a planet in space. Calculating the flow of air over an airplane wing, understanding how chemicals react over time in a mixture, modeling the growth of populations in biology. Run-length encoding, RLE. Run-length encoding, RLE, is a compression technique that shrinks the size of an image by recording the lengths of sequences of repeating colors instead of each individual color. Think of a row in an image with 10 white pixels. Instead of saying white, white, white 10 times, RLE summarizes it as 10 white. Use cases. RLE is great for images with lots of identical consecutive pixels, like simple graphics with solid colors, icons, or black and white documents. Run-length encoding. Run-length encoding is a simple method that compresses data by replacing repeating elements with a single value and a count of how many times it repeats. A, B, C, C, D, E, A becomes 5A, 3B, 2C, 1D, 2A. Use cases. 1. Compressing text files with lots of repeated characters. 2. Reducing the size of simple graphic images like icons or logos. 3. Optimizing data storage in databases when similar values recur frequently. Schnorr signature. A secure method to sign digital messages, ensuring they're sent by the true sender. Imagine you want to send a note that only your friend can confirm it's from you. With the Schnorr signature, you can do this by creating a special autograph for your message. Here's a kid-friendly example. You pick a secret locker combination, like choosing a secret number, X, and then using a math trick, you share a different number, the public key, Y, that tells friends it's your locker without giving away your secret combination. For instance, you pick a big secret number, X equals sign 4, and you both know a special number, P equals sign 23. Another number, G equals sign 5, is used to calculate Y by doing the math, 5 circumflex 4, which is 625, and then dividing it by 23 and taking the remainder, which is 4. You tell everyone y equals sign 4. To sign a note, you follow some steps with a bit of math to get the signature made of two parts, R and S. You share the note and these parts. Your friend uses Y, R and S with a bit of math. If their result is R, then the note is definitely from you. Uses: sending secure emails, making safe online transactions, verifying the authenticity of digital documents. Secant method. The secant method is a way to find where a curve meets the x-axis by using two starting points and repeatedly creating new estimates. Imagine a curve on a graph that touches the x-axis, and you want to know exactly where it does. First, you guess 2 points where the curve might meet the x-axis. Then you draw a straight line, the secant, between these guesses. Where this straight line crosses the x-axis is your new guess. Repeat this with your new guess and one of the old ones to get closer to the answer. It's like playing hot or cold to find a hidden spot. Use cases. The second method is used in math and engineering to solve equations that are difficult to solve with pen and paper. It is often used in situations where other methods like the Newton-Raphson method can't be applied. Segment tree algorithm. The segment tree algorithm is a method that organizes numbers into a binary tree to enable quick searches for the smallest number within a specific range of numbers. Think of a line of numbers like steps on a ladder. You want to find the smallest step between 2 points you choose. By arranging these steps into a pyramid, segment tree, where each block covers a range of steps, you can easily find the smallest step in the range by checking the blocks that cover it, instead of checking each step one by one. Use cases. Finding the minimum or maximum in a range of an array. Updating the value of an element in an array and then finding the new minimum or maximum quickly. Calculating sums or other aggregate functions within a range of an array without recalculating everything each time. Segment tree. A segment tree is a tree-like data structure that allows for fast updates and retrieval of information about intervals or segments within an array. Imagine you have a list of numbers and need to find out the highest number within certain parts of the list quickly. A segment tree can help with that. It breaks down the list into smaller chunks, figures out the highest number for each chunk, and organizes this information in a tree for rapid access. For example, with the list 3, 1, 5, 4, 2, 6, you might create segments like 3, 1, 5, 4, and 2, 6. The segment tree will remember the highest number in each segment. Then, if you want to know the highest number between the second and fourth numbers in the list, you can just check the tree and get your answer quickly. Segment trees are useful in situations where you need to manage and query data about ranges, such as finding sums or maximums in parts of an array, for computer graphics, and in various other computational geometry problems. Selection network algorithm. The selection network algorithm is a method for sorting a predetermined number of elements in parallel. It sequentially eliminates options based on set criteria until the most suitable one remains. Suppose you want to choose the best fruit out of an apple, orange, banana, and grape. You decide you want a fruit that's easy to carry, so the grape is out. Then you want one that doesn't need peeling, so the banana and orange are gone. You're left with the apple as it meets your preferences. Use cases. The algorithm can be applied in various scenarios such as determining priority tasks, selecting the right candidate for a job, or deciding which product to buy, always ensuring the choice aligns with the predefined requirements. Selection sort algorithm. Selection sort is an algorithm that organizes a list by repeatedly finding the smallest element from the unsorted section and moving it to the end of the sorted section. Imagine lining up your toy cars by size. You find the smallest car and put it first. Then you find the next smallest car from the remaining ones and place it second. Repeat this until all cars are lined up from smallest to largest. Use cases. This algorithm is used when a simple sorting method is needed and efficiency is not a primary concern, typically with small lists. It's useful for educational purposes to demonstrate basic sorting principles. Self-organizing map, SOM. The self-organizing map is a method for computers to organize information by finding patterns without being told what to look for. Think of the self-organizing map like a coloring book. You have lots of crayons, data points, and an empty picture, the map. The crayons don't have labels, so you don't know what color they are until you use them. As you start coloring, you place similar colors like light green next to dark green, close to each other. Gradually, your picture becomes organized into areas of similar colors, even though you didn't know the colors at the start. Use cases, sorting animals into groups based on their characteristics. Organizing a library of music by genres without knowing the songs. Grouping customers with similar buying habits for marketing. SHA-256 is a method for turning information into a unique, fixed-size string of characters to ensure that data hasn't been tampered with. It's like turning a secret note into a puzzle that only you and your friend know how to solve. If you write a note and use SHA-256, it scrambles the message into a mix of random letters and numbers. Your friend, who knows how to solve the puzzle, can change it back into the original note to read it. Use cases. SHA-256 is widely used to check the authenticity of digital files, secure sensitive data, and in the creation of digital signatures that verify the identity of the sender of an electronic message. Shaker. Sort shaker. Sort is a sorting technique that alternates between forward and backward passes to arrange items in order, similar to the way you shake a set of marbles to sort them by size. Imagine you have a row of numbered cards. You compare two adjacent cards and swap them if they're out of order. First, you go from the beginning to the end of the row, and then from the end back to the beginning, like a shaking motion. You repeat this process until all the cards are in the correct order. Use cases. Shaker sort can be used in applications where bidirectional sorting could lead to faster organization, such as small lists on limited resource devices or for educational purposes to demonstrate sorting concepts. Shamir's secret sharing. Shamir's secret sharing is a method of dividing a secret into multiple parts, where a specific number of parts are needed to reconstruct the original secret. Imagine you have a code to unlock a treasure chest. Instead of giving the whole code to one friend, you break it into 3 different parts and give each part to a different friend. If you ever want to open the chest, you need at least 2 of your friends to combine their parts of the code to unlock it. Use cases. This technique is useful for securing sensitive information, like encryption keys or access codes, and ensures that no single person has the full secret. It's used in data security and protecting backup information. Shank's baby step giant step algorithm. A method for quickly finding the discrete logarithm in a cyclic group by alternating between small and large steps to reduce the number of calculations needed. Imagine you're in a maze with numbered rooms, and you need to figure out the number of steps to reach a specific room. You start by taking one small step, baby step, into the next room and noting the number. Then you take a large leap, giant step, ahead several rooms and note that number too. You continue alternating between baby steps and giant steps, each time keeping track of the room numbers until you land in a room with the same number from both a baby step and a giant step. Once this happens, you can calculate the total number of steps to reach your target room without having to visit every single room. Use cases. Cryptography for securing data by solving complex mathematical problems, computer science and algorithms for efficient problem solving. Any application involving large cyclic groups where the discrete logarithm problem arises. Shell sort shell. Sort improves insertion sort by comparing elements separated by a gap, reducing the gap size over time. Imagine you want to organize your books on a shelf by color, but instead of moving them one by one, you try the shell sort method. You start by organizing every 5th book. After that, you organize every 3rd book. Finally, you sort each book one by one. Gradually, your books are sorted without moving them all at once. Use cases. Sorting data in an efficient manner when an array is of moderate size. Reducing the number of swaps compared to traditional insertion sort. When a mostly sorted array needs quick finishing touches. Shell sort algorithm. Shell sort is an efficient method of sorting that first compares distant elements and then gradually reduces the distance until elements are directly adjacent. Imagine you have a row of numbered cards and you want to put them in order. Instead of just comparing cards that are next to each other, you start by comparing cards that are several spots apart. For example, you look at every 5th card. After sorting those, you move to every third card, then every second card, and finally, you compare cards that are right next to each other. This method helps sort the cards quicker than just comparing one pair at a time. Use cases. Organizing large sets of data where simple sorting takes too long. Improving the efficiency of data arrangement in databases. Sorting files on a computer where elements are initially far apart. Shor's algorithm. Shor's algorithm is a method used by quantum computers to quickly find the factors of large numbers, much faster than traditional computers can. If you want to find out which two numbers multiply to make 15, Shor's algorithm can quickly tell you the answer is 3 and 5. Use cases. Shor's algorithm is useful for breaking encryption, researching materials and drugs, and solving complex mathematics that involve large numbers. Shortest common supersequence algorithm. The shortest common supersequence algorithm finds the smallest string that contains two given strings in the same order as they originally appear. Consider two strings, ABC and CDE. The shortest common supersequence is ABCD, which keeps the original order of characters and is the smallest string that does so. Use cases. This algorithm is used in areas involving string processing and manipulation, such as DNA sequencing, text editing, and data compression. Shortest job next, SJF. Shortest job next, also known as shortest job first, SJF, is an efficient scheduling method that picks the task with the shortest duration to complete first among all available tasks. Imagine you have 3 snacks to eat: a small cookie, a medium-sized granola bar, and a large fruit salad. Using the shortest job next method, you would eat the small cookie first because it will take the least time to finish. Use cases. This algorithm is used in computer operating systems to manage which programs get to use the computer's processor next, as well as in real life to organize tasks such as completing homework or serving customers based on wait time. Shortest path algorithm. This algorithm finds the quickest route from one point to another in a network, like a roadmap or computer network. Pretend you're in a maze. To find the quickest way out, you use the right-hand rule, keeping your right hand on the wall while you walk. This trick helps you reach the exit without getting lost. Use cases. It's used for planning routes in GPS systems and organizing data in computer networks. Shortest remaining time, SRT. Shortest remaining time is a scheduling algorithm that gives priority to the process with the least time left to complete. It is like choosing to help the friend who has the smallest amount of work so that everyone finishes together quickly. Suppose 3 friends have different chores that take 5, 10, and 15 minutes. The SRT algorithm would help the friend with the 5-minute chore first, then the one with the 10-minute chore, and finally the one with the 15-minute chore. Use cases. SRT is used in operating systems to manage process execution, ensuring that tasks requiring less time are completed first, leading to efficient use of the computer's resources and faster overall performance. Shortest remaining time. First SRTF, shortest remaining time first SRTF, is a method where the task with the least amount of time left to finish is the one that gets done next. If a new task comes in that can be finished quicker than the current one, the new task is done first. Think of having a mix of quick and slow video games to play. You start with the quickest one. If a friend brings over an even quicker game, you play that one first instead. Use cases. 1. Operating systems use it to decide which program to run next. 2. Factories use it to schedule jobs so that they can get more done in less time. 3. It's used in places like airports to decide which flights get to take off or land next, based on how quickly they can be ready. Sieve of Eratosthenes. This algorithm quickly finds all prime numbers up to a certain number. It marks non-prime numbers, leaving the primes uncrossed. Imagine you have a list of numbers from 1 to 100. The sieve of Eratosthenes tells you which ones are prime. 1. Circle number 2, it's prime, and cross out all multiples of 2. 2. The next uncrossed number is 3. Circle it, it's prime, and cross out all its multiples. 3. Keep circling the next uncrossed number, prime, and crossing out its multiples until the end. 4. The circled numbers are the primes. This method is used to find prime numbers for math problems, in cryptography, and anywhere you need a list of primes. Simon's algorithm. Simon's algorithm is a quantum algorithm that efficiently finds a hidden pattern in a function. Imagine we have a set of cards. Some are duplicates, but we don't know which ones. We use Simon's algorithm, which is like a magic trick that quickly reveals which cards are pairs without checking them one by one. Use cases. Simon's algorithm is used in quantum computing for cryptography, particularly for breaking certain types of codes that would be very secure against traditional computers. Simplex algorithm. The simplex algorithm is a method used to find the optimal solution to problems that involve equations with multiple variables. Imagine you have a lemonade stand and you want to make as much money as possible. You need to decide how many cups of lemonade and cookies to sell, but you have limited sugar and flour. The simplex algorithm helps you figure out the perfect mix of lemonade and cookies to maximize your profit. Use cases. 1. Businesses use it to minimize costs or maximize profits. 2. It helps in planning and resource allocation. 3. Engineers use it to optimize design and operation processes. Simulated annealing algorithm. A probabilistic method to solve optimization problems by exploring options, sometimes accepting worse ones, and gradually focusing on the best solution. Imagine you're playing a game where you must find the best route to a treasure. At first you choose routes randomly. When you find a good route, you remember it. Sometimes you even try a bad route, just in case it turns out to be good later. Over time you become pickier, choosing only routes that seem to lead to the treasure. Use cases. Scheduling tasks to minimize delays. Arranging components on a circuit board to reduce wiring. Finding the shortest path for delivery routes. Optimizing layouts in manufacturing to save space. Simulated annealing. Simulated annealing is a strategy for finding an approximate best solution to a problem by exploring various options, including some that may not initially seem ideal. It's like being a treasure hunter who sometimes has to go down the wrong path to eventually find the most valuable treasure. Imagine you're at an ice cream shop with many unique flavors. You want to find the yummiest one. You start by sampling a flavor randomly. If the next flavor you try is tastier, you remember it. But even if you try a less tasty one, you don't give up. You keep trying different flavors, sometimes even those that might not seem as good, until you find the one that tastes the best to you. Use cases. Simulated annealing is used in various situations such as 1. Scheduling. Finding the best schedule for machines in a factory or classes in a school. 2. Route planning. Figuring out the most efficient delivery routes for trucks. 3. Engineering design. Optimizing the design of parts or systems to improve performance. Singular value decomposition (SVD). Singular value decomposition is a mathematical method that breaks down a matrix into 3 simpler parts, helping to understand the structure and relationship between its components. Imagine you have a big jigsaw puzzle. SVD is like a magical lens that shows you 3 things: the edges of the puzzle, where each piece goes, the importance of each piece, and tips on how to best assemble the puzzle. Use cases. SVD is used in image compression, where it helps reduce the size of images without losing quality. It's also used in recommendation systems to suggest products or movies to users by understanding patterns in data. Skip list. A skip list is a smart way to arrange data that lets us quickly find, add, or remove items. It's like a set of stairs with shortcuts. Imagine we have a stack of boxes with numbers 1 to 10. Normally, to find box 5, we'd count from 1 to 5. With a skip list, we might have a shortcut from box 1 to box 3, then another shortcut from box 3 to box 5, which gets us there faster. Skip lists are used in databases, search engines, and anywhere we need to manage lots of data smoothly. Sleep sort. Sleep sort is an unconventional algorithm that uses time delays to sort numbers. Each number creates a delay before it appears, with shorter delays for smaller numbers. Imagine you have the numbers 1, 4, and 2. You make each number take a nap for the number of seconds it represents. The number 1 wakes up after 1 second, number 2 after 2 seconds, and number 4 after 4 seconds. They line up as they wake up. 1, 2, then 4. Use cases. Sleep sort is more of a novelty and isn't used in real-world applications due to its impracticality and dependency on time, but it can be a fun example when learning about sorting algorithms and threads. Slime mold algorithm. The slime mold algorithm is inspired by the way slime molds naturally seek out efficient paths to food. It's a method for finding the best route to a goal by simulating this behavior. Imagine a maze with a piece of cheese at the center. A slime mold starts at the entrance and spreads out, marking its trail. As it explores different paths, it strengthens the trails leading closer to the cheese and abandons the less efficient ones. Eventually, the mold forms a strong, clear path directly to the cheese. This is like using the slime mold algorithm to solve the maze. Use cases. The slime mold algorithm is useful for solving complex problems like finding the shortest path in a network, optimizing transportation routes, and planning efficient logistics. Slow sort. Slow sort is a purposefully inefficient method of sorting that compares and arranges items by repeatedly selecting the smallest one from a list. Think of sorting toy blocks by color. With slow sort, you'd find the first color, set it aside, then search through all the remaining blocks for the next color, and repeat until all blocks are sorted. This takes a long time as you look through all the blocks for each color. Use cases. Slow sort is mainly used for educational purposes to demonstrate inefficient sorting and to contrast it with more efficient sorting algorithms. It's not used in real-world applications due to its slowness. Smith-Waterman algorithm. The Smith-Waterman algorithm is a method for finding the most similar parts of two sequences by comparing them piece by piece and scoring the similarities. Imagine Alice and Bob have lists of their favorite hobbies and want to compare them to find which hobbies they both enjoy the most. They use the Smith-Waterman algorithm to score each pair of hobbies for similarity. Soccer and soccer would score highly, while soccer and dancing would score lowly. The algorithm then connects the highest scoring pairs to build a path. For Alice and Bob, it finds that soccer, painting, and cooking are common, indicating they have 3 hobbies in shared interest. Use cases. The Smith-Waterman algorithm is mainly used in bioinformatics to align portions of biological sequences, like DNA, RNA, or proteins, to find the most similar regions, which can be important in understanding genetic relationships and functions. Smooth. Smooth sort is an efficient sorting algorithm that rearranges items in a sequence by comparing and ordering them. It's like heap sort, but designed to perform better in the worst-case scenarios. Imagine you have a collection of cards with numbers, and you want to line them up so the numbers go from smallest to largest. Smooth sort is like a clever game where you compare pairs of cards and swap them if they're out of order, doing this over and over until all the cards are sorted. First, smooth sort compares the first card with the second one. If the first card has a bigger number, they swap places. It continues comparing and swapping pairs of cards down the line. After the first pass, it starts over, but now it's smarter about which cards it compares, thanks to a special pattern it follows. It also remembers which cards are already sorted, so it doesn't have to check them again. In simpler terms, smooth sort is a smart and efficient way to put things in order by comparing them with each other and swapping whenever needed, going back and forth until everything is perfectly organized. Use cases. Organizing data in databases. Sorting files by name or date on a computer. Ordering numbers or items in a list for analysis. Arranging products by price or category on an e-commerce site. Smooth sort algorithm. Smooth sort is an efficient sorting method that improves on the basic concept of heap sort. It is designed to be fast, with a time complexity that doesn't exceed O and log n in the worst case. It works by recognizing and leveraging patterns within the data to sort items in an intelligent and swift manner. Imagine sorting a deck of cards by number and suit. You place the cards on a table, and a smooth sort machine starts to compare pairs of cards. If a card is out of place, it swaps them. Unlike random swapping, the machine finds sequences of cards that are already in order and uses this knowledge to minimize the number of swaps needed. This way, the cards get organized faster and with fewer moves. Use cases, organizing a music library by genre, artist, or album name. Sorting a list of students by their grades or attendance. Ordering products in a warehouse based on their size or category. Solove-Strassen primality test. This algorithm helps us figure out if a number might be prime by using some special math rules. It's not always right, but it's pretty quick. To see if 17 is prime, we pick a random number like 3 and do some math with it and 17. If the results match after we do this math, then 17 could be prime. If they don't match, 17 is not prime. Use cases. The Solove-Strassen test is used by computers to check if big numbers are prime, especially in cryptography, where prime numbers are super important for keeping information safe. Sorting algorithm. This method organizes items by selecting the smallest one first and then sequentially arranging each following item in order. Simply 1. Gather all your action figures. 2. Find the shortest action figure. 3. Place it at the start of your display shelf. 4. Find the next shortest figure and place it next to the first one. 5. Continue until all figures are lined up from shortest to tallest. Use cases. The sorting algorithm is used to organize things by size, like lining up books by height on a shelf, or arranging pencils from shortest to longest in a case. Sphinx algorithm. The Sphinx algorithm is a secure method for digital signatures that remain safe even from powerful quantum computers. Think of it like a secret handshake that you and your best friend have. No one else can copy it because it's your unique creation. Use cases. The Sphinx algorithm is used for secure communication, protecting sensitive data, and ensuring that digital documents haven't been tampered with. Splay trees. Splay trees are a type of binary search tree that moves elements you've recently used to the top, making them quicker to find the next time you need them. Imagine your toys are sorted in a splay tree. Your favorite action figure, which you play with often, stays near the top, so it's easy to grab quickly. Less favorite toys end up lower in the tree and take a bit longer to find. Use cases. Splay trees are useful in scenarios where you need fast access to recently used items. This can be handy for keeping track of frequently visited websites in a browser, or managing data in a way that prioritizes the most recent or common requests. Spread sort algorithm. Spread sort is a sorting method that organizes numbers by comparing pairs and swapping them based on their value range, gradually increasing the comparison distance until all numbers are in order. Imagine you have a row of numbered blocks. You compare the first 2 blocks, and if the first is bigger, you swap them. Now skip 1 block and compare the next 2, swapping if needed. Continue this pattern, doubling the number of blocks you skip each time until all the blocks are in the correct order from smallest to largest. Use cases. Organizing large sets of numerical data efficiently. Sorting numbers in situations where the range of values helps determine their final position. Stochastic gradient descent. A method to find the best settings for a machine learning model by making small adjustments. Imagine you're at the bottom of a hill and need to get to the very top where a flag is, but it's foggy and you can't see the whole path. You start walking uphill, and with each step you feel if you're going higher. If a step takes you lower, you change direction. Step by step, you figure out the way to the top to reach the flag. Use cases. Stochastic gradient descent is used in machine learning to improve things like speech recognition on your phone, recommending videos on websites, or even helping self-driving cars make decisions. Stooge sort algorithm. Stooge sort is a sorting algorithm that repeatedly divides a list into 2 unequal parts, sorts each part, and then swaps elements if needed until the entire list is in order. Imagine you have 9 toys lined up and you want them from smallest to largest. You ask your big brother to sort them. He looks at the first and last toy, swaps them if the first one is larger, then divides the toys into 2 groups, the first 6 and the last 6. He sorts each group this way, and if needed, he swaps the toys again. He repeats this process until all toys are sorted. Use cases. Stooge sort isn't used in practice due to its inefficiency, but is interesting from a theoretical standpoint as an example of recursive sorting algorithms. It can be used for educational purposes to teach the concepts of recursion and sorting. Strand sort is an algorithm that sorts items by repeatedly removing sorted sequences from the list and merging them. Simply example. Imagine you have a mix of colored beads, red, blue, green, yellow. Strand sort separates each color into its own group. First, take all the red beads and make a pile. Then do the same for blue, green, and yellow beads. After sorting them into color piles, you merge them back into one big sorted pile. Use cases. Strand sort is used in scenarios where data needs to be sorted in a sequence, similar to organizing scattered items into ordered groups before combining them into a single sorted arrangement. Strasson's algorithm. Strasson's algorithm is an efficient method for multiplying two matrices by reducing the number of multiplications needed compared to the standard approach. Imagine you want to multiply two large numbers, such as 1234 by 5678. Instead of using the traditional long multiplication method, Strasson's algorithm breaks down each number into smaller parts, 12, 34, 56, 78, and combines them using only 7 multiplications, along with some additions and subtractions. This simplifies and speeds up the entire process. Use cases. Strasson's algorithm is used in computer science and engineering when dealing with large matrices, such as in graphics processing, scientific computing, and any application requiring efficient computational performance. String matching algorithm. This algorithm searches for a specific sequence of characters within a larger text. Imagine you're looking for the word cat in a sentence. You check each word until you find cat. String matching is used in search engines to find keywords, in word processors to find phrases, and in DNA sequencing to locate genetic patterns. Strongly connected components. Algorithm. This algorithm identifies groups of connected points in a certain direction within a network, where each point can reach every other point in the same group. Imagine a map of a group of islands where one-way bridges connect the islands. The algorithm helps to find which islands can be visited from any other island in the same group without leaving the group. Use cases. It's used to analyze networks like social media to see who influences whom, understand web pages' interconnections for search engines, and find related tasks in a project where one task depends on others. Subset sum problem. This algorithm determines if a group of numbers can be added together to match a target sum. Imagine having 6 candies labeled with the numbers 1, 2, 3, 4, 5, and 6. You want to know if you can choose some of these candies that, when their numbers are added together, equal 10. By selecting the candies with numbers 1, 2, and 7, their sum is 10, and you've solved the problem. The subset sum problem is used in budgeting to find if you can purchase a combination of items within a set budget, and in cryptography for security algorithms. Support vector machine, SVM. A support vector machine is a type of algorithm that helps computers classify things or predict outcomes by finding the best dividing line or curve. Imagine you want a computer to identify different fruits like apples, bananas, and oranges. You could use an SVM to help it learn. You'd measure things about the fruit's like size and color, then plot these on a chart. Each fruit type would be a point in a different color. The SVM algorithm looks for the best line or curve, a decision boundary, to separate the fruit types on the chart. After it finds this line, the computer can use it to identify new fruit types based on their measurements. In short, an SVM helps a computer distinguish between items, like fruits, by teaching it the best way to draw a separating line or curve. Use cases. Identifying different types of objects in pictures. Sorting emails into spam and non-spam. Predicting whether a loan applicant is low or high risk. Sutherland-Hodgman algorithm. The Sutherland-Hodgman algorithm is a method for trimming a polygon so that only the part inside a rectangular area is shown. Imagine drawing a star on a large sheet and then placing a smaller rectangular frame over it. The algorithm helps you trace only the parts of the star that can be seen within the frame, discarding the rest. Use cases. The algorithm is used in computer graphics to display only the parts of shapes that fit within the screen or a designated area. Taboo search algorithm. Taboo search is a method for solving complex problems by trying to improve a solution step by step. It remembers the recent steps it has taken and avoids repeating them to find new and better solutions. Imagine you're playing a game of hide and seek in your neighborhood, trying to find the best hiding spot. Each time you hide in a spot, you make a note not to hide there again soon. This way, you'll discover new hiding places and maybe find the best one. Use cases. Taboo search is used for planning efficient delivery routes, scheduling flights or classes, and organizing manufacturing processes where you need to find the best order or arrangement of things. Tarian's algorithm. This algorithm helps identify groups of points in a network that are all reachable from each other, much like finding interconnected neighborhoods in a city. Imagine a maze of one-way streets. Starting from one street, you try to explore all the streets you can reach. You mark each street you've visited with a number to remember the order. If you hit a dead end, you go back and try a different route. Once you've explored everywhere, you'll know which streets are connected to each other. Use cases. It's used in computer science to organize data, plan transport routes, and understand social networks. Tarian's strongly connected components algorithm. This algorithm identifies groups of nodes in a directed graph that are all reachable from each other, known as strongly connected components. Imagine a schoolyard with paths connecting different play areas. If you can travel from one play area to any other in the same group without crossing into another group, that's a strongly connected component. The algorithm starts at a random play area and explores the paths, marking each area visited. If it circles back to the start, a group is found. This process repeats until all connected groups are identified. Use cases include understanding social networks, analyzing web pages for search engines, and mapping routes in transportation networks. Ternary search. This is a method to find something in a sorted list by cutting the list into 3 parts and checking the middle part first. Imagine you're in a toy shop looking for one specific toy. The shop is split into 3 areas. You start searching in the middle area. Then if the toy isn't there, you cut that area into 3 smaller areas and search the middle again. You keep doing this until you find the toy, or until the area is so tiny that if the toy were there, you'd see it. If it's not in the middle, you do the same in the first area and then the last area if needed. Use cases. Finding a number in a sorted list of numbers. Discovering the exact point where a line starts to go up or down on a graph. TimSort is a sorting algorithm that combines the simplicity of insertion sort with the efficiency of merge sort to arrange data in a specific order. It is the default sorting technique in Python. Consider sorting a deck of cards. First, you sort small groups of cards using insertion sort. Then you merge these groups together like in merge sort until the entire deck is ordered. Use cases. TimSort is ideal for sorting large datasets in programming languages like Python and is optimized for real-world data that often contains ordered sequences. It's used in systems that require efficient and stable sorting, like databases and file systems. Topological sorting. Topological sorting is a method to arrange the elements of a directed graph without cycles, acyclic, in a specific sequence where each item comes before all the items it points to. Imagine you need to get dressed. You have to put on your underwear before your pants and your socks before your shoes. Topological sorting helps you find the right order. Underwear first, then pants, socks, and finally shoes. Use cases. Scheduling tasks with dependencies, like construction steps in building a house. Organizing courses you need to take in school where some must be completed before others. Managing software compilation where certain modules depend on others. Tournament sort is a sorting method that arranges items by matching them in pairs, similar to competitors in a tournament, to find out which one is greater and should move on to the next round until the greatest item emerges as the winner. Imagine 8 students competing in a spelling bee. They compete in pairs, and the winner of each pair moves on to the next round. This keeps happening until only one student remains who is the best speller. Use cases. Sorting a list of numbers from smallest to largest. Organizing players in a sports competition based on skill level. Arranging tasks by priority in a to-do list application. Toy sorting algorithm. This algorithm helps to quickly and easily organize scattered toys into designated areas based on their types. 1. Create categories like dolls, cars, blocks, and stuffed animals. 2. Assign a specific place for each category like shelf for dolls, toy box for cars. 3. When a toy is picked up, refer to the list and place it in its assigned spot. Use cases, keeping a child's room tidy by sorting toys. Helping a child remember where each type of toy belongs. Teaching organizational skills and categorization. Traveling Salesman Problem, TSP, Solver. The TSP solver algorithm finds the shortest path to visit a series of cities once and return to the starting point. Imagine you have a list of cities like dots on a map. You want to draw a line from one dot to another, visiting each dot just once and ending up where you started. The goal is to make this line as short as possible. The TSP solver might try every possible way to connect the dots, a brute force approach, and choose the shortest one. Use cases, planning delivery routes for trucks, organizing postal mail routes, scheduling flights for airlines. Treep. A treep is a data structure that efficiently organizes and manages items based on two attributes, their value, like a binary search tree, and a randomly assigned priority, like a heap. Imagine you have a deck of cards. Now, you want to stack them so you can quickly find any card you need. The treep helps you stack the cards in a special way. Each card has a number, its value, and a secret number, its priority. You arrange the deck so that the card numbers go up from left to right, like steps, and the cards with the higher secret numbers are near the top of the stack. This way, your favorite cards are easy to grab, but you can still find any card quickly. Treeps are useful in many scenarios, such as managing databases where you need quick access to data, arranging users based on their permissions and activities, and even in computer graphics for organizing objects on the screen. Tree sort tree. Sort is a sorting technique where we create a binary search tree from the elements we want to sort and then visit them in a specific way to put them in order. Imagine we have some numbered blocks and we need to line them up from smallest to biggest. To use tree sort, we first choose a block to be the base. We then put smaller numbered blocks to the left and larger numbered blocks to the right, building a tree shape. After our tree is built, we collect the blocks starting from the leftmost side, moving to the right, and that gives us our sorted lineup. Use cases. Sorting numbers or other items that can be compared. Organizing data in a way that's easy to search through later. Triangular mesh. Sort a simple sorting algorithm that organizes data for easy access within a triangular structure. Imagine sorting colored beads into a triangle-shaped board. You place one bead in each hole. After filling it up, you swap beads in rows to create a pattern, then do the same with columns until all beads are arranged by color. Use cases, efficiently managing and rendering 3D graphics, optimizing network data flow, and organizing spatial databases. Triangular sort algorithm. Triangular sort is a method where you sort numbers by repeatedly comparing and rearranging groups of 3 in a specific pattern until they're all in the correct order. Imagine you have the numbers 5, 3, and 7. 1. Compare 5 and 3 and swap them to get 3 and 5. 2. Compare 5 and 7. They're in order, so no swap is needed. 3. You now have 3, smallest, 5, middle, and 7, largest, properly arranged. Repeat with different groups of 3 numbers until the whole set is sorted. Use cases. Triangular sort can be used in educational settings to teach basic sorting concepts and in simple computer programs where sophisticated sorting algorithms are not necessary. It's particularly useful for small sets of data. Trie algorithm. A trie is a special type of tree used to store words in a way that makes it quick to find them. Imagine you have a drawing with branches. Each branch is a letter. To find a word like cat, start at the top and follow the branches for C, A, and T. If you can follow all the branches for cat, then cat is in your drawing. Use cases. Tries are useful for checking if a word is in a dictionary, helping with autocomplete on your phone or matching words in a game. Ukanen's algorithm. Ukanen's algorithm efficiently constructs a suffix tree for a given string in a short amount of time. Imagine you have a long string of letters, like a word but way longer. Ukanen's algorithm helps you build a special kind of tree that shows all the possible endings of that string. It's like taking the word and breaking it down into all the smaller words you can find at the end of it. This tree helps with finding things in the string really quickly. For example, if your string is banana, Ukanen's algorithm helps you create a tree that includes a, na, ana, nana, anana, and banana. Ukanen's algorithm is particularly useful for tasks like searching text for patterns, analyzing genomes in biology, and auto-completing words when typing on your phone or computer. Unshuffle sort algorithm. This algorithm sorts items by repeatedly taking an item from a mixed-up collection and inserting it into its proper place in a new ordered collection. Simply put, imagine you have shuffled cards. You take one card and start a new pile. Then you take the next card and decide if it goes before or after the first card. Keep doing this and soon all cards will be in order. Use cases. Sorting playing cards. Organizing books on a shelf by height. Arranging files in alphabetical order. Van Emde-Boas layout. The Van Emde-Boas layout is a method of arranging a special kind of tree, called the Van Emde-Boas tree, into an array. This setup improves the speed of searching for elements by making memory access more efficient. Imagine sorting your toys into boxes so you can find any toy quickly. Each box is labeled with a size and color. Now, if you want a small red toy, you go straight to the box for small red toys, find it fast and play. Use cases. Quick searches in databases, efficient network routing, fast access in memory systems. Viterbi algorithm. The Viterbi algorithm determines the most likely sequence of events that are not directly observable, based on a set of known outcomes. Imagine a game of guessing which cup a ball is under after someone has shuffled them. The Viterbi algorithm is like a note you keep, where you write down which shuffle moves had the highest chance of the ball ending under a specific cup. As the game progresses, you use your notes to guess where the ball is most likely to be. Use cases. 1. Deciphering encrypted messages. 2. Predicting weather patterns. 3. Recognizing speech in voice recognition software. Wagner-Fisher algorithm. The Wagner-Fisher algorithm calculates how many edits are needed to change one word into another by using a grid to compare the differences between the words. With the words cat and act, create a grid with cat across the top and act down the side. Fill in the grid with zeros for matching letters and ones for differences. Then add the lowest numbers from adjacent cells to find the minimum edits. Underscore a CT, underscore 0123 C1112A21222T3222. The bottom right number 2 indicates that 2 edits are needed to change cat into act. Use cases. The Wagner-Fisher algorithm is useful for spell checking, DNA sequencing, and anywhere it's necessary to measure how similar 2 strings are by counting the required edits. Whale optimization algorithm. The whale optimization algorithm, WOA, is a method for finding the best solution to a problem, modeled after the way humpback whales hunt for the best feeding spots. Imagine a group of whales trying to find the perfect place to feed. They spread out, communicate with each other about potential spots, and gradually hone in on the area with the most fish. Use cases. UOA can be used in various fields such as engineering, computer science, and economics to solve complex optimization problems like designing efficient networks or finding cost-effective routes for delivery. Winternitz one-time signature algorithm. The Winternitz one-time signature algorithm is a secure method for creating digital signatures that can only be used once. It uses a series of numbers generated through cryptographic hash functions to sign messages uniquely. Imagine you have a unique sticker you put on a letter to prove it's from you. Once you send the letter, you can't use that sticker again. You need a new sticker for the next letter. Use cases. The algorithm is used in secure communication to ensure messages are authenticated and to prevent forgery, commonly in scenarios where high security is necessary, like blockchain technology and secure email. Word break problem. The word break problem is about figuring out if you can split a long word into smaller words from a given list. With the word illikiisikream and the list I'd like ice cream, the algorithm checks if illikiisikream can be split into I like ice cream. Use cases. This algorithm is used in text editing software to check spelling and in voice recognition systems to understand spoken words. XMSS algorithm. The XMSS algorithm is a secure method used to create a digital signature that cannot be broken by quantum computers. Imagine you have a box that only opens with a specific key you've made. You place a note inside and lock it. XMSS is like that key, ensuring that only people with the right key can open the box and read your note. Use cases. XMSS is used to protect important digital messages. It ensures that only the intended recipient can access the message and verifies that the message has not been tampered with. Z algorithm. The Z algorithm quickly finds patterns in text. It compares segments of two strings to identify exact matches. Imagine looking for the word cat in catapult. The Z algorithm combines them into cat $catapult and checks each segment for matches, identifying that cat appears at the start. Use cases. The Z algorithm is used for pattern searching in DNA sequences, plagiarism detection in texts, and searching words in documents.